Okay, thanks everyone for coming. Sorry I can't be with you in person due to a COVID situation in our house, but it's great to have you all here. Just wanted to say like a very mini quick intro to the Gradual project. Of course, many of you will know about this project that we've been running here at Kent for some time now, and also joint with Augusta University. And one of the sort of research vehicles of our project is the Gradual language, which we have some recent release of, and yeah, I'm very excited about today's program. There's lots of really interesting talks. I have this slogan that I put in lots of stuff about how grading is about matching the structure of a proof or a program with the structure in the indices of the modalities, and I think we're going to see that in lots of different guises and different interpretations today, so it's going to be really fun. Just a thanks to everyone on the sort of team Gradual, lots of people here and at Augusta who are involved in this, PhDs and postdocs and academics. So thanks to all these people, and Peter down there, that's Harley student, who I don't have a picture for, and also some undergraduates who have been involved over the years as well. So yeah, we got lots of fun talks today. There'll be some coffee breaks and lunch breaks. For those in person, we can expense claim the coffees and the lunches, so Idris will be handling that. And yeah, you can see the schedule online. Hopefully the air conditioning will work well in SW101 for those in person, so that we can sort of make it to the end. There's a few slight changes to the short talk session at the end of the day. There's quite a few people who wanted to come in person but couldn't in the end because of COVID things, or had some changes going on. Yeah, and just to sort of say a bit about University of Kent, for those of you who couldn't make it, we're sort of down here in closer to France than to London, in Canterbury. We have this big, beautiful green campus that overlooks the city, overlooks the cathedral. Hope those of you who are there in person will be able to sort of mosey around later and see a bit of the town. And yeah, we have this campus sort of nestled in this parkland that overlooks the city. So I'll hand over to Andrew, who's going to be giving our first talk.
Yeah, let me go ahead and all right, you should now be seeing my slides, I hope.
Yeah, great. So
awesome.
Our first speaker is Andrew Hirsch. He's at MPI at the moment, but soon to be at the University of Buffalo. And he'll be talking about giving semantics to program counter labels via secure effects. Thank you, Andrew.
Yeah, thanks, Dominic. Like Dominic mentioned, I'm a postdoc right now at MPI in Saarbrücken, Germany, and will soon be a professor at University of Buffalo. I think technically I'm currently a research assistant professor there for some administrative reasons. So the work I want to talk to you about today is, well, first of all, it's joint work with my collaborator, Ethan Cicchetti, who's currently at the University of Maryland. But it's about program counter labels and secure effects. And what it's really about, it's about, if I can get the slide to change, it's about two different uses of graded monads and how they work together. And the two uses are information flow security and effects. In security, we use grades to represent security policies, and graded monads enforce a security condition called non-interference. In the effects world, grades represent effects, and graded monads are used to give semantics to type and effect systems. This means that in the effect world, the graded monads are defined as a transformer on the semantics of a type. The transformer has to supply the necessary effectful operations. Whereas in security, we actually treat monads as a black box, so we don't get to see inside of them. And this is actually really important for enforcing non-interference. And the way I want to start is by looking at the security side, which I suspect for most of you is going to be less familiar, but I'm going to take both sides slow. So if you're less familiar with the effect side, hopefully this will be fine for you as well. So when defining what's called a coarse-grained information flow language, what we need to do is we need to add a special type, which I've written here using L, corresponding to labeled types. So what we're doing is we're actually adding a information flow label or a security policy to the type and saying that this type needs to be treated with this policy. These policies have a preorder on them, which we call flows to, and intuitively, a label L1 flows to a label L2 if L1 is a less restrictive policy than L2. In order to use this to reason about security, we define a relation, which we write like this, which expresses information labeled at L can influence data of type T, or type tau, excuse me. That is, there's that either tau is a labeled type with a label L prime, where L flows to L prime, or it might be a product and then L needs to influence both sides of the product, or whatever for any other type constructors you have. But there's one really important exception and some related ones in more complicated systems, which is that there's no way, this should be a plus, not a times, excuse me, that's just a typo. There's no way for label L to influence a coproduct. Why? Because the choice of which side might need to be protected itself. Now, in order to use a label type, we can use this relation to define an eliminator, unlabeled, which takes a label type and just uses it as the type itself. We can use this to prove that that programs that type check are what's called non-interfering. And the basic idea is to run the program twice on two different secret inputs. Non-interference then says that the outputs have to be low equivalent. That is, the public parts, including effects, have to be the same as each other. And I want to mention this is a really beautiful visual representation that my collaborator Ethan came up with. And there's a lot of these throughout the talk. They're all shamelessly stolen from him. I'm not nearly as good of a graphic designer as he is. Okay, so that's the basic idea of non-interference, but things get more complicated when we have computational effects. For instance, what if I look at a secret Boolean, and if it's true, I write 0, but if false, I write 1 to some piece of state. This produces the same value either way, it's just unit, but any adversary who can see the state can now tell what the secret data was. This is what's called an implicit leak, or an implicit flow. In order to rule out these implicit flows, we keep track of an extra label in every typing judgment, which we call the program counter label, or the PC. This label keeps track of how sensitive the control flow is. That is, how much secret data has been used to determine whether or not we execute an instruction. So what we do is we don't allow any effects that might leak information based on the sensitivity of the context. So if you can write to the state, you can modify the state. You can only do that if the PC flows to the label of the state. That is, only if you're willing to let any adversary who can see the state know how you got to this instruction and that you got to this instruction. On the other hand, effects that don't create observable effects for the adversary are always fine. So reading the state is usually fine. It's allowed for any PC because an adversary can't observe that. Now we need to raise the PC when we are using labeled data. So we do that using a join operator. Usually these labels form a semi-lattice. This isn't actually required. You can do something a little bit more complicated if it's just a pre-order. But the idea here is that when we unlabel E1, it now has affected the control flow, so we need to add in its label to the PC. And an important piece of intuition that people use a lot is that this PC is a bound on the effects in the language. And our goal is to actually make this intuition precise. And in order to do that, we use monads to give semantics to effects. And let's look at how that works. The idea is that we split our semantics into two worlds: the effectful world, to which we want to give semantics, and the pure world, which we already understand the semantics of. We then find a function m from effectful types to pure types, along with a translation from effectful programs to pure programs. And this translation takes programs of type tau to programs of type m tau. For example, if I had a program E, which could read and write state, I can transform it into a program that takes in a state and produces a state. So M would be this appropriate arrow and product type. I imagine this is very familiar to almost everybody there. But with this, I can easily translate read as the function that returns the state, and write as the function which ignores its input and produces the state, or writes to the state, excuse me. With this, we can look at the example program from earlier and translate it to something more like this, which again does this manipulation. But now we can actually reject this program without using a program counter label at all. Because if the label sec doesn't actually flow to L state, this can't work. So by making the effect explicitly output type, we've gotten rid of the PC. And this feels like it's going to be really useful for our goal, which is to make this relationship precise. So this is the semantics of type and effect systems. And what they do is they add an effect judgment to every typing judgment. So for instance, we might have effects being read and write, and then read has read effect, write has a write effect, along with whatever other effects you might have. Unlabel is going to have both effects, and it's also going to require that L can affect tau 2. But we also need something more, because we need to reason about, can the adversary see through the effect what is going on here? So we need L to flow to some appropriate label, but it's not necessarily clear what that is. To solve that, we introduce a function from effects to labels. Just that simple. And we write it with a subscript. So I write L of epsilon, that's L subscript epsilon. And then we can ask that L flows to epsilon 2, to L of epsilon 2. That is, you should be able to see whether the, you should be able to see the effect of epsilon 2 if you can see the label L, because L determines whether or not epsilon 2 ever runs. I'm sorry about those parentheses there. That's just another typo. So in order to handle multiple effects, we need something more general than a monad. Maybe a graded monad, but maybe an indexed monad is what a lot of these things actually use. So an indexed monad is defined over a lattice of effects composed by join, and it's good enough for many type and effect systems. But it turns out actually not to be good enough for security because of the program, because of this program, which throws an exception if a secret is true, otherwise it doesn't, and then is composed with a write to the state. So if the secret is true, this write never actually happens. So there's actually two ways of solving the difficulty that shows up here. if the label of exceptions flows to the label of state, then whether or not we throw this exception determining whether or not we write to the state is fine, because anybody who could see that we threw the exception can see that we wrote to the state. The other option, which is a more general option, is to allow a partial algebra of effects. So we require that the exception label flow to L epsilon in order to be able to perform an epsilon after a possible exception. Index monads can't handle this because join is total. So we actually move to productors, which are based on effectors of effects rather than lattice. And this is actually a generalization of a graded monad because they aren't based on a monoid, but actually a relation between a list of effects and effects. And this means that we can express partiality, which is actually really good for security. Productors come with a semantic framework, that is a series of rules that say when a type and effect system can be given semantics via productor. This can be used to axiomatize effectful languages so that we can prove theorems about them. One of the major contributions of our work is an extension of this semantic framework for secure effects. So we should understand what the original framework looks like first. The framework discusses two languages like before. One is pure, and we understand its semantics. And the other one is a language of the type and effect system. So I'm going to write the effect on top with this little epsilon here. The pure language has sequential composition, so we can feed the output of one program as the input of another. And in the effectful world, we can do the same thing, but now we need some way of combining these two effects together. And we do that via the effector relation. The final key rule lets us transform an effectful program into a pure program while changing the output type of the program. We call this capturing the effect. The rest of the rules in the original framework tell us how sequential composition and capturing play with each other. And that's the original framework. That's by actually my PhD advisor, Ross Tate. It doesn't discuss security at all, so we need to extend this to be able to talk about secure effects. In order to do that, we need an axiomatization of the protection relation and how it relates to effects and capturing. So since we're using a productor to capture the effects on the output types, we need to know what labels the transformed types protect. To be protected by a transform type, a label needs to be able to influence not just the original type, but also the label of the effect. We also need a notion of indistinguishability for both the pure and the effectful language. Finally, we need to know that capturing the effects of effectful programs doesn't cause things to become equivalent that weren't before. With these two simple additions, we have a framework for secure effects. Technically, there are some other rules stating how these things interact with sequential composition. In order to validate this framework, we proved an important theorem. Assuming that the pure language is secure, the type and effect system is also secure. In order to do that, though, we have to develop an abstract version of non-interference. Because our framework doesn't have values, we just have programs. But programs produce values. So instead of two secret inputs, we have two secret programs, P and Q, and we're going to sequentially compose them both with the same program R. R is non-interfering if it produces the same public outputs no matter what P and Q we pick. So we want to use this abstract version of non-interference to show that all programs in languages that fit our framework are non-interfering. Well, if all the pure programs are non-interfering, then capturing the effects in an effectful program gives us a non-interfering program. But we need to know that we haven't accidentally made things equivalent by doing the capturing, which is exactly what the rule from before gives us. So this is a rather quick sketch of the proof, but it actually goes through pretty much all of the details we'd want to go through here. And the beautiful thing is it's really just this very simple abstract proof that you can do in this framework. Sorry, I think I heard somebody speak up a little bit there. Did I hear correctly? Okay, I'm going to assume not and move on. Okay, so this is a nice framework for reasoning about secure effects, but we still have to connect it to PC systems. Usually when we prove non-interference, we use the PC to prove what's called a confinement limit. If a program type checks with a high security PC, all of its effects must also be high security. So if the PC doesn't allow writes, the program doesn't write to the state, and similarly for exceptions. It turns out that we don't actually need all of that. We don't need to know that the effect is high security. We just need to know that there is some effect that we can type check in a secure type and effect system, since both of these actually preserve non-interference. They actually enforce security. So if we know this, and we know that the pure language is non-interfering, and we're in the framework that we've suggested so far, we get as a theorem that the PC system actually enforces non-interference. This is the theorem that we call non-interference half-off, gave its name to our paper, because it says that you get to just reason about non-interference for the pure part of your language, and then you reason about the effects abstractly. And this lets you kind of separate concerns. You don't have to get everything tangled up, which adds a lot of complication to traditional non-interference proofs. Oh, I see somebody said something in the chat. Yeah, okay, so somebody asked that I said that partiality is good for security. I'm going to actually come back to this at the question and answer session, if that's okay, since we've already moved on from there a bit. I'm sorry if I missed this earlier. Yeah, I will come back to this and enter this at the question and answer session. Okay, I'm going to go ahead and look at one more example of an effect other than state and exceptions, just to make sure that we haven't overgeneralized or undergeneralized, in fact. And that example is non-termination. This requires, in order to use non-termination in our framework, we have to have a type that represents kind of a non-terminating version of tau. So in this pure language that I'm working with now, everything is terminating unless it has a bottom type. And then fixed points, fixed points are only allowed on bottom types. This is actually used in DCC, which is the first coarse-grained information flow system. So we're able to use DCC almost exactly as it is in order to do a lot of this work, which is really nice. We can develop a language with unrestricted fixed points as well, but now we use a type and effect system to track whether a program is pure or possibly non-terminating. And here we say that it doesn't really matter what effect E has, excuse me. If you take a fixed point of E, it's possibly non-terminating. We can also define a PC system for that, where the PC has to flow to the possibility of non-termination. So anybody who can see that this program doesn't terminate has to be able to see the PC. And then the standard monadic translation gives us that possibly non-terminating program is a program with bottom type. So we're using this pointed type or bottom type construction as a monad here. Translating this using maybe translating the unlabeled rule with this gives us something like this. But in DCC, this actually fails. This is never possible because no labels are allowed to influence the non-termination monad in DCC, because they didn't want termination label, the creators of DCC didn't want termination behavior to leak secrets. They made sure that only unlabeled data could influence termination. In order to fix this, we actually use the label of an effect, just like above. So we actually add this rule to the system that says that if L flows to the label of possible non-termination, and L also protects tau2, then L protects tau2 bottom. And with that additional rule, we can do this translation and apply non-interference half off to prove non-interference. But this is actually a very special version of non-interference, because if this LPNT label is public, secrets actually are not allowed to influence termination behavior. And for those of you that know what that means, this is termination sensitive non-interference. So this is a very well-known and desirable strong property, but one that's often very hard to enforce and reason about. Like a lot of more denotational semantics for non-interference, we very naturally get termination sensitive non-interference when reasoning about non-termination as an effect. So I'm almost done, but I just want to quickly sum up. So we showed that program counter labels enforce secure effects, and secure effects are given semantics as productors defined on an IF language, where productors are a generalization of graded monads. We gave a semantic framework that gave PC labels this semantics, this productor semantics. And this combines two uses of grading, one for effects and one for labels. We showed that the framework is useful for common effects, including state, exceptions, and non-termination, and developed the non-interference half-off theorem, and applied it to non-termination to get termination sensitivity. In the paper, we do a little bit more. We show that not every PC system in our framework bounds effects by the PC. And we actually look at a Galois affection between labels and effects. We extend this function from effects to labels and take it backwards. And we actually find that using a Galois connection plus a few extra things forces PCs to act as a bound on effects. So this validates the common conventional wisdom. So with that, I'm happy to wrap up. I think I'm just a little bit over my originally scheduled time, but I'm happy to take any questions.
Great, let's thank our speaker. Yeah, so we started a little bit late, so we got time for some questions. I guess we can pick up the one from Marco in the chat about is partiality is good for security. Can you talk a little bit more about that?
Yeah. So the point is that when you're sorry, 1 second. There we go. The point is when you're working with security, you have these points where you want to say that this effect isn't allowed to follow this other effect, because then so the example I gave in the talk, which I went by kind of quickly, I know, was throwing an exception being followed by writing to the state. So the idea here is that if somebody can see writes to the state, but not see that you threw an exception, but you throw an exception, this person sees that you never wrote to the state and goes, aha, now I know that they threw an exception, and that can leak information. So by allowing our this partial semantics of effects and saying there is no semantics to programs that compose an exception with state in that order, we're able to actually represent that. So I hope that makes a little bit more sense. Marco, if you, cool.
Okay, anyone else want to jump in with a question?
So, Andrew, can you hear me?
I can barely hear you. I think that's Vineet talking, but I'm not sure.
Yeah. So I can be slightly more louder if that happens. So I was wondering this productors framework that you explained. So can this also be...
Vineet, I think you might need to just move up to the computer at the front.
Okay.
Yeah, that would really help. I'm starting to understand you.
Yeah. Okay, so what I'm saying is, so this productive framework that you explained, can this also be seen as a generalization of like maybe, you know, index monads like SLIO or well, CG, the monad that myself and Deepak have in 2018 CSF. So that's not really an index monad, but have you thought about productors as a generalization of those monads as well?
So I know they're also a generalization of index monads, because graded monads are a generalization of index monads, and their generalization of graded monads. Obviously very related. You're just moving from function space to relation space. I don't know enough about, I haven't looked specifically at that paper of yours and Deepak with that in mind. So I haven't looked at the details of that particular construction. I suspect that it is, though.
Okay.
So we could have easily done all of this with two productors. We end up using one productor and one index monad, because that just is the structure that's traditional to information flow labels.
Yeah. I see. Okay. And also, have you thought about generalizing this framework to account for declassification?
A little bit. I'd really be interested in thinking about how to do that, but we haven't gotten any. We haven't done any concrete work on that yet.
Yeah. Okay.
Great. Okay, let's thank our speaker again. Excellent. And if the next speaker is who's Dylan, I think he's there in person, so he can maybe share screen and move to the front.
That's very good. I share my screen and then.
Yeah.
We use the same laptop.
That should work. Yeah. Okay, we can see that. And if you stand by Mike's laptop at the front, then there's a bit of a weird black bar on your share screen. I think is that the Zoom masking itself out?
That's the best I can do.
Great, thanks very much. Okay, so the next speaker is Dylan McDermott, who comes to us from Reykjavik University. Thanks, Dylan, for coming in person. He's going to be talking about canonical gradings of monads.
Thanks, Dominic, and also thanks to the organizers for setting this up. So I'm going to start with an example, just to give you some idea of what I'm going to talk about. So the idea is that we can start with, say, a writer monad. So suppose that we have some set C of characters, and then this over C are essentially, strings that you might want to print to a screen, for example. Then we have a writer monad, which we can use to model computations that print. So a computation that returns elements of X is a pair of a list over C and an element of X. And then this comes with some unit functions, which is say, well, the trivial computation that returns X just prints nothing and returns X. And then the multiplication says, given two strings, we can just concatenate them. I'm going to talk about monads in terms of multiplication rather than anything like fancy extension, just because it's kind of simpler for what I'm going to talk about. Okay, so now we can grade this monad in a bunch of different ways. So we could say something like, we care about the lengths of the string that we're printing, and then grade by natural numbers. And then we say a computation of grade E is a pair of a string of a length at most E, and the result of the computation. And then we get some graded monad graded by natural numbers. So in particular, the unit just kind of restricts, and we get something of grade 0. the multiplication restricts, and we get some good grade E1 plus E2. And we can do something, we can do some other grading as well. So we can grade by subsets of the characters. So we say, if E is now a subset of C, then we can talk about computations that only use characters from the subset E. So a computation is a pair of a list over E and an element of X. And then we get some other graded monads, kind of just graded by subsets of C. And the point I want to make here is that in both of these cases, all we're really doing is saying, I have a bunch of grades, and to every grade, I'm just saying, here is a subset of the computations. So here is a subset of the computations over the writer monad. And I'm just going to use these subsets to build a graded monad. And somehow a lot of graded monads kind of have this form. There is some ordinary ungraded monad lying around, and we just kind of take subsets of it to construct a graded monad. I'll give one more instance of this. So we can also grade by subsets of the strings. So now sigma is a subset of lists over C. And then we get some graded monad that grades the writer monad again, and it just uses, strings from the set sigma. The reason that I mentioned this one is it's kind of special in some way. So it turns out that we can kind of it kind of extracts the first two gradings that I showed from this third one. So what I mean is, in the case of the first one, we're grading by natural numbers. And for every natural numbers, we get a subset of the strings, right? The strings that have length at most E. And then, so this is now a grade in the sense of a grade for the third example that I showed, a grade for this canonical one. So then we get some set of computations. So the point is now that just by composing this function f with like this canonical graded monad, this third one, we actually get the first one. And there's something similar for the second one as well. So every subset of the characters gives us a subset of the strings. And then just by composing with some function f from grades to grades, then we just get then we get this second grading that I showed. And the interesting thing is that somehow every grading, for some definition of grading, every grading of the writer monad will factor through this canonical one in some sense. This is what I mean by when I say this is canonical. Right? In some sense, these subsets of strings are the best possible collections of grades. Is the best possible collection of grades. So what I'm going to talk about is a kind of what's going on in general. So the point is that for every monad on set, I'm going to say, there is a notion of grading of this monad, essentially where we take subsets of the computations. And T will always have a canonical grading in some sense. So in particular, every grading of the monad T just arises by kind of considering the canonical grading and then defining some function that sends grades to these canonical grades. There is also a more general version of this story. So I've been talking about subsets. We can replace the subsets with kind of some more general notion of like subfunctor, which we can just assume as some data. So I'm going to assume some m as some data, and then we get some notion of m grading, and we can get canonical m gradings in some cases, and then we get a similar story for these m gradings. And in fact, one instance of this is we can kind of grade monads by shapes of computations, kind of as an instance of this. And I'll talk about this towards the end. But firstly, I want to go back to this version where we just have subsets, and we don't talk about there's no m here. So I'll say what a grading is properly. So a grading of a monad T is first a collection of grades, which I'm going to say form a partially ordered monoid. In fact, more generally, I sort of don't in general want to say partially ordered monoid. More generally, I might want to say monoidal category or something like this. But I'm just going to stick to partially ordered monoids for now. And then the grading also comes with subsets of the computations. So for every E and every X, we have a subset of T of X. And these are sort of the computations of grade E. And these satisfy a bunch of conditions. So they're required to sort of respect the inequalities in grades. So whenever E is less than E prime, we get bigger subsets. So G of E is sort of smaller than the G of E prime. And also we require G to be closed under all of the monad structure. So in particular, the unit of the monad will give us some unit of a graded monad, where the grade is now I. And the multiplication of the monad will give us some multiplication for the graded monad, using this using this O dot, this multiplication of grades. And these are just defined by literally restricting the units and the multiplication of the original monad. So I haven't required this explicitly, but it turns out, just as a kind of slightly obvious fact, that G will form a graded monad. G is a monad graded by these chosen grades. Okay. So these are the examples from the beginning. We can grade by natural numbers, or sets of characters, or sets of strings. All of these form gradings in this sense. Okay, now one thing I want to mention before I come back to canonical gradings. In some senses, kind of an obvious choice for a lot of the data. So if we choose some set of grades, and also choose a subfunctor of the monad for every grade. So here I just mean GEX is a subset of T of X for every E and every X. And also this G is sort of closed under what T does on functions, so under the kind of functorial structure of T. We can kind of extract the rest of the ordered monoid of grades in kind of a reasonably sort of obvious way. So the point is, we need to have an inequality on grades, and for this we can just say, well, the inequality literally just says E is less than E prime whenever G of E is smaller than G of E prime. This, in some sense, is kind of the obvious choice for the inequality once we fix G of E. And then in some cases, we can also get a unit and a multiplication just by essentially saying these are the smallest grades such that the unit and the multiplication of the monad will restrict to this graded monad. This doesn't happen in general. We need in particular to have smallest grades. But in a lot of cases, this will happen. And in fact, for all of the gradings that I will show, this is really how we define them, right? We just take, in particular, we just take like the unit and multiplication of grades are just the smallest grades that work. Okay. So now I want to talk about canonical gradings. I will talk about canonical gradings of functors first. So just forgetting about eta and mu for a while. A grading of a functor is just like a grading of a monad. We just kind of forget about some of the structure. And it turns out every functor will have a canonical grading. So we can take as grades literally the subfunctors of T. So these collections G of E. These are now the grades. And now to get a grading, we need to say, well, for every subfunctor, I need to construct some subfunctor of the monad. This will be my G of E. And this is literally just the identity. So the point is, we come up with this collection of grades, which is just subfunctors, and we say, well, every subfunctor, every grade, this is what we just use as a subfunctor. And then we do get a grading in this sense, up to some like modulo some size issues, which I won't mention. And this is canonical in some sense. It's canonical in the sense that for every other grading G, there is in fact a unique map of grades from E to the subfunctors of T, such that G kind of arises by composing with F. So another way to look at this is just to give a grading of T is literally the same thing as to give a monotone function between grades. A monotone function that gives you canonical grades, these subfunctors. This is kind of trivial in a sense, because I've said a grading consists of a bunch of subfunctors, and now my grades are subfunctors. So actually, this universal property is not really doing much. These functions F are literally just, these functions F just assign subfunctors, and these are literally what gradings do. So this is not doing much. It's slightly more interesting with gradings of monads. So now we want to say that these subfunctors will give some canonical grading of the monad T, if T is now monad. It works in much the same way, except now we have to define a unit grade and a multiplication of grades. This is actually not so difficult. We just use this trick of taking the smallest grades that will work. So in this case, we just say the unit grade is just the image of eta. So the subfunctor that just consists of the computations that arise by doing eta. And then for the multiplication of grades, we just say we'll take the image of mu. So the subfunctor of computations that just arise by doing mu of some computations. And then we get a universal property, which is much the same as the previous one. The only difference now is that these functions f have to respect the kind of the monoidal structure of the grades in some way. And this just means we have these inequalities I have on the bottom left of the slides. Okay, so now every monad has a canonical grading. Every monad on set has a canonical grading where we take the grades to be the subfunctors of T. Okay, now I want to move to this. No, now I'll give you some examples first. So the point is now I've said the grades are subfunctors, but it turns out in some cases subfunctors are sort of reasonably nice things. So if we take the writer monad, we want to ask what the subfunctors of the writer monad are. It turns out these are literally the same as just subsets of lists over C, so subsets of the strings. So now the canonical grading of the writer monad is given by subsets of lists over C. The grades are subsets of the strings. So in fact, the canonical grading is the thing that I showed a few slides ago. It's this grading where we take the subset sigma of lists over C. And now it follows from this universal property that we get this situation where these other gradings of the writer monad just arise by considering functions f that just map your grades to these canonical grades, and then composing with this canonical graded monad.
Is there any discussion about this?
It will work for any monoid. Did you say monoid or? Yeah. Yeah, there's nothing special about this. It will work for any monoid. So the grades are just subsets of the monoid. Yeah. Okay, I'll give you one more example. We can take the reader monad over some set V of states. So now a computation is just a function that takes an initial state from V and returns a result. And we can ask what the subfunctors of this thing are. It turns out they're a bit more complicated than the last one. They are these upwards closed sets sigma of equivalence relations on V. So the point is, if we're given some sigma is now a bunch of equivalence relations. And now we get some subfunctor S of the reader monad. And this consists of those computations that kind of respect one of the relations inside sigma. So for which there exists some R inside sigma, such that this function f respects R. So for example, if sigma just consisted of the total relation, this would say essentially f cannot look at the initial state. So f would just have to be a constant function. Right? Because it would say for every v and v prime, f of v would have to be equal to f of v prime. So this means essentially the computation cannot look at the initial state. So the subfunctors are now equivalently these upwards closed sets of equivalence relations. So it turns out we get a canonical grading of the reader monad by these sets. And then we can construct some other gradings of the reader monad just by using this canonical one. So for example, we can grade now by single equivalence relations instead of sets of equivalence relations. Where here we just say, well, given a single equivalence relation, I can construct a set of equivalence relations. It's just those equivalence relations which are bigger than this one I started with. And now by composing with this canonical grading, we get some new graded monad read prime. And what this does is it just says a computation of grade R is just a function from V to X that respects R. So if R says it cannot distinguish between these two initial states, then the computation is not allowed to distinguish between them. Okay, Now, I'll briefly mention this more general story where we replace subsets with kind of something else. So now I want to say, I'm going to assume some class of natural transformations, some class M of natural transformations between functors from set to set. So for example, we could take component-wise injective natural transformations, and this will actually give us the examples I had on the previous slides. So a component-wise injective natural transformation essentially just picks a bunch of subsets of a functor. Like up to isomorphism are literally just component-wise inclusions. So we're just picking out subsets. So by taking this, then we'll get the previous example. But more generally, we can get kind of other notions of M subfunctor. So now we can talk about, say, what a grading of a functor is again, and it's kind of much the same as before. I'm not saying a category E for some kind of technical reasons, but we have some collection of grades E. We assign to every grade E some functor, which actually should form an M subfunctor of T, where M subfunctor is just kind of the parameter that I've assumed. And now we get this canonical grading story yet again. So we can just say the canonical grades are the subfunctors of T. And for every one of these subfunctors, we just kind of map it to itself. And now we get some grading of T. And now we again get some universal property that says these grades are canonical. Again, for some annoying technical reasons, these are now isomorphisms instead of, like, there is now, I'm now saying this triangle commutes up to isomorphism instead of equality. I kind of have to do this with some technical reasons, but I won't say this in any detail. Now we can also do something with monads. So we can again define some notion of M grading of a monad. Again, it's just much the same as the previous notion of grading of a monad. The difference from the previous slide is now we have some notion of multiplication on grades. And the rest of the structure needs to kind of respect this notion of multiplication in some sense. Then under some conditions, these M subfunctors will be the canonical grades again, and we'll get some canonical grade monad. Again, with some universal property, kind of like the one that I showed previously. This does not always hold. We need some extra stuff. So the reason this doesn't always hold is that we need to kind of repeat this construction where we say take images of eta and mu. We can't do this in general, just with some general M, but we can assume some extra things about M that will allow us to do these constructions. So I won't explain this in detail, but the point is that we assume that M forms a factorization system. So now we have some other class E, which will be, for example, surjective and component-wise surjective natural transformations. And then we say, well, every natural transformation has to factor into something from E followed by something from M. And now this image construction is just factorizing natural transformations in this way that I have here. And then under some extra conditions about closure of some things under E and closure of E under some things, then it says that we actually get these canonical gradings of monads. I should say why I want to generalize in this way. So one reason is it's now sort of actually quite easy to replace functors from set to set with some other category. And one reason we might want to do this is because we might want to say, I want to do strong functors instead of ordinary functors. Because usually to model some effects, we want like a graded strong functor instead of a graded strong monad instead of just a graded monad. And now if we just replace these functors with strong functors, we can kind of do these same constructions, and now we can do the same thing for strong monads as well. But a second reason is there are actually some other sensible choices of M, even if we just say functors from set to set. So let me give you one example of this. So if I have a monad T, we can talk about shapes. So we have some set T of one. One here is just a one element set. And these are now the shapes of the monad, shapes of computations. And every computation T inside T of X will have some shape inside T of one. So for example, the shapes of a list monad are equivalently natural numbers. And these just essentially denote the length of the list. So the shape of a computation T is just the length of T as a list. And in a lot of cases, we want to grade by shapes of computations rather than by something more complicated. And it turns out there is a story about kind of canonical gradings by sets of shapes. So I can say that I can define a notion of Cartesian subfunctor. So these are again just the same as subfunctors. So we just pick out subsets of T. But we're satisfying some extra condition, which essentially says they're completely determined by looking at just the shapes. So whether T is inside S of X is just determined by whether the shape of T is inside S of 1. Now, equivalently, these things are literally just subsets of T of 1. So they're just sets of shapes. And we can use these to kind of, as an instance of this previous story where we have some general M. So up to isomorphism, these Cartesian subfunctors do provide some class M of natural transformations, for which we can do all of this construction where in particular, we can factorize natural transformations. So now by the things I said previously, we get some canonical grading. We get some canonical grading of a monad T. I should say there are actually some side conditions on T, which don't hold for every monad. It actually works a bit more generally than this, but there are some side conditions which hold in particular for list. So in the list case, it turns out that Cartesian subfunctors, well, they're just subsets of shapes, and shapes are natural numbers, so they're just subsets of natural numbers. And these are sort of allowable lengths of lists. So a computation of grade sigma is just a list whose length is an element of sigma. And now we can extract an inequality, a unit, and multiplication just from this previous stuff. So in particular, the unit just says the length has to be 0. The multiplication says the length has to be a sum of the length from sigma 1 and the length from sigma 2. And now we get some canonical grading of the list monad. So we get a graded monad list prime graded by sets of shapes. And this satisfies some universal property kind of as an instance of the things that I showed previously. Okay. Now, one thing that I'll just briefly mention before the end, there is also a story for algebraic operations for monads. So usually to model effects, we don't just want a monad, we want algebraic operations as well, which are the things that will actually cause effects. So we might have something for printing strings or non-deterministic choice or something like this. So now we can ask, if we have these canonical grades, can we canonically grade algebraic operations in some sense? And it turns out we can. So in particular, if we have a bunch of canonical grades, S1 to Sn, these are sort of the inputs to the algebraic operation, the grades of the inputs. It turns out there is always some canonical grade for the output S prime. And now we get some notion of algebraic operation for this canonical graded monad. So I won't say in detail what this notion of algebraic operation is or why we have this kind of multiplication by blank or anything like this. But I just want to say that there is also some story about algebraic operations, and algebraic operations kind of fit quite nicely into this story. Okay, but the main point is, I think there is a nice technical result here, which is that, for every monad we get some notion of canonical grading, and in a sense, this canonical grading kind of includes all of, the usual gradings that we might want to give for this monad. So there is a paper about this, or there will be a paper about this. It will be at ACT next month. It's not currently available yet. But yeah, you can read the paper if you want to know more. Thanks.
Excellent. Thank you, Dylan. Let's take some questions.
Yeah, I guess I might do this, but So your reader example reminded me of this work from years ago on grading state monads for read light effects by Edwin and Unifying kind of idea that it's just this kind of relational formulation somehow.
Do they grade by relations? Or?
Yeah, no. There's a relational interpretation.
Yeah, there's an interpretation with relations. Which,
Could you repeat the question, please, Dylan?
Okay. Yeah, the question is about this paper of Nick Benton and some other people, I forget who. I think the paper is Reading, Writing, and Relations, right? Yeah, where they have this kind of, they grade the state monad and they kind of have some relational interpretation of this graded state monad. This, I don't know if there's any connection really.
Looking at this again. Well, I just reminded me of like they interpret read-only things so that you must preserve. So,
yes.
Your general framework you can have monads monads on category sets and binary.
We could have monads in this category, and then I'm not sure what would happen. Yeah, I haven't looked at this, so I'm not sure what would happen. One thing I can say is we can also do a similar thing for the state monad, a similar thing to this. The difference there is that these, instead of having equivalence relations R, we now have pairs of an equivalence relation and a function from V to V. So this essentially says a computation needs to respect an equivalence relation R, but also update the state according to this function from V to V. And I guess this looks a bit further from what they are doing in this paper.
Yeah, that sounds a bit like where you kind of you restrict what like the state update can do. Like you must really follow these transitions.
Yes. Maybe there is some connection. I don't really know.
Is this sort of, can you interpret this as a security thing? Like sort of saying there's some secret data and saying how much.
Can you repeat the question, Dylan?
The question is, can we interpret this as some security thing? Because, so we have relations which impose some conditions about, you know, which V's we can look at, right? Yeah. Or which V's we can distinguish between. I would somehow hope so, right?
So V is like abstract secret data.
Yeah. But I would say if V had an element of V has some public part and some private part, we can say the relation says you can only distinguish between the public parts and not the private parts. I guess it can be interpreted in this way. I haven't thought too much about how to interpret this. So, I mean, this literally just popped out of some abstract nonsense. Yeah. And like this is just what it turned out to be. I haven't really thought about how to interpret this kind of in any computationally. And I guess this is a sensible interpretation.
It's sort of, I mean, there's these translations of B, C, C into system F, right? Essentially, there's a kind of reader style transmit where you abstract of the variable reader style. And because it's system F, then you can interpret that with different relations, different places, you get one experience.
This is not something I know about.
Still similar. Okay. So somehow BCC is sort of readable that you're reading from some. You quantify it,
yeah.
Some you're kind of restraining by a condition of abstract.
Okay.
All right. Well, I think we'll take the rest of the questions offline. So thank our speaker again. So we now have a coffee break until 11:10 UK time. So those in person can go down to the Gulbenkian, and Vineet will sort everyone out, get a coffee, and the rest of us can pick up our home beverages, and we'll see everyone back at 11:10. Okay, so thanks everyone. Welcome back. In this session, we've got a slight change in the schedule. So we've got James speaking first, as is in the schedule, and we're swapping Jonathan Brachthäuser's talk, which is supposed to be at 1:30. He's swapping with Jean-Philippe. So Jonathan will be at 11:40 and Jean-Philippe will be at 1:30. I will tweak the schedule online. Okay, so without further ado, our next talk, we've had a bunch of stuff about sort of graded monadic-like things, sort of stuff happening on the right. Now I think we're going to be hearing about things related more to on the left, to sort of graded necessity world, but actually going beyond that, beyond semirings, which is an intriguing title. James Wood from the University of Strathclyde and Huawei in Edinburgh. Take it away, James. Thanks.
Okay, yeah, thanks for the introduction. I'd hoped to give this in person, but alas, yeah, I've got a little bit of a sore throat, so I'm not going to speak very loud. You might want to adjust up your volume. I don't know how it sounds on your end. But yes, so this is some basically stuff I've been thinking about while writing my thesis, as I suppose a lot of things are these days. In my thesis, I use the general confusion of this talk as a bound on the things I'm going to study, but I think looking into the future, maybe we want to study more things beyond semirings for what usage restrictions. Let's start off. Why do we like semirings? Why do we use them in languages like Gradual and various other systems? So semirings have two parts, right? They have an addition structure and a zero and an addition, and then kind of on top they have the multiplication, which distributes over the addition. And those two parts, the addition is supposed to be some sort of accumulation of usages. So if we add up semiring elements, that corresponds to using something in one place and using it in another, and eventually we're going to use kind of both of them in a program. Multiplication is a bit more subtle. I've glossed it over to modality. This is, I suppose, often explained via what's it called, bounded linear logic, where we can say using things multiple times is a kind of Bang modality. And yeah, as I said, there are plenty of examples both of kind of general semiring systems like Gradual and some of the work I've done and some of the work various other people here have done, as well as a fairly long history of systems where people were interested in something specific, and it later turned out that they fit in this general framework of semirings. Things people have done on like non-interference, sensitivity in a quantitative sense, and probably a whole bunch that I'm forgetting right now. So why would we ever want to change? These are kind of sort of various reasons that you can take as a just to sort of see general doubt in your mind. I'm not going to solve all of these all at once, but these are reasons why we might deviate from the path. So my first point is that it's sometimes difficult to achieve a kind of parsimony. So sometimes we don't want the full power that semirings give us, but we've kind of fixed ourselves there by, you know, we kind of painted ourselves into a corner by having the semiring definition. So the example I give here is multiplicative additive linear logic, where there is no, there's no bang, correspondingly no modality. We kind of expect not to have a multiplication. But we find it kind of difficult to deal with just commutative mono, just the addition. Reasons I'll come on to later. So I said multiplication by 0 can act strangely. This is very much a can act strangely, not does act strangely. So this, you sometimes see if you get a box 0 or bang 0, whatever you want to call it. If you look at the bottom of your typing derivation and you look up and you see a box 0 introduction, it kind of reincarnates variables that we couldn't previously use. You know, 0 said we can't use it, but we got that via a multiplication by 0, and above we can use them in whatever way we want. This makes sense and is used to good effect in like quantitative type theory, where they care about erasure, but erased things can be used in types. But not all models we could want are like this, and sometimes it causes problems. And the last one is kind of more a usability thing, that maybe if you think about Idris's linearity checking, you want to kind of be in a part of the program and say, well, what usages of variables do I have available? And if your addition is kind of functional, then you're not told this in this whole. The usage is kind of I don't know, dissipate from it. So you won't know anything until you fill the whole program in, and then it checks against each binder and tells you the problems there. So yeah, I hope you're convinced that at least one of those is a problem, or could be a problem. So
I'm convinced that those are problems, but what does the last one have to do with semirings?
So this is a good question. I suppose it has to do with semirings in set, and I'm going to be talking about categories that are not set. But then we need something that's not semirings. So yeah, maybe this is badly timed. Thanks for the question, but
keep going and maybe it'll become clearer.
Yep. So I'm going to give like the most hand-wavy introduction to monoidal categories ever. I'm going to use monoidal categories to state some algebraic things that are maybe a bit like semirings. So what are monoidal categories? They're things that let you write string diagrams, which are more or less circuit diagrams. So you think of F and G as some components, you know, digital logic components, and you can plonk them together by connecting the wire of the right parity. Or if you have two components, they go next to each other. This understanding works, at least for now. And the rest of the conditions of monoidal categories say that they behave in a way that you would kind of expect. Yeah, these are some of the categories, the monoidal categories I'm going to think about today. So set is our basic one. We have sets as objects, functions as the boxes, the morphisms, and one, the unit, the one element set, and Cartesian products to give this idea of multiple wires. Then rel is one where the objects are sets again, but the morphisms are relations. So that says I kind of feed something in at both ends, and they have to relate. The kind of top and bottom have to relate to each other. And then there's commutative monoids, which have their own sort of tensor product. Loads of other algebraic structures have a similar kind of tensor product if they've got a commutative addition. And to deal with partiality, we've got sets and partial functions. And again, this is not the Cartesian product. This kind of lives somewhere between set and rel. But the cross is not the categorical product. It's the product from sets, and yeah, we'll see a bit about it later. So to do algebra in these things, we can use these string diagrams, and this is saying if we've got a zero generator and we compose it with a plus gate in the digital logic terminology, it should be the same as just a wire. So hopefully you can see how this corresponds to the equation above. Associativity, if we wire things up in this way, it's the same as wiring them up in the other way. And if we have symmetric monoidal category, we can cross the wires and say crossing the wires for this addition gate doesn't do anything. So what was I going to say there? Yeah, so we can state at least as far as commutative monoids in all the example categories I said before. So we know what a commutative monoid in rel is now. Well, okay, we're gonna have to churn through the definitions a bit, but we can find it out. There's an answer. What about semirings? So we kind of need a bit more. So somehow symmetric monoidal categories are even sort of too unstructural in the sense of substructural that maybe we're familiar with. And what we have to do is the interaction between the multiplication and the addition needs duplication and deletion. So I've given the annihilation rule, which needs deletion. So this side talks about some x coming in as the input there, but on the right or in the middle hand side, we don't have an x, so we somehow need to get rid of it with this mysterious circle, which nothing in monoidal categories provides us with. And to equate these two things of the same type. And the solution normally taken by, well, I at least know that the quantum computing people take this solution because they're the people I know, is that you take your original monoidal category, you turn the past 3 slides upside down, and they give you a co-commutative comonoid rather than a commutative monoid. So you turn all these diagrams upside down, and that makes sense as something in monoidal, symmetric monoidal categories, and you consider the category of co-commutative comonoids in that monoidal category, and that resulting category is Cartesian, so you get a duplication deletion, or you can kind of see from addition and 0 turned upside down, the addition is the duplication now, and the 0 kind of deletes stuff. So that's what this mysterious circle is going to be. So we don't normally think about comonoids much, and that's because in set they're all just a trivial one.
What's the
there's a
step?
question?
Can you hear me? Yeah.
Yeah.
What's the step that's going on whereby we start with a symmetric monoidal category and we turn it into a Cartesian category?
We have a new category where the objects are co-commutative comonoids
In our symmetric monoidal category.
in the original, yeah.
Okay. Okay. I'll take that on trust.
Yeah. My intuition is that you have a duplication and deletion from the operations of the comonoid.
Okay.
I'm not going to go through the full details because
Yeah.
actually takes a bit of effort. Right, and so as I just said, I think there's no interesting co-commutative comonoids in set. They're all just the obvious fan out and get rid of things. And this is a reasonably well-known result by the kind of people who know it. But for other categories, we can kind of have a look, see whether they might exist. So for rel, they definitely exist. You can just take commutative monoid, turn it upside down. Rel is I think it works because rel is a dagger category. You can just turn everything upside down and it still works. There's no direction in a sense. It also works for these algebraic ones for similar reasons. But sets of partial functions, let's have a look at that. So here I've got written the unit laws for comonoid. So we should have these operations that compose in this way and act like the identity. And if we start in the middle with the identity, it says we should be able to feed in an x and always get an x out. The identity, this should be the same to the left as duplicating according to the comonoid, deleting one half and taking the right one. So this left-hand equation says that it must be the case that when we feed in an x, we get two things out, one of which deletes, and the other of which is actually x, because it's equal to the identity. And also this must be defined, because identity is defined. So this z really will have to be an x to make this equation hold, and similarly this y has to be an x to make this equation on the right hold. So that must mean that when we pass x into this co-multiplication, the copying, because it's functional, it's deterministic, we must have x coming out of this branch and x coming out of the other branch, and also because this is always defined, then any x that we put in here and that comes out here will be deleted, and this will be defined. It means that all the comonoids in sets of partial functions are the boring one that really like just copies the thing, deletes everything, everything's total. So that in turn means that any semirings we take in these comonoids, because all the operations are homomorphisms over the comonoidy stuff, it means that they too have to be total and deterministic. So total because of the co-unit, deterministic because of the co-multiplication. So all the semirings and sets of partial functions are just the semirings in set. We haven't gained anything. So that's not so great. So we better do something about it. If we want something that's not just semirings and sets, let's have a look at what else we might want to try. So I'm going to look at two of these. We're going to find a different category of sets and partial functions, the first one, and in the second one we're going to weaken multiplication a bit, because that seems like something that comes up a bit. So first observation is that sets and partial functions is kind of like the category of sets and strict partial functions, if we're putting a programming languagey hat on. And the way I choose to observe this is by going via this notion of generalized elements. So if we have a distinguished element I, or this could be the monoidal unit I, we can consider the set of morphisms into any object A. And these kind of look like the elements of A. So in set, this is the one element set, and sets from the one element to a set just look like a set, the set itself. And if we take this view of sets and partial functions, then we've always got this bottom element in any set of generalized elements that's undefined on the point. So even the empty set in sets of partial functions has this generalized element bottom. And when we look at composition in sets and partial functions, it says do the first thing. If it's defined, do the second thing. Otherwise, just be undefined. So if we have this bottom element as the first morphism, then whatever we compose on the end of that is going to result in something undefined because the bottom was undefined. So we can't have anything non-strict. So what if we did have something non-strict? This was something Bob brought up to me like last week or something. So that's where credit goes. I understand it as kind of similar to some constructions we do in domain theory, where bottom really is at the bottom of some ordering, and we say that things are monotone, so that if you're defined on real elements, sorry, if you're undefined on any real elements, you've also got to be undefined on bottom. Otherwise, otherwise you kind of got more information turning into less information. But you don't have to preserve bottom. The preserving bottom is strictness. That's the definition. So we can state the algebraic laws of semirings in the way we usually would, and we are now allowed to do this kind of 0 times bottom is 0. We don't have to preserve bottom. And 0, 1, omega, this sort of traditional semiring works and works with the order we normally think of omega being at bottom and the other 2 points being above it. how do we actually use this in a programming language is maybe, I don't know, but less clear to me. Maybe it's more clear to other people. So I think typing derivations should somehow avoid bottom. It's if you have bottom in there, then weird things can happen, like we see in QTT. You can start with a omega somewhere and not use it unless you're going to use it twice, in which case 1 + 1 is omega. So you kind of get to add them up and use the omega. So I think you need to avoid that if you want something sensibly behaved. And then this information ordering, I don't think it really needs to be the same as subgrading, subusaging. I'm not sure. I don't think it makes sense to coerce over it because we're not supposed to be talking about bottom. But yeah, so yeah, that's one idea. And the other idea, before I run out of time, is I don't know, I call it commutative monoid with actions and with a point as well, I suppose. So let's look at just commutative monoids, the addition part, and we're going to weaken the multiplication. So so we want the multiplication would normally be a homomorphism over the commutative, the addition E part. And we're just going to weaken that to saying we've got a set of actions that preserves the zero in addition. So this looks a bit like distributivity, but the actions are kind of living outside, so we don't have to care about duplication and deletion of them. So yeah, we've got these. We've got commutative monoid for addition, and then some actions. And here's an example to make it a little bit more concrete. We start in rel, sets and relations, and we want to do some sort of 0, 1 omega that avoids 1 + 1 is omega and stuff like this. But so some kind of partiality. And we say that it's got so in relations how it works is that the generalized elements are subsets, relating the unit type to a set is the same as a predicate on that set. So this predicate is true on 0 and omega and false on 1. And we define all the clauses of addition that we like. I think is where I normally put this. So things can add to 1 by exactly 1 the size being 1, and omega kind of lives in its own world of only interacting with omega. And this, I checked this last night because I was kind of disbelieving that it actually worked, but it does work. So omega kind of is the element that acts as a unit for omega, and 0 acts as the unit for 0 and 1. And then because we've got a 1, I suppose we're always going to have a 1, then the actions also kind of look like a subset of the original set, because we can always apply the action to 1. That kind of looks like the internalization of the action. And you can see this as multiplying, but only by a subset of the elements, by this subset of the elements. So we don't have to multiply by 0. This is called the big win here. So we've got an identity action, and then omega is the interesting one that does the modality of saying basically it turns 1 into omega. Oh no, sorry, it undefined on 1. It just turns, it kind of states that everything's 0 or omega. Yeah. So let's wrap up. Maybe I'm running a bit over. Sorry about that. So I suppose the takeaway points are sometimes we can't find the right semi-ring. So maybe we need to maybe we need some more ideas. Something beyond semi-rings. And there's a whole plethora of things we could do to weaken the definition of semi-ring, which are worth exploring. I don't know, and maybe it's not even up to me to decide. Someone else should have a look at it while I've got a new job. So thanks for listening.
Great, thanks, James. So let's just do one quick question. I think Flavian wanted to ask something. He pinged a message.
Hi, can you hear me?
Yep.
Well, not very a question, as a kind of comment. Some years ago, when I was working in semi-ring and on this kind of stuff, it occurred to me that we can weaken the notion of semi-ring in this graded exponentials by using just right semi-ring, or let's say lax left semi-ring, which in this we can, if the multiplication is not commutative, you can say that the left absorptions on the right distributivity can be weakened or even throw away. Will it be useful for you? I mean, you do this sort of trick, you get rid of the issue with the bottom, because you can have situations when you multiply by bottom, gives you a bottom is nice, but you can multiply by bottom, and this is something different. And that sounds reasonable for you?
Yeah, so I suppose my first thought, probably not thought about it, is it looks a bit like this idea of having actions, right?
Yeah, I think
this looks like a kind of multiplication, but only on the left.
Yeah, exactly. Yeah, it's kind of this kind of thing. But in the example I had, it seems that I also have some lax right absorption, or lax left distributivity, which means there is also some in the example. I mean, you can have this kind of structure if you look at so if you take any monoid and you look at the power set of those monoid, then you can have this kind of structure. This was described in the article I had on the modalizations of exponential semi-ring in also of exponential graded exponentials or BLL exponentials in REL with some weird exponentials. So yeah, I mean, I think this kind of stuff make a lot of sense, and we have to understand them. And I'd like to see your work in the. Do you have a paper on this?
No, unfortunately not. I've also got no idea what.
Okay.
So what Flavian is saying, James, it sounds a little bit like what you had in your TLLA paper, where you generalized to a left skew. I think it was lax, like skew or lax. I think it's the same thing.
Yeah. It's a
skew semi-ring, which kind of.
It's not too skewed, but it's lax, right lax semi-ring. I mean, we can. There is one point we can relax it. And but in the article I didn't call it like this, because I just say that, well, this thing exists, but we don't use it. It would be a bit too complex to use it. But you're right, we have to understand what's going on there. And if you want to discuss this one day, I would be very happy to.
Yeah, I was going to say I'd like to discuss this further. Probably not in this question session, for Dominic's sake. But yeah, I'll take a look at that. Thanks.
Great. Okay, let's thank the speaker again. Brilliant. Okay, so we're sort of about 5 minutes behind, but I think you're right. So we permuted two things in the schedule. So our next speaker is Jonathan. He's
Yes.
sharing. Brilliant. Excellent.
Hi.
Okay.
Can you hear me quite well?
Yes, that sounds great.
Okay.
So Jonathan comes to us from the University of Tübingen, and he's going to talk about effects, capabilities, and boxes from scope-based reasoning to type-based reasoning and back.
Thanks, Dominic, and thanks for the kind invitation to talk here today. So with this talk, we will be moving a bit into the direction of type systems. One of my currently favorite topics, which is type system ergonomics, like trying to develop type systems that that are easy to use and that lead to nice types, right, for the users. So just to give you a brief context of what I will be talking about today, in my chair at the University of Tübingen, we are working on a programming language. It's called Effect with a K. It's a new programming language, and just see a message on the chat. Okay, no, that's not good. It's a new programming language, and we use it as a vehicle for our research in different lines. So one is lightweight alternatives to traditional effect systems. I'll be talking about that today. But we also work on ahead of time compilation, efficient compilation. My collaborator Philip, he's just at PLDI and talking about this this evening. And recently we also started working on just-in-time compilation for control effects, for effects and handlers. Just to give you a brief overview of what we're working on. But today I'll be talking about one particular result. It's a paper in the upcoming UPSLA edition. It's called Effect Capabilities and Boxes, like the talk. And it's already publicly available. I also want to mention my co-authors on this paper, which are Philip Schuster, Edward Lee, and Alex Broch-Gruszewski. And if you're curious, there is an online artifact where you can play around with the type system, type check your own programs, and also there's a full coq mechanization available. I'll put up the link later again. Okay, so the talk is structured similarly to the title of the paper. And at first, I want to talk a little bit about traditional effects and traditional effect systems and algebraic effects, and what we are working on in contrast, which is what we call capability-based effect systems, and the difference there. Then I'll zoom in on capabilities and in particular talk about effect safety and how to establish effect safety in a system where we talk about individual capabilities. And finally, and this will then luckily be the graded part, we talk about boxing and representing sets of capabilities in types and grading in the particular sense. Yes. So let's start with a brief overview and to see what I mean when I talk about capabilities. So here's a quick quiz. It's supposedly a language with effects and handlers. You can think of effect handlers as exception handlers. And the quiz now is we have this function or this effect operation called raise here. And the question is, where will raise be handled? Any ideas?
In the with?
So hopefully, yes, that would be nice. Yes, good point. So if you're familiar with, let's say, exceptions in JavaScript, you would guess that it could be handled by the try catch or the try with below, but also a higher order function itself might instantiate some effect handlers or some exception handlers, right? So it also might handle the raise effect. And even if we assume the signature, which is now below here, Then the signature says, okay, for all effects E or epsilon, we take a argument function that has some effects epsilon, and then we also ourselves have effects epsilon. And this suggests that, okay, higher order function probably can't mess with our raise effect. But I say purposefully suggests because we have to rely on a property which is called effect parametricity to trust our implementation of higher order function that it does not catch all effects, for instance, right? So if there's a catch-all mechanism, then you could still observe exceptions and maybe not propagate them to the outer context. So in general, traditional effect systems and also traditional effects, they are very similar to dynamic scoping, right? So we can't just judge from looking at this code whether raise will be handled by the exception handler that's immediately next to it. And now in contrast, this is the very same example, but now in what I call explicit capability passing style. And here we now have these two occurrences of the term level name Atkey. One is a binding occurrence, that is this one here, and the other one is a bound occurrence, right? And the basic idea is that capability passing or using capabilities on a term level is that they establish lexical scoping between the handler and the site where we actually use or perform an effect like raising an exception. And now the corresponding signature of higher order function could look like this. It doesn't mention any effects at all because it cannot observe any effects, right? If it would be able to observe the Atkey effect, then actually it would be something like or uppercase Atkey to tau, right? So it could actually provide the capability to the argument function, and then it would also show up here. And then again, by lexical reasoning, we can immediately see that we are now calling the effect operation, which is provided or handled by higher order function, and not by the lexically enclosing exception handler. So I'm talking about this here because in our work we focus on capabilities and this capability approach and lexical scoping. And to contrast now traditional effect systems with our approach, let us look at how effects are traditionally typed, right? So often you have judgments which look like this here. And in addition, we also have already seen such judgments in our first talk today. In addition to the return type or the type of the value that we produce, we also have, for instance, a set of effects that could be read as additional output, right? So we both produce tau and we can also throw potential exceptions. So this is like a different control path. And on function types, these effects typically are reified in a similar form. So often this is read as a ternary operation. We have argument, result, and the effects of the function. So there's nothing new here. And but what's an interesting property of traditional type systems is that we can use the additional information that we have to reason about what effects can occur at most, right? So I'm looking at the function signature here. We can reason about it and say, okay, yeah, the worst thing that can happen is an exception, right? It's a conservative approximation because maybe the implementation doesn't actually throw an exception, but no other effect could occur. So that's a property of these effect systems, and we can reason about purity. And operationally, as I've discussed on the slide earlier, effect usage and handling, they are often dynamically scoped. So at runtime, this order of handlers on the control stack actually determines which one will handle an effect operation. And yeah, we refer to this mode of reasoning about the absence of effects as a type-based reasoning. And now let's contrast this to capability-based effect systems, or treating effects as capabilities. And here we see, okay, now if I have a statement S and I want to type check it, I assume, or I can use the fact that our typing context gamma might contain this capability, right? And this fact can be also reified into our function types, where now function not only take some arguments, but also potentially some capabilities. And now you might notice that we can't approximate anymore what's the most effects that this function can use, because we also have closure in our systems. So a function could potentially close over some other capability than Xe, and we have seen that in our example. But we can now approximate what are the effects that can be observed from the outside, from the caller. And by observed, I actually do not mean like observed by side channeling or anything, but observed by handling them concretely, by providing capabilities. And the basic observation is, okay, now effects usage and handling, they are lexically scoped. Just like arbitrary values in many systems are also lexically scoped. And thus we refer to this as scope-based reasoning, because we can just use all of the effects that are in our current scope, that are available as capabilities in our scope. So let me show you one example. Here in this example, we first define some function which is called myModule, and it abstracts over two capabilities written in braces. One is called console, the other one is called time. And now we define a local function that's called sayTime, and it uses these two capabilities, right? So it uses console to print something, and then it uses time to refer to the current time. And we can just use them because they are in our current lexical scope, right? So they are available here. And if we look at the type of sayTime, it doesn't mention at all that it uses console or time. It just says it goes from unit for no arguments to unit. And I personally think this is a good signature in terms of that it's very concise. It hides the fact that there is effects being used, right? So this might be a bad thing. We will come back to that later. But it is very concise, and it's also truthful in the sense that sayTime doesn't have any unhandled effects and effects that we have to handle in order to call it. They are just provided by the lexical scope here. So capabilities, they give us very concise types. What's about effect safety? Is that actually leaving out these information from the types, is that actually safe? And I've talked about closure and lexical scoping, and we have this example, or we have seen that example already, and it's a mechanism to actually obtain effect polymorphism, in the sense that higher order function was effect polymorphic. It can take arbitrary function arguments that can use arbitrary other effects, and without actually having to abstract over effects by means of explicit polymorphic abstraction, like for all epsilon or something. We don't need that here, but still we have some form of effect polymorphism. However, closure is also a very easy mechanism to actually break effect safety if you consider the following example, where we introduce this capability Xe here, and then we return a closure that closes over Xe from our scope, right? And this obviously would break effect safety because now calling Xe outside of our effect handler, the effect handler is no longer on the stack, and the program crashes, and that will be very bad if that will be allowed. So what can we do about this? And a technical solution that for the effect language that we used is to distinguish between first class values and second class values, and you'll see what that is in a second. So In general, first-class values, they can just be returned and stored like arbitrary values that you're familiar with. But there's this restriction: they cannot ever close over second-class values. And then on the other side, we have second-class values, and they cannot be returned or stored. So there's the restriction on second-class values. But they can actually close over other second-class values, and obviously also over first-class values. And following from this paper, there's observation that if a function that would be second class, for instance, cannot leave the dynamic scope it is defined in, then it's perfectly fine to not actually track any effects on it, because the dynamic scope, it can go only up or down the call stack depending on how you draw call stacks. So it can only travel in one direction, it can never be returned, right? So it's fine to not track its control effects. And in the language effect, we embrace this idea, and we have first-class values. We often call them value types, and examples are int and bool and user-defined ADTs, and we pass them in around parentheses. And then there's block parameters, and they are second class, and they can never be returned. Okay, so this example here, it's safe. We define a local function, second class closure. It closes over some capability xe, and then we also pass it to a higher order function, and there's no worries. It can never be returned because it's second class by construction. So that's very nice. And in our previous work, we always had that slogan saying, okay, in the effect language, there simply are no first-class functions. And that made many people a bit anxious. Like, oh my God, how am I supposed to program in a language without first-class functions? Actually, it wasn't that much of a restriction because we do have higher order functions, just not first-class functions. And in fact, the example that I've shown you before, it's actually not syntactically valid because you cannot return functions, syntactically even. However, we want to address this. And in the remainder of this talk, we want to actually bring back first-class functions in a safe way. But we do not want to sacrifice the ergonomics. We don't want to have verbose type signatures for effect polymorphic functions. And as a step towards this goal, we make the notion of second classiness more fine-grained. We will see that in a second. And then we actually index types, and that's now finally where grading comes in, of first-class values, which are functions in this example, with additional information. Okay, so first step, let's generalize second-class values. We have this example again, right? And we assume that console and time, they're available in the lexical scope. Then here's a second example. It's called repeat, and it takes a function f, and it calls it n times, right? And that's it. So there's nothing special happening here. And finally, we have a third function, which is called say time thrice, and it calls repeat, and actually it passes a say time, which is eta expanded here. And now if we observe what each of these functions close over, right? We can say all of them are second class, and they treat also their arguments as second class, but we can be more precise. So we can see, okay, say time, it actually uses console and time. So we could reflect that in our, or reflect that on our binding. We have this a little bit more information, right, about say time. We know it closes over console and time, the capabilities. Repeat, in contrast, it doesn't close over anything, right? So it we pass f to it, but it doesn't close over anything. And then finally, say time thrice, it doesn't close over anything directly, but since it passes say time to repeat, it indirectly closes over these console and time capabilities again, right? And this is additional information that we want to track in our type system, not in the types, actually. The types are still very simple. It's unit to unit for the first function, for instance, but still track it in the type system on our bindings. And formally, this can look like this. So we have these value types tau, and we have block types sigma, and you see we have multi-arity functions because, currying in effectful language is one of the prime evils. And then there's a capability sets. These are just sets of block, of what we call tracked variables, like capabilities, for instance. And now the magic is in our typing context. So typing context can be empty, of course, but we can also bind values, which are boring. But in particular, we can also annotate our blocks, our bound blocks with additional information. So there's two different binders. There's tracked bindings, like for capabilities, and then something called transparent binders. And this is something we would put on, say, time, on this function, right? So there we put console and time. So as an example, here we could type check an arbitrary statement in a context that has some capabilities like console and time, and also our function say time that is a transparent binding because it is truthful about the capabilities it closes over. And importantly, just to emphasize, the annotation is on the binder. It's not on the type. So we want to keep our types concise, but track more information. And I think there's lots of Coeffect people here in the room, and also contextual modal type theory people. So I think they would agree that tracking additional things in the typing context might be a good thing. Okay, so just a very brief introduction into the syntax so that you can see some typing rules. Our systems are often in fine-grained call-by value, so we distinguish between pure expressions, that is just boring values, and also blocks, which are essentially functions. We just call them blocks to not confuse them with first-class functions. And then there are effectful statements, right? And they are sequenced. So we have a sequencing here you can return. So these are basically monadic operations. We have function calls, and also we can bind blocks to block variables f. Okay, finally, let's look at some typing rules. Yeah, well, there's nothing special to see here for expressions. Expressions are boring. There's no effect. We don't need to track anything. It's completely standard. It's getting more interesting if you look at block typing, where our typing judgment now has this additional context restriction C. And for the Coeffects people in the crowd, you could read this as an additional information on the typing context, right? We write it in this style here because we actually want to read it as effects. We treat using capabilities as an effect, but you can still read it as a coeffect or something, as an annotation on the typing context. Okay, so for transparent bindings like say time, right? If we want to use a variable like f that's annotated with C, then we require C to be available, right? And for tracked bindings, same thing. We require f to be available right now in our context. So these are the two rules for block variables. And then we also have subsumption on these restrictions. So obviously in a context that provides some of the variables and some additional ones, we could ignore the additional ones. So for statements, these two rules are basically boring. So if you have pure expressions and we embed them in effectful computation, then the set is empty. And for sequencing, we just take the union of these two sets. So there's nothing special here. Interestingly, for when binding blocks, right? So we first type check the block against a restriction C prime, and then we put that on the binder. And then we go on with some arbitrary C. So the closure of our block doesn't actually immediately propagate into our own context. And again, on statements, we also have subsumption. And that's already enough to type check a program like this, right? So we have, okay, I didn't show you the actual application, but so we have seen blocks here and how the capabilities just flow outside to the binder, and then we put them on the binder. Right? That's the idea here. A bit like tracking free variables. Okay, so for blocks, if we want to type check a block, we type check the body, and actually we allow the body to also use the bound parameters, which are tracked. So we put this little star here. And then we actually don't add this information into our types. So we just make that available in our typing judgment. And for type checking an application, we first type check it against the function type, obviously, and the arguments. And right now, this is also completely boring at the moment. So obviously, it will be just a type tau, which is the return type. And the restriction that the call itself has to be typed in is the restriction of the block of our callee and of our arguments, the union of that. Okay. And that's also now enough to say to type check say time thrice. Now it's we have tracked a lot of information, like the fact that functions close over capabilities, but we haven't actually used it so far. We just annotated our binders. They don't show up in the types. That would be a little bit boring if we stop here. When working on the system, we made this one observation, which I think is crucial, which is only ever when functions are used first class, then actually the types need to be truthful about the capture. Otherwise, we can just ignore it and have the same ergonomics as before. And what that does that mean? So if we have this function from before, repeat here, right? And now this is like computer science 101 example. We want to write a function repeat here that partially applies repeat to f, right? So what we do that, we need to return a function now, but how can we return them? They are second class. That it can't work, right? So the idea here now is to introduce this box construct, which is inspired by box modality, and various lines of work on that. And in that particular position, we now actually need to move from our contextual information to type-based information. So now the inferred type for repeater, it not only says it's int to unit, but it also annotates the function type with additional information. It annotates it with the information that we actually close over our argument f here, our block argument f. So that's where we move from our contextual information into our types. And here are some more examples, but I think I have to be a bit quicker about them. So this one closes over console, so we have to put that on the types. This one closes over say time, and we have seen it transitively closes over console and time, so it needs to be on the type. And also repeater of say time closes over console and time. Boxing would be completely useless if we don't have any way to actually get the functions out and call them. So there's no way to call boxed arguments. And that's why we introduce an additional construct which is called unbox, and it turns a first class function value, which can't be called, into a second class function, which now can be called again. And this is the moment where we go back from our type-based information to our context-based information, or tracking on the contexts, and make sure that the current calling context still supports the capabilities that need to be in scope. And formally, so we extend our expressions with the box construct and our types with this graded box modality. And similarly, we have this new block, which is called unbox. And the two typing judgments look almost too simple. So we just type check a block B in C, in the context restriction C, and then we put that on a type. So there's really nothing special here. And when we unbox E, then it has to have a boxed type. So it needs to be annotated with some capability C. And now we move in the other direction, and we require the current context to still support this restrictions C. Okay, so in summary, the idea is that we track reference to capabilities additionally on our binders. These are not necessarily visible to the users. It's just important bookkeeping in our type checker. But the moment where we actually use a function as a first class value by boxing it or in order to return it, for instance, then we actually need to reify this information into the types, and we use the box construct on the type level for that. And the other way around, if we now want to actually call it, actually use it in a different context, we need to unbox it again. And so boxing and unboxing, they allow us to transition between these two worlds. And in the paper, which I of course happily invite you to read, we have a full formalization, including operational semantics for effect handlers, our soundness proofs, and the artifact, which is here on the right-hand side, also not only includes this live demo where you can type check your own examples, but also the full mechanization in COG and some documentation of that. So with that, I'm happy to take any questions.
Great, thanks, Jonathan. I think we should do a quick question before lunch break. No, we're a bit over here.
I have a very quick question. So,
could you go to the front then, Vineet? Is that Vineet, I think?
So I was just wondering, instead of internalizing the global effect that you have on a first-class function as a coeffect in the context, have you considered internalizing it as a possibly a grade on the effect, like, you know, as a monad? Are there any trade-offs that you considered, or why did you choose this? Was it just because you already were tracking coeffects in the context, or?
That's a very good question. So actually, from a semantics perspective, the semantics of our system is actually given in terms of monads, because we model delimited control as a monad. We just track it as a more coeffect-like annotation on the context, because it immediately corresponds to this lexical scoping of capabilities. And there is recent work on by, for instance, Dan Lyon and Ning Shi on trying to also establish lexical scoping of effects in a system that's based on more traditional semantics, monadic semantics like free monads. But it's tricky because they need to kind of retrofit then to establish lexical scoping, whereas we start with lexical scoping and it fits very well into typing context and about tracking additional information in the context itself. So I think it's about this story of lexical scoping.
Yeah.
It makes it fit nicely.
Yeah, great. Thanks.
Oh, there's a question from Alex.
Hi. Yeah, I think that this business with second-class values and not tracking the capabilities or the effects on a certain, if you're not going to return this value, I think, if I'm not mistaken, that should correspond to actually modal possibility. So if you use box, which is model necessity, I presume here, then the second order thing is actually a diamond, so modal possibility. I think I can give you more references on that idea if you want to take a look.
Yeah, that would be great.
Okay.
And obviously, it's very closely related to contextual model type theory. So
right, but in contextual model type theory, in that paper that we wrote, we never talked. I mean, we just briefly talked about the diamond in the future work, but so that's not all that well explored. But yeah, I think it actually closely corresponds to diamond.
Yeah. So our annotations on the typing context gamma, they could be read as the modal context, right? Because you annotate each.
Right. But with the diamond, you will need context on both. You will need the annotation on both the left sides, on the context, but also on the judgment on the right side. And then eliminating the diamond gives you exactly this business whereby you can, in the limited scope, if you're not returning the value, you can actually not track its annotations, because the handler, so to speak, which the diamond provides, just handles everything that's in this. The handler is being installed as a global thing. So then you can ignore anything that it handles inside.
Yeah, it would be great. We haven't thought about diamond modalities yet, so I would be
Okay.
happy to take any pointers.
Great. Okay. Thank you very much. Thanks, speaker again.
Thank you.
Okay, so we move to the lunch break now. We will resume at 1:30, and yeah, I'll see many of you then. And I think everyone who's in person will go to the Gulbenkian. I will try and stop by on my way to the nursery at a distance and just say a quick hello in person. And yeah, I'll see everyone else. Yeah, after the break when we continue, and Jean-Philippe will be. We'll be talking after the break. Thank you.
Something a little.
This meeting is being recorded.
Okay, voice. So hopefully a less technical, well, perhaps a less technical talk now. And also perhaps this is good after lunch, I don't know. Joint work with Julian Grove. If I can. There you go. So I'll give a bit of background to begin. And there is Zoom thing here. Let me see if I can put this out of the way so I can read. Well, why don't you read the slides while I'm setting up my Zoom? I've been told by pedagogical experts that whenever you have a quote, you should let the audience read it and not read it yourself. I suppose I have time to do both. So, so this is a quote from Richard Montague, and it's sort of in the tradition of treating natural language as a mathematical object. And what he's saying is it should be possible to understand the syntax and semantics of natural language using a mathematical theory. And this was more than 50 years ago. We shall see a little bit what we can do about it. And so when we talk about natural semantics, or when I talk about natural language semantics today, what I mean is we aim at giving this kind of precise mathematical meaning, the same kind of thing that you would apply to a programming language, really. But now we're going to see if this applies to a natural language. So maybe this kind of approach is unfamiliar to most of the audience. So let's start by something simple from Montague. So let's, well, in the Montaguian style, let's say you want to analyze the sentence "John walks." Well, how can this be done? Well, let's say you can interpret the words of the lexeme John and walk independently. What would it look like? Well, John can be interpreted as an entity. And so here the type is E. Walk would be interpreted as a predicate, so a function from entity to truth values. And here we're going to leave entities and truth values completely abstract. It is not going to be our focus, but you can imagine, if it helps you, that E is a kind of element in a set, let's say, and T, it could be logical formulas about this set, or let's say possible worlds that concern the set of entities. And so if we analyze the work as a predicate and John as an entity to obtain the truth value, so that the truth value that correspond to the sentence John works, well, we simply apply one to the other. And here I'm making things a little bit more complicated by using a reverse function application so that we keep the textual order as well. That can be useful, as we shall see. Okay, very well. I see there is chat already. Sounds very loud, doesn't it?
Don't worry, that was that is not on your side. It was in the room mic, but we've muted that now.
Okay. Feel free to interrupt at any point. I often miss chat questions, but unmute yourself and go ahead. I don't mind questions. I don't think we are that many that this is going to be troublesome. All right, so this is sort of the basic idea. Okay, so just as a warm-up. Now, dynamic semantics. Okay, so what we have seen so far, it's very similar to what you would encounter in logic. It's what you can call pure interaction between the various syntactic categories, nouns, adjectives, adverbs, verbs, etc. And so you can just do it by function application, and some complications occur for quantifiers and things like that, but it's going to follow the same kind of structure. However, there is certain aspects of natural language that don't follow this sort of pure analysis, and it's best to use side effects. I'm going to talk a bit more detail how anaphora fits the picture, but the overall approach, anyway, is to change the Montague semantics to be monadic. Okay, so what could that possibly mean? Okay, that's a little weird here. So the monadic dynamic semantics, well, what do? We enthuse every lexical item with the possible set of effects and in the types, it's reflected by making the type monadic. Okay, so work is not just a predicate, it's a monadic effect, and that returns some predicate, and likewise for John. And well, this is where the reverse application operator comes in handy. We are no longer using the straight application, but we use the applicative functor structure over M, and here it's the the reverse operator as well, just to keep the order of the words the same. Okay, and so there you have it. In this case, there is no useful effect to speak of, but anyway, the types function, and we find that the phrase John works itself is potentially effectful, even though there is nothing useful to speak of here. Well, it's only applicative functor. Why we talk about monads? Well, you can ask the question later. It's a bit hairy. So, an example of a useful effect, anaphora. Okay, so for the non-linguist audience, what is anaphora? Well, whenever there is an expression that depends on the context, we can characterize it as anaphora, but typically it would be pronouns. Okay, so for instance, if you have the discourse, John is here, he walks, well, that should be meaning the same as John is here and John walks, because he would, in this case, unambiguously refer to John. And so, well, that's an example of anaphora. Okay. So that being said, what does it look like to have a monadic interpretation of anaphora? Well, can use state, a state monad. So here I'm going to do a sketchy version of it. So we could interpret the proper noun John as doing two things. So not only returning the pure value that corresponds to the entity John in the set of entities, but also save that entity or store that entity in the state. Okay. So first you store it and then you return. Very good. And then a pronoun can retrieve this entity from the environment. Hopefully this is clear. So we can use the get from the state monad, and well, that's going to retrieve the entity that we saved previously, that we stored previously. Okay, and so this way, the phrase John is here heroes. Well, we're going to interpret John, and there is a predicate that doesn't change the state. And when we get to he, since we have kept the word order by using the applicative functor of the right kind, the applicative functor, well, application of the right kind, functorial application of the right kind, then at this stage, when we get to he, we're going to retrieve the entity John from the state and interpret it correctly. Okay, so obviously, this is very simplified for pedagogical purposes. In practice, you can complicate this to your liking. For instance, you can have many entities. You can have a thing that doesn't just get whatever entity that was introduced last, let's say, but you can have you can retrieve entities based on the features of the pronoun. So for instance, he, that would refer to a male animate entity, let's say, and so on and so forth. If you have several entities, you can probabilistically return the relevant ones, etc., etc. Okay, so that's an example of dynamic semantic effects. And well, our observation here is that you face the same kind of problem as what you do when modeling programming language semantics with monads. If you want to build a semantics which is modular or extensible, you have various effects that you want to consider in a theory, and how do you combine them? Well, that can be tricky. Okay. And so there is the approach of monad transformers, but that's, well, it gets you only part of the way there, because as you know, the order of, depending on the order of combination, you get different semantics, and it's generally not very satisfactory. Okay. I'm wondering if I'm okay with time. I think that should be okay. Yeah. So, all right. And now what we introduce is, let's use a graded monadic semantics for dynamic effects. Okay. Okay, so the graded monad structure is, I imagine what you'd expect. I might use this notation later on. Maybe something a little less conventional is we don't have just an equality relation between this defined over the set of grades, but we have a reduction relation. So it's written like this with the squiggly arrow. And we nevertheless want that the unit is the unit for the operator of the monoid that you have up there in the bind operator, noted star, and you want this monoid to be well. You want this to be a monoid. You want the operator to be associative, and here that means that you want reduction in both directions. Very good. And later on, we're going to give a semantics for this, and we're going to do so in terms of a lambda calculus, but without grades. So we actually explain something. Okay. All right. So taking a look at our example of anaphora. What's the grade? Well, we are going to remember the relevant introduced and used entity in any piece of the discourse. And so you can see here John. Okay, maybe I show with the cursor. Well, what does it do? Well, this part of the discourse introduces a new entity. So this is why it's E here, and now I don't know how to explain this. A new piece of the discourse E. A new entity introduced in the discourse E, and what we have on the left-hand side is a label, and we'll come back to that in a second. On the other hand, a pronoun like he is going to assume that there is such an entity in the discourse introduced. And we also use a label. So this label is somehow a description or an identifier for the reference that we are talking about. So before the colon, after the colon, here it's the type of the referent, introduced or assumed. And what I'm not going to talk about is how to resolve these matching between these kind of labels. This is a complicated thing in general. We're going to have some sort of resolution algorithm. I'm going to note anyway that the same kind of predicates about reference. So for instance, he is going to refer to male entities, this kind of thing. This is going to be what the algorithm manipulates. Anyway, and also a rich system of types can be used instead of just entities. Anyway, what's going to happen if we analyze the sentence that we had seen before? John is here, he walks. Well, we're going to accumulate the grades, yeah, according to the bind operator, and we're going to first introduce the entity John, and later on use it. And so the grade is going to reflect that, and you read it from left to right. So first introduction of an entity, and then assuming this entity. Very good. And then because there are two sentences here, both correspond to a truth value, and so I return two. I note that two truth values should be returned by the semantics of this. Okay, very good. And now, what does this mean? what does anaphora mean? And what's interesting is we can have an abstract view of how anaphora should behave simply by looking at the reduction rules for grades. So I'm going to ask you to look at equation 2 first. This says that if we assume twice the same referent, so we assume twice the referent D here, well, from a semantics point of view, it's exactly the same as assuming it once. And so we have this reduction from 2 times the same assumption to a single time. And this is what I call collecting assumptions. Also noteworthy is the equation 4. If we first introduce the referent and then we assume it, well, in reality, we don't actually assume it since it's already introduced. So we can forget the second bit. We can forget that we assume it. So it's really equivalent to introducing it. And so we have this reduction relation here. I mean, this part of the reduction relation. Okay. The rest is not as exciting, if that was. So if we refer to different reference, then we can commute the grades, commute this part of the grades, and likewise for introductions, they can commute. And if we talk about different reference, they can also commute between introduction and assumption.
JP, and is there a reason that you've got some of these are equalities and some are reductions?
Yeah, I mean, so, here I want reductions in both directions. I really want them to be. I want them to go both ways, because otherwise you may get stuck in a corner if you don't.
But is that a bit different to equality? You're not saying these like, well, I don't know. You're saying you want these to be syntactically the same. It's like you sort of quotiented it by the equation, or?
I mean, you can treat it in different ways, but technically what we have done here is we have reductions in both directions. So it's the reduction can go both ways, and later on we will ensure that it's confluent.
Okay. All right. Thanks.
Thank you for the question. Okay. So, well, in particular, in our example with John here, we first introduced John and then we assumed it. Well, it should be the same as just introducing it. Okay. And so, in the state case where anaphora was represented as the state monad, we had the familiar get and put. And the question here is, well, do we have the familiar get and put? Well, no, it's not exactly that. So I give them other names. There is an introduction operator that looks just like the put. There is an access operator that seemingly just looks at the put, but with grades, obviously. Okay. And they are the laws are not that of a state monad, because if you try to enforce the law of the state monads, then the grade reduction relation becomes non-confluent. And I can go into details later in case we have time during the question part of the talk. Anyway, it looks in the end almost the same as what we had in the simple state case, but now we use introduction for instead of put and access instead of get, and the grades are like so, and we get precisely the type that we wanted here if we run the analysis. Yeah, first introduce and then assumption, because we run first introduce, when we introduce, and when we take the semantics of John, and access when we use the pronoun. Okay. So that was anaphora in this framework. And what's interesting is we can describe a whole bunch of other effects. And what's nice is we introduce new grades for these new effects. And it's essentially independent from what we did for the other linguistic phenomenon. So one thing that can be done is to describe scope. And I think I'm sort of running out of time, so I'm going to gloss over that super quickly. Questions later if you care. What's a bit interesting, I think, is the semantics. So we turn the grades into well, we interpret them as a graded monad by interpreting every grade as a functor. And well, the unit grade is the identity functor, the composition is the functorial composition. And we're going to look at introducing an assumption here. So introducing, well, this is like a writer. Assumption is like a reader. And so if we come back to our John walks and John is here, he walks, the interpretation is, well, the two truth values. Okay, we don't really care about that. And but the effect is producing the entity that's introduced, and depending on the entity that's introduced. Since they turn out to be the same, there is a reduction. In general, whenever there is a reduction, then we will find a function taking us from the semantics of. So it's really a natural transformation between those grades. Okay, well, let's look at this case. If you introduce and then assume an entity, then it goes like this. We must find a function from pair of introduced entity, function from entity introduced, to just pair of function entity, introduced entity. I'm not going to insult you and write the body of the function. I think you can find it pretty much instantly in your head. And the other one is for quantifier handling, and I think I'm just simply going to skip that. The point is, you have this for a whole bunch of different effects. Or am I actually running out of time? I don't know, can't remember. I think it's possible. Okay, and so I said before that grade reduction should be confluent. This means, in particular, since those two things are equal, if this reduces to something, I mean, if this reduces to something, then that should reduce to the same thing. And also, in particular, if you reduce the inner parenthesis on the right, if you reduce the composition on the right first, you're going to get the same result as if you reduce on the left first. And that's quite important for compositionality. So that means that you can understand a subpart of the discourse independently of its context. And this is quite important because otherwise it means that you can't really understand anything without having the full context. So compositionality is considered very important in this semantics of natural language, and well, we do have it. It's a property to test for every reduction law that we add. but it's not that difficult because most of the reduction laws that we have, they are going to be commutation. And so it's easy. Okay. Yeah. So let's conclude slowly. Okay, so we have our system of grades, and I think it's interesting that the parallel between programming languages or logic and natural language keeps to be a fruitful one, even 50 years after Montague's conjecture. So we have a kind of canonical semantics as functors for the monads. It's both nice and also perhaps a little trivial, but you know, I think at least the structure is clear. The reduction of grades provides meaning, and what's nice is, so we do it first. We can do it first thinking abstractly about the overall linguistic phenomenon on the grades, and then you figure out the semantics, the reduction on the semantics. So this is a really useful guiding principle in constructing the theory. The paper is going to appear in the, well, it's in the final stages of processing by the Journal of Logic, Language and Information. So hopefully to appear, let's say. And in the paper, we have more phenomena and more effects, if you're interested. And the point is, all these effects can be described independently. And if there is interaction, which can happen sometime, then more reduction occur, and then you have to check that you have a confluence of the resulting theory. But it's mostly modular. And I'm going to stop here. Is that okay?
Yep, thank you.
Very good.
Thank you, speaker.
Thanks for your attention and thanks for the invitation. I think I forgot to say that.
Okay, let's have a quick question. Thank you, JP. Let's just do a quick question. Nicholas, is there something you want to ask? You posted a link.
That may be the preprint.
Ah, right. Okay.
Someone found.
So I had a question. Has this kind of flavor that makes me feel like it's some kind of free construction, a bit like some kind of free thing, because it's almost like a term algebra and you're interpreting each one of the leaves and then composing them together. Have you thought about it in that way?
Yeah, it's a free construction.
Yeah.
Yes.
Do you have any proofs about the sort of freeness in a mathematical sense, or is it sort of more an intuition?
I mean, perhaps it could be connected to the talk from the morning. I'm not exactly sure. I didn't follow all the details, but it's not unthinkable. But I cannot like give you a. I mean, if you define freeness, then maybe it could be answered technically. But now I think just at an intuitive level, it's definitely something like that. Yeah.
Right. Yeah. Yeah. And I definitely had that feel of it when you're speaking. Yeah. Awesome. Well, thank you so much for that, JP, and lovely to have a talk like that kind of brings us full circle with also the meeting that was yesterday about sort of grading in philosophy, linguistics, and computer science. So that's yeah, thank you for that. Let's thank our speaker again.
Okay.
And the next talk is from Edwin, who I think is here.
Yes, hello.
Hi, Edwin.
Hi, am I audible?
You are.
Very good.
Okay, so let Edwin get his screen up.
Ooh, hang on, this is should have my screen now, I hope.
Yes.
Let's not have that. Let's have this bit.
Great. Okay, so the next talk is by Edwin Brady from St Andrews about Idris 2 quantitative type theory in practice. Thanks, Edwin.
Great, thank you. Thanks, Dominic. Yeah, thanks for having me as well. It's nice to be in Canterbury, even if it's virtually. So I would have loved to be there in person, but yeah, some other time. Yeah, so I'm going to tell you about the state of Idris 2. You may have, if you've heard me talk about this before, then I'm essentially going to tell you the overview of Idris as you may have seen before, but I guess I might have one or two new jokes if you're lucky. We'll see what happens. Yeah, so Idris 2 is a dependently typed. That's not what I wanted to happen. That's right. It's a dependently typed functional programming language with first-class types, and the reason, I suspect the reason Dominic asked me to talk about it here is that the new version is built on quantitative type theory as developed by Conor McBride and Bob Atkey. So I look at what other people are doing with quantities and with graded types, and I get jealous of some of the things that people can express. But I should say that what I want to achieve with Idris 2, or what I wanted to achieve originally with Idris, was just having a playground where I could write. Well, not even just a playground, but a system where I could write larger scale programs with dependent types and see how I could use expressive dependent type systems in larger scale software engineering. So larger rather than large. I don't know, this certainly doesn't count as large. But I've got to a point now where Idris works to the extent that we can use it to implement itself, which I don't know if that necessarily proves anything, but it does show that it's scalable to the size of a realistic language implementation. I give these numbers here, not because I think it's fast, but just to give you a sense that you know, it'll only take a few minutes if you want to download it and have a go on your own machine, assuming no issues with dependencies. What I have been working on lately, just as an aside, I haven't been working so much on quantities and graded types lately, because I think this 4 minutes is too big a number. This number gets bigger every time I give this talk, and this number's too big. So I'm taking a little bit of a diversion to re-implement the core and remove some of the bottlenecks that currently make this take too long. Nevertheless, I'm still going to show you what it can do and what its take on quantitative types is. Okay, I think given the time, I should probably just launch straight into the demos I'm going to do. I will say what I mean by quantities, or what Idris's take on quantities is. So this is based on, as I said, Conor and Bob's work on combining linear and dependent types. And the key idea that you'll see throughout the interactive programming that I'm going to do is that every variable in scope is associated with a quantity. So there's a lot of choices we could make for these quantities. And I subscribe to this idea of the language strangeness budget that Steve Klabnik talked about with reference to Rust. I'd quite like people to use Idris and develop libraries for it and just try stuff out, and you know, maybe even use it in practice. And so I do feel a little bit cautious about the kinds of things that I'm going to add. So while there's loads of possible choices for quantities, I've kept it reasonably conservative. So the choice we've made is that a quantity can either be 0, meaning that it's not used at runtime. This turns out to be really useful just on its own, which we'll see in a moment. We have 1, which is used exactly once at runtime, so that's essentially linearity. And then we have omega, which is unrestricted usage at runtime, which is basically what it was before, what it was before we built on QTT. Now, I should say now, if you do want to interrupt with questions, please do. I see there's 2 chat messages, but I can't see what they are. So if you do want to interrupt with a question.
It was just me commenting on on what you were saying, like, you know,
okay.
Sort of trying to make, you know, stick to one thing, you know, so people might use it. And I was like, yeah, in Gradual, we're like doing the opposite, like just going nuts.
I have to say, I think it's brilliant that people are doing the opposite.
Yeah,
because apart from anything else, you figure it out. I'll steal the idea. If that's correct. You know, that's,
yeah, of course.
If that's the way we go, then you know that's the way we make progress.
Yeah, steal away. Yeah.
Yeah, but just to say, if people do want to have, I will ignore any numbers that get bigger in this chat pop up. But if you do want to ask a question, I think there's a small enough number that you can just interrupt. Okay, so I think actually, although linearity is cool and interesting and we can do all sorts of fun stuff with it, I think actually the most important additional quantity that we've got is zero. So a problem that I wrestled with for a long time, and this is what my PhD thesis was about, is how do you know which bits of programs are needed at runtime, and how do you know which are compile time only? And until QTT came along, we had all sorts of analyses we could do. We had looking for duplicated values, so one of which you could erase, or doing a whole program analysis to see what was being used. Well, QTT makes it a lot simpler and a lot more comprehensible for the programmer, because you can actually see in the type what is there at runtime and what isn't. So I'll show a little example of that. So this is actually my new favorite introductory example for dependent types, for the simple reason that it doesn't have any vectors in it, but also because it's something that I think people will get the idea of this, and you've probably seen run length encoding before anyway. So it's a fairly basic compression scheme. I think it was originally used in TV broadcasting. So the idea is you say how many of a thing you've got. So if there's lots of runs of the same number or the same bit of data, you can compress it by saying how many of those things they are. So it's good for paint programs and like simple image formats. And the idea is you have a list of things and you compress it to pairs of the number of that thing and the thing. So what we do then to make sure that what we have, the encoding we have is a sound encoding of the input, we index the run length encoding by the initial list. So the empty encoding is the encoding of the empty list. And if we have a number and a thing and some more stuff, then that will be an encoding of n copies of x and that more stuff. So I've got a compress function down here. I'm not going to go into the details of the compress function. Just know that it exists, and that if you've got a list of A, then if it comes out with run length of that list, then it must be a sound encoding. Not the optimal encoding, because this n could perfectly well be 0, which would be silly, but I'm only after soundness here. I'm not after an optimal encoding. I'm going to show you how to this rep function. This is actually in the library, but for those of you who haven't seen Idris before, I think it's worth just very quickly showing how we do development. So I call this type-driven development by analogy with test-driven development. So the type comes first because the type is like our plan for the program or idea for the program. We develop it interactively. So by issuing commands, let's say here, give me a skeleton program, and it gives me a program with a hole. I can check the type of the hole, and we're already seeing something interesting here, which is that what is in the scope of that hole. So I'm trying to produce a list. I have an X of type A, I have a K of type net, but I also have an A of type, and it has this mysterious 0 next to it. So the 0 is the quantity. If it shows nothing, that means unrestricted. So K, X and K unrestricted. This A is a thing I'm allowed to talk about, but the fact that there's a 0 means that that's not going to be there at runtime. So I can already tell what's there at runtime and what isn't just by looking at the holes. So another thing I can do is case split on an input, and that will give me the 2 patterns for natural numbers, so that's 0 and successor. And rather than write this rather than go through the details here, another thing that's quite handy is we've got some very basic type-driven program synthesis. So if I hit Vim here, so there's the same things in VS Code and Emacs. So if I hit the generate button, it will generate some candidates for this function based on the type. And by some heuristic, it will pick what it thinks is most likely. So the heuristic it's choosing is The one it's found within about a second that uses all of the variables. And if I don't think it's the right one, I can kind of keep hitting it with a hammer until it. I mean, you can see that these ones it's generating are probably less likely. Anyway, let's go back to the correct one, which happened to be the first one. So the other thing I wanted to show you about, so you see 0 is just like the type that we're parameterizing over. Naturally, you'd imagine that's erased at runtime. It's also good to know that this list that we're parameterizing over is also unavailable at runtime. So let's try writing the uncompressed function. So the uncompressed function will get us back our original list. This tie in brackets just means we're giving a name to the implicit argument, so it's the same as this tie here. So it's so that we know what the element type is we're pulling out. So if I try the same thing of writing this uncompressed function interactively, what you might hope to be able to do, and what you could have done in Idris 1, would be to say, oh, I'll just have x's, just to make it clear that x's is a variable in scope. Like x's is the uncompressed list. Why should I bother uncompressing it? And I'll try reloading that now, and it says no, you can't do that because x's is non-accessible. That basically means it's got a zero available at runtime. And this is, I think, a good thing. It's clearly a good thing, because if that x's was available at runtime, it wouldn't have helped. We wouldn't have actually compressed anything, because we'd be carrying the compressed thing and the uncompressed thing. So yeah, that additional level of being able to express that something is a fact about a program. So the list here is a fact about the program, and the actual computation is handy. Just to finish this off, I'm gonna. So what I really want to produce is the singleton type that at runtime is going to be x's. So this is my way of saying, I know we can only talk about it at compile time, but we can have a value that, because the value is unrestricted and we have a compile time proof that the value is the same as this thing in the type, then we know that if we can produce one of these, it's going to be the same thing as the one we had in the first place. And again, I'm just going to generate that. We've kind of written the uncompressed program in the index of run length, so why should we write it again? So I mean, there's a lot of fancy type-driven program synthesis out there. What we have in Idris is pretty simple, really. It's the kind of the most naive thing that works and needs a bit of development, but it does allow us to say that, well, if we've expressed what we want to in the type, why should we do it again? So this is our way of saying, well, the x's was only available at compile time, but we can produce a thing at runtime that we guarantee is the same as the one we had before. So that's 0. That, I think, is the most useful quantity to have. But where things get more fun is where we can express more stuff is when we have linearity. So what we're using this for in a few places, and is for expressing resource usage protocols and talking about external states. So if we have some external thing, the external thing might be in a particular state, and we can only run operations on that thing when it's an appropriate state for running those operations. So a nice simple example of this to show the idea is an ATM. I don't know about you. I've used an ATM something like twice in the last 2 years, but I still remember how they work. They're basically in 3 states. They're sitting there waiting for you to insert your card. They're sitting there waiting for you to insert your PIN. And then on the 3rd state, everything is validated and you can do stuff. But it should only be dispensing money when you've got into this final state. And it should only be able to get from the card inserted state to the running session state if the PIN has been checked correctly. So I would like to express that in the types, and QTT, and combined with dependent types. I like to say that dependent types are a way of expressing what you can do, and linearity, quantities, is a way of expressing when you can do it. Put these two things together, you can well, you can express everything that that you might want to, maybe. Right. So how do we express that in code? This L is I guess call it the linearity monad. It's a bit more complicated than that, but essentially what it does is it lifts some underlying monads. Doesn't even have to be a monad, but it lifts some underlying context into a linear world. We can say, we can express how many times the thing the operation is returning is going to be used. So if we leave this out, it's assumed unrestricted. I don't really have time to go in here into the mechanics of how Idris does this. Essentially, there's a default argument values. So initializing the ATM will give us an ATM that's ready, and I have to use it exactly once. When I insert a card, I feed in the ATM that's ready, and it has to be, it's a thing that has to be, or the thing that is linear, and the thing I get back is an ATM with an updated state that I have to use once. And so on. The interesting case is check pin. So this res type it's essentially a dependent pair. So the first argument is the result of the operation. The second argument is a function that tells us what the resource type is going to be based on the result of the operation. So if we check the pin correctly, we're good, we can go ahead. If we check the pin and it's incorrect, then we're still in the card inserted state. So I'll show you how that works with a bit of interactive programming. This is where interactive programming really gets useful, because when you've got lots of things going on in the type, the programs that you end up with, I think you don't really see the fancy type shenanigans in the resulting program, but it's kind of hard to get to the right one because you've got to do the right thing at every step of the way. So having holes in interactive development tells you where you are and where you need to go. So here I've got an ATM in the ready state. I can use it once, and that basically means somehow I have to get rid of this. So I have to consume it, or the program's not valid. Two ways to consume it. One is just to not do anything, and another is to start the protocol and get to the end. So I've got one I made earlier here because it's easier that way. So inserting the card gets us to the next state. It's actually it's worth seeing what happens if I call that M prime, because then you see that we can still talk about the old state of the machine. So we might want to reason about that, for example. We might want to use that in some fact about the program later on. So it's important to still have it there in the context, or it might be important to still have it there in the context, but it's no longer available at runtime. We can only talk about the glorious past when we had an ATM that was ready. So we'll insert a card. We'll check the pin, and we'll see when we check the pin that this is in a fairly complex state here. So we're going to have to break this down a bit. So this res, it's a dependent pair type. We can pattern match on it. So the syntax for that is essentially this. So it's a pair of the result and the machine. Again, do it step by step. So now we have an ATM, but we don't know anything about the state it's in. So I can still do operations on this ATM, like maybe print a message on it where the state is irrelevant. But if I want to do something where the state matters, we've kind of got a clue in the type here that the next thing we're going to have to do is check the result of OK. So yeah, we can print a message if we want, no problem. And I'll just comment out the rest of the program, and you can see what happens when we're in one state or the other. It's now, just by the fact that we've done the case analysis, we now know that we're in a state where we can proceed. So this is allowing us to describe state transition systems and implement protocols correctly, be confident that we're following the protocol correctly, provided we've got this description correct, of course. So I have almost no time left to tell you this, but I'm going to summarize anyway. we can this protocol description. You get, I think you can get a long way with just these kind of simple states, and you can, once you start looking, you find state machines and APIs all over the place. So one of the most useful ones we found so far is network sockets, for example. So the Berkeley sockets API, I always found incomprehensible, but as soon as I wrote it down as a state machine, I could see what was going on, and you can give precise types to that. So that's one thing that you just see in Unix APIs. But you can have lots of fun with just looking at what other people have done with linear style type systems. So session types is one example. Session types introduced by Kohei Honda back in the 90s. They allow you to describe communication patterns tracking the state of a channel. So we can come up with descriptions of what you can do on a channel. So I can send a thing on a channel, I can receive a thing from a channel, and I can close a channel. I could come up with a global protocol description where I say, okay, a protocol is a request from a client to a server, a response from a server to a client, and then more of a protocol. And we can write functions that interpret that protocol from the client's point of view, from the server's point of view. Then when we write the programs for the client and the server that are running concurrently, we know that the communication pattern is going to be followed the way it should be. And I'll just show you the API. So this is pretty much the same sort of thing as we were seeing with the ATM, except that it's kind of calculated from the protocol description. So if my channel says the next thing I'm going to do is send something of type tie, and then there's the rest of the protocol, then I'm allowed to send. And then what happens next is, well, we run the next function on the value we actually set. Receive is the other way around. So we see this res again. This is a dependent pair of the thing that actually came on the channel. Because if we receive something on the channel, we don't know what we've been sent. So we're going to have to inspect it to find out what the protocol expects us to do next. But there's really nothing more than what was going on in the ATM example here. It's just that we have a function to calculate the next step of the protocol. Let's see, in the interest of time, since we were running a little late, I won't show this running unless people want me to. But hopefully you get the general idea that these protocol descriptions, anything where we can write a function that explains what happened next after a value was sent, so we can scale it up into something fancy like session types. I won't do this demonstration unless somebody asks. So I'll just wrap up there. So quantitative types, I think what's really cool about them that I've really found useful is that it's telling us more during interactive development how we can use the values that we've got. So it's telling us if something is available, it's telling us if something is available only once. Also, something we haven't really looked into, but if it gives the programmer more information, it's also giving program synthesis more information. So at least in theory, we could expect this to be additional input that we give to our program synthesis tools. One thing to say, a couple of things to say about the future. So what I've showed you with session types here, we've only got binary session types for concurrent programs. That's already potentially useful, but there's so much more you can do, and there's so much more work being done on session types that it would be interesting to see if we can encode it. So, can we encode multi-party session types? How do we express which parties know what? How do we handle errors and timeouts? But I think the thing I'm more interested in for the moment is how can we make the quantities we've got more expressive without somehow blowing our language strangeness budget? The biggest thing I want actually is to be able to quantify over quantities. So it's kind of annoying that we have to say something is definitely 1, 0, or omega. We tried something a bit more expressive at one point and ran into all sorts of problems with subtyping, and so decided not to do that. So yeah, I'm looking forward to hearing what other people come up with that, as I said earlier, that we can steal to make what we can do in Idris much better. So yeah, I'll stop there. I'm happy to take any questions though. Thank you.
Thank you, Edwin. So let's have some questions. I kick things off. So why do you need the IO monad for the linear session channels interface? Do you really need it?
You don't really need it. You know what, as I remember it with this example, it was just to have fewer moving parts. So you could have, so at some point you need to fork, and you need the ability to send things and receive things, but there's no reason why that has to be done through an IO monad. One thing you can do, in fact, the way the IO monad's implemented in Idris is we have a linear world type, which is like a token that represents the outside world. And something I've experimented with is saying, well, let's not use the monad. Let's just pass that world type around and see if we can program with it directly. It works. I don't really like it, but it works. So yeah, you could imagine that this is just there is a constraint on this that says it's, well, as long as it's something that knows how to do concurrency.
Okay. Any other quick questions? If you're in the room, you'll have to shout or stand up near one of the microphones.
Is there anything in the chat? There are any messages in the chat.
So I will say that we'll hear more about graded session types later, and also program synthesis from grades and quantities later as well. So you set things up wonderfully, Edwin.
Fantastic.
Some of the later talks.
Excellent.
Yeah. Great. Okay, let's thank Edwin again. That was excellent. So our next talk is from Pritam. Pritam, are you there? Can you share screen?
Yeah.
Excellent.
Do you see the screen?
Yep, perfect. So Pritam is a PhD student at the University of Pennsylvania. He's going to be talking about from ungraded to graded, a historical perspective on linear type systems. Looking forward to it. So over to you, Pritam.
Thank you. Thanks everyone. So my name is Pritam Choudhury, and in this talk, I shall share my perspective on the evolution that grades played in that evolution. Okay. So let's begin. So I have been working on graded type systems for some years now, and at times I ask myself, why graded type systems? What purpose do they serve? I know that this is a difficult question to answer because we haven't yet fully explored the potential of graded type systems, but we can try to provide partial answers. So I shall provide my partial answer with the help of this analogy. So on screen, you can see a timeline of the evolution of travel luggage. Do you notice any trend going from the older models to the newer ones? So when I saw this figure, the trend that stood out for me is that all the newer models have wheels underneath them. People who have traveled with the older models know how difficult it is to carry and turn these luggages around. But with the newer models, carrying and turning them around is almost effortless. So I like to think of grades as wheels. They are an accessory added to type systems to make them more flexible. This is true of a variety of type systems. Compared to their ungraded counterparts, graded linear type systems are more flexible. Compared to their ungraded counterparts, graded modal type systems are more flexible. Compared to their ungraded counterparts, graded information flow control type systems are more flexible. So in this talk, I shall focus on linear type systems and show how grades make linear type systems more flexible. So let's start with the history of linear type systems. So linear type systems started with after the introduction of linear logic by Girard. Linear logic can be seen as a logic of resources. Resources may be either linear or non-linear. Linear resources must be used exactly once. Non-linear resources can be used any number of times, and that includes no use at all. And the challenge was to model both linear and non-linear resources in the same type system. So one of the earliest type systems to address this challenge was Abramsky's linear term calculus. So in this calculus, all resources are assumed to be linear by default. The non-linear resources are then marked with a bang. Let's look at some of the typing rules. So here we have the typing rules. The var rule is because all assumptions are linear, so we have just x of type A in the context in the var rule. Then for the bang, we have 4 rules: the promotion rule, the dereliction rule, the contraction rule, and the weakening rule. The promotion rule corresponds to nonlinear resources being used multiple times. The dereliction rule corresponds to nonlinear resources being used linearly. The contraction rule corresponds to nonlinear resources being copied, and the weakening rule corresponds to nonlinear resources being discarded. So this system has some good properties, but there is a syntactic problem with this system. Promotion does not commute with substitution in this system. So the substitution lemma looks like this. Let's see what happens when we promote and then substitute. So we have f and we have x and then we have fx. And then we have y of type bang b, and we promote it to bang y of type bang bang b. And when we substitute fx for y, we have bang fx of type bang bang b. Now, what happens when we first substitute and then promote? So we substitute fx for y, and then we have fx of type bang b, but now we cannot promote because the assumptions in the context are not bang. So promotion and substitution don't commute with each other. The system gets around this problem by including substitution as an explicit typing rule. So now this problem was addressed in a later type system, the intuitionistic linear type system by Benton, Bierman, Dipaiva, and Hyland. So how do they address this problem? They just bake substitution directly into the promotion rule. So let's look at some of their typing rules. So the dereliction, the contraction, and the weakening rule are similar to the ones we just saw, but the promotion rule is different. Here you can see that it is both a promotion and a substitution rule simultaneously. So with this promotion rule, substitution can be proved by an induction on the typing derivation. One does not need to add it as an explicit typing rule. So these two systems, Abramsky's system and the system of Benton and co-authors, are the standard ungraded linear type systems. They have some good properties, but they also have some problems. What are the problems? The first problem is that they're verbose. They need explicit term level constructs for promotion, dereliction, contraction, and weakening. The second problem is their promotion rule. In Abramsky's system, promotion does not commute with substitution. And in the system of Benton and co-authors, promotion rule is simultaneously a promotion and a substitution rule. The third problem is that there are no clean introduction and elimination rules for bang. You have these 4 rules for bang, no clean introduction and elimination rule. So what is the root cause of these problems? I would say the root cause of all these problems is their assumption that all resources are linear by default. This makes the system rigid, makes it difficult to model nonlinear resources. So let's see how this problem was addressed. So now we move from ungraded systems to systems that are somewhat graded. I shall call them semi-graded systems. So these systems give up the assumption that all resources are linear by default. They make the system more flexible by dividing resources into two sets, linear and nonlinear. And then use dual context to represent linear and nonlinear resources. And change the typing judgment to reflect that. So here gamma contains linear resources, whereas delta contains nonlinear resources. The two standard dual context linear type systems are the linear nonlinear lambda calculus by Benton and the dual intuitionistic linear type system by Berber. In this talk, I shall focus on the dual intuitionistic linear type system by Berber. So it is a semi-graded linear type system with dual context, linear and nonlinear. Let's look at some of the typing rules. So for var, we have two rules. One is the var L rule for linear variables, and the other is the var NL rule for nonlinear variables. So notice in the var L rule, in the linear context, there is just X, because linear resources must be used only exactly once. Whereas in the var NL rule, delta can have more variables because they are nonlinear in nature. In the var NL rule, the linear context is empty because X is a nonlinear variable. We don't want any linear variables to be discarded. Now notice that we have two rules, an introduction rule and an elimination rule for bang. In the bang intro rule, there can be no linear assumptions in the premise because we cannot copy or use linear resources multiple times. In the bang elimination rule, because we are eliminating a bang, we pattern match it against a nonlinear variable. So X appears on the nonlinear side of the context, on the nonlinear context. So Berber system has many good properties. It addresses all the problems, all the three problems that we discussed. Bang has a clean introduction and an elimination rule. No need of additional constructs for promotion, dereliction, contraction, and weakening. And substitution can also be proved by straightforward induction. So this is all good. We can track linearity using Berber system. It works well for a simply typed system. But can we extend them to richer type systems, for example, dependent types? Let's consider this suggestion. So here is the application rule in Berber system. We have gamma 1 and gamma 2, and in the conclusion, we are concatenating those two contexts. Now, what would a dependent version of this application rule look like? It may look like this. We are doing the same thing, just changing the types to dependent ones. Now, the question is, can A depend on the variables in gamma 1? The answer is no, because then the second premise judgment wouldn't type check, because gamma 1 and gamma 2 are disjoint. So if A depends on some variable in gamma 1, then the second premise wouldn't type check. Similarly for gamma 2. So A cannot depend on either gamma 1 or gamma 2. So A cannot depend on any linear variable for that matter. So in such systems, types cannot depend upon linear variables. So a funny way of saying this is that dependency stops where linearity starts. So and this problem remained as such for a long time, and this made some people believe that linearity and dependent types are inherently incompatible. A breakthrough was necessary, but it was not clear where and how. So sometimes when breakthroughs are necessary, we need new perspectives. So let us look at linearity from a new perspective. Let us look at linearity as a coeffect. So what is a coeffect? Coeffects model the dependence on programs upon their environments. For example, how much space does a program need? How many memory lookups does it need during evaluation? Linearity, which accounts for resource usage by programs, is a coeffect. Now, let's take an example. So let's say we have this term x plus y. While evaluating it, we need to use x twice and y once. So the idea here is that take a general coeffect calculus and specialize it to track linearity. So let us look at a general coeffect calculi then. So coeffect calculi have a long history, but research picked momentum around 2014 with 3 key papers. One on bounded linear types in a resource semiring by Gika and Smith. The second, a core quantitative coeffect calculus by Brunel and co-authors. And the third by coeffects, a calculus of context-dependent computation by Petrichek and co-authors. So the interesting thing to note here is that all these 3 papers use the same principle to track coeffects. All these papers use semiring-like structures to represent coeffects. All these papers grade individual assumptions in the context, and all these papers freely manipulate the grades on assumptions via the semiring operations. In this talk, I shall focus on a core quantitative coeffect calculus by Brunel and co-authors. So let's look at this system. So it is parameterized by a partially ordered semiring. The contexts are graded by the elements of the semiring. You can see the R on the colon there. Now we have operations on context. We have context addition. So how is this defined? When the same assumption appears in both the contexts, you add the grades. Otherwise, you just keep them as such. We also have context scaling, which scales all the grades in the context. Then there is an ordering on context, which says that increase in order means more resources. Let's look at some of the typing rules. The sub rule is like, if I have more resources, I can throw some away. The variable rule is as expected, and we have the bang intro and the bang elim rule. Notice that the bang intro rule in the dual context system required that there be no linear assumptions in the premise, but here we don't need any such restriction. And in the bang elim rule also, there is a difference. In the dual context system, the linear assumptions were just concatenated in the conclusion, but here we add them. And this makes a difference. How? Let's see. So how we can use this graded system to track linearity by using 2 grades, one for linear resources and omega for nonlinear resources, with the ordering that omega is greater than 1. And linearity tracking in this system is more flexible. Let's see with the help of an example. The reason behind this is the same linear assumption can appear in multiple premise judgments. For example, in the dual context system, this derivation is only possible, but not this derivation. So what is the difference between these 2 derivations? Note that in the bottom derivation, in both these judgments, X appears as a linear assumption, and then in the conclusion, X is assigned nonlinear role. Whereas in the top derivation, X just appears as a nonlinear assumption all throughout the derivation. So here X can appear as linear in multiple assumptions and then be assigned a nonlinear role in the conclusion judgment, but something that is not possible in a dual context system. So in a simply typed setting, this flexibility does not give us anything much, but in a dependent setting, this becomes very important. Let's see how. So let's go back to dependent types. Where were we? Types cannot depend upon linear variables, leading to dependency stopping where linearity started. So how can we use the ideas from graded type systems to overcome this problem? So we have this potential dual context application rule for a dependent system where we saw that neither A cannot depend upon the linear variables in gamma 1 or gamma 2. So let's try to formulate this application rule in a graded fashion. So here is a graded version of the same rule. What the third condition means is that gamma 1 prime and gamma 2 prime, when you take away their grades, are exactly the same. Now, this is very different from the DILT rule where we have concatenation. Here we have an addition. So, and gamma 1 prime and gamma 2 prime have essentially the same variables in their domain. So here A can depend upon the variables in gamma 1 prime or gamma 2 prime. So the restriction that types cannot depend upon linear variables is lifted. So A and B can now depend upon variables in gamma 1 prime and gamma 2 prime. But this then leads to another problem. What's the problem? Now, notice in the second premise judgment of the RPCF rule, both the term A and the type A can use resources from gamma 2 prime. Now, the question is, in such a situation, how do we account for the use of resources in types? The good thing is the grades give us the flexibility to answer this question, not just in one way, but in multiple ways. So let's see how. Here I shall first describe why linear dependent types require a graded type system. Because here we have two kinds of use in action, one in types and the other in terms. Graded systems help decouple these two uses. They also allow simultaneous use in types and terms, and they offer the flexibility, they offer multiple options for accounting use in types. I shall discuss three possible ways. One is the approach of McBride and Atkey, don't count use in types at all. The second one is our approach, count use in types, but only when they appear as terms. The third is the approach of Moon and co-authors, where you count use in types all throughout. In this talk, I shall focus on our approach. So let's look at our approach of accounting resource usage in a dependent type system. So we have our system is called GRAD. It is a graded dependent type system parameterized by a partially ordered semiring. We count use in types, but only when they appear as terms. Let's look at some of the typing rules. So notice the variable rule. Here, the capital A, the type A, can use resources from context gamma in the premise because it is appearing as a term. But when it appears as a type in the conclusion, we zero out those resources. We zero out those assumptions. So when it appears as a type in the conclusion, it does not use any resource. The sub rule is as expected. The pi rule is interesting. Notice B can use X any number of times. It does not have to use X linearly. So B can use X R times. R does not have to be 1. R can be anything. But in the lambda rule, small b, the term B has to use X exactly once. So this is the difference between accounting in types and terms that we have. The application rule is like the one that we just saw. So GRAD has an operational interpretation where use corresponds to memory lookups. So now let's recap the development of linear type systems. First, we have linear logic by Girard, then the ungraded linear type systems are proposed, the one by Abramsky and the one by Benton and others. Then we have the semi-graded linear type systems, the one by Benton and then the one by Berber. And then we have on the other side work on graded coeffect calculi, Gika and Smith, Brunel et al. And Petrichek et al. And then we see that linear and dependent types finally start talking via grades. We have McBride's Plenty of Nothing, Atkey's QTT, and then our grad and Gertie by Moon and others. Okay, so while I was looking at this historical development, I could not but notice that this evolution parallels the evolution of numbers in human history. How is that? The evolution of numbers in human history also went through 3 stages. In the first stage, there was just a number sense. For people at this stage, number is a concrete reality, inseparable from the nature of the objects directly related to it. For ungraded systems too, grades are a concrete reality. They are inseparable from the types, and they are directly related to the types. So accounting at this stage is very rigid. Then we have the semi-graded type systems, and we have numbers showing up, but they are tightly connected to physical objects. For example, parts of the body, notches on bones, knots on strings, beads on abacus. So here we have the semi-graded type systems where we have grades, but they are connected to the zones of the context. We don't have them separately as an entity in itself. Accounting at this stage is more flexible, but it is still difficult. Then we have the graded type system, and we have abstract numbers. So for people at this stage, numbers are abstract entities represented through symbols and manipulated through rules of arithmetic. Here too, we have grades that are abstract entities represented using elements of abstract structures and manipulated using algebraic operations. Accounting in this stage is very flexible. So with this, I shall conclude my talk. I hope I have been able to convince you that grades help make type systems more flexible. So thank you.
Wonderful, Pritam. Thank you very much. Yes, that was a really nice capture sort of view of the history there. Let's take some questions. Bob's standing up there.
Hi, can I ask a question? Thank you. It's a very nice talk. Particularly like your last evolution of systems thing. So I would say now, like some of the experience from dependent type programming is that numbers are just abstract nonsense, and they don't provide enough information. So you want kind of you don't want to do array programming with numbers. You want to do array programming with proofs of locations exist inside an array, because otherwise you get index out of bounds exceptions like that. So is there a step beyond grades where the grade is tailored to the type? So at the moment, all these graded systems, the grades are independent of the type of the thing they're talking about. But I was reminded of this morning, I think something in the talk Andrew gave, was sometimes you want the grades to be kind of like, why are we only talking about graded monads or graded co-monads, essentially? Like, why aren't we talking about graded other types? So things like numbers having unit types and things like that. That's kind of my big question. Is there a step beyond just abstract numbers that goes to more structured kinds of grading information?
Thank you for the question. I think like it is quite possible, because I have felt that grades don't capture everything that I want. Like I think like there are 2 possible directions that may be taken. One is like find richer structures or more expressive structures That would be one way. The other way could be like find a different mechanism altogether, like maybe something more general than grades. I don't know what that would be, but that might be another possibility. Having said that, I would also say that we haven't yet fully explored the potential of graded type systems even. I think there's a lot that can be done just with grades. So, and that might also give the clue to the things that might be done next.
Yes. So just to add just a comment here. So I think we have already started exploring grades which go beyond decorating just monads and comonads. So for instance, in the context of amortized cost analysis, when we look at potentials. So potentials, one view of potentials is that you can add it to any type, and the way you introduce and eliminate them, they don't really follow the monadic or the comonadic structure actually. So yeah, so I think yeah, we have already started looking at those kind of things. So it's just a comment to Bob's question.
Yeah, like I haven't read the entire paper, but I have skimmed through it, and I think it's a nice paper. I have used the idea of potential in a different context, like in some work on monads and comonads, but not in directly a graded setting. Yeah.
Max, you have your hand up.
Hi, Pritam. Yeah, so I think I have a bit of an objection to the history there with the semi-graded part, or at least the way that you described it surprised me, which is that, my understanding is that the problem with these original linear type systems that was solved by linear, nonlinear logic and Dill was that the earlier systems were basically trying to take the comonad structure and just directly add it into the rules. And what Dill and linear nonlinear logic did was that they gave and the problem with that is that the comonad doesn't have a universal property. It's not a left adjoint or a right adjoint. Whereas in LNL and Dill, they give the type a left universal property, or in LNL, they break it up into two types, one which is right and one which is left. And so I think, like, I'm not sure that really had to do with, I'm not sure what the relationship between that is and the grading, because I think you could take the graded semantics that we have now and do just a bad job with it and reproduce the early bad systems that they had for linear logic, like try to give the same kind of bad dereliction rules, etc. And it's more that we learned that lesson that types should have universal properties makes everything work out better, so we don't try that anymore.
So the reason I call them semi-graded is that they make this shift from a single context to dual context. So we can think of dual context as like the omega being present on one context and one being present on the other context. Like, it is not there clearly, but we can think once we have a graded system, we can think it in this way, like there is omega on one context and one on the other context. So in that respect, I am calling them semi-graded, though they are not graded in the current sense, what we understand. Like, I would like when I look at this trajectory, they fall like in between. Maybe they were a step towards this, though it's like connecting the dots looking back.
Okay. Thanks.
Yeah, thanks. I had perhaps a similar comment, but I think I can see what Pritam's saying. It's a sort of like kind of retrospectively seeing it as a kind of a way of attributing as property to the different parts of the context. It's a kind of like, yeah, it's a kind of grading, just not presented in the way we normally see it. Okay, cool. Sorry, go on.
I was just going to say, I mean, I think in the interim between DIL and the graded systems, the number of papers where they had exotically complicated numbers of contexts, where like these are the ones you can use as many times you like, these are the ones you can use once, these are the ones you can use on Thursday, these are the ones and like it's really quite sort of complicated. I think grading has kind of got rid of a lot of those complications, apart from the ordering ones, which are interesting.
So I think it was the paper of I think it was Choudhury had the one where you sort of put it together in the single context, but with a kind of marker on variables. That's like this is a discharge variable. I think they're called like ones that are nonlinear, came from inside of a box, and that's how we took that idea in our kind of approach as well. Okay, well, we're at the coffee break now, so let's take a break and we'll come back at 3:30. And yeah. Okay. Looks like we're arriving back from coffee. Okay, well, I think we can proceed for now. I think people can hear. Okay, so sorry for that delay again. We'll start we have about 7 minutes behind, but okay, we will proceed onwards. So we had non-linear linear logic mentioned in the last talk, which I think will set things up nicely here. So we've got Harley Eades from Augusta University going to talk about mixed graded linear logic. Away you go, Harley.
All right, thanks a lot, Dom, and thanks everyone for being here. And I'm excited to tell you about this project that we've been working on for quite a bit now, and I've probably talked to a couple of you already about this before, but we're now at the stage where we've got most of the work done. So it's pretty exciting to be able to share a little bit about what it is that we've developed. And this is joint work with Tori, Daniel, and Dominic. And it's part of the Gradual project. And I'm at Augusta University in Augusta, Georgia, in the United States. And everyone knows where everyone else there, Tori and Daniel and Dom, are at Kent. So really, this project sort of came out of an idea from way back when I first met Dom. I was doing a lot of work on linear, nonlinear logic by myself and with Blair Kapavia at the time. And when we started talking about graded types and things like that, I was really kind of interested in whether or not you could do something similar to linear, nonlinear logic for graded types. And so what kind of got me thinking about that was is something that I'll talk about first. And so, but I really wanted to introduce linear and nonlinear logic. I didn't know if that would have been introduced already in the workshop. And so maybe I'll do it just kind of slightly quickly so that you can see how I'm, what kind of syntax I'm using and things like that. But this is sort of linear and nonlinear logic in one slide. It has two logics. So there's a logic on the right and kind of making a dot. Can people see my dot okay? Not sure if the people are actually there.
Yeah, I can see that dot. But... Yeah.
All right. So on the right-hand side, we have a mixed linear logic, and it's mixed because we have hypotheses that are considered nonlinear. So in the original LNL logic, it's intuitionistic logic. And so here we have hypotheses that can be copied and discarded. And then we have linear ones. Now, the way that I'm writing this, it looks like we have this separation of context. We have two separate contexts. And that's really just being used as a presentational device that you can really consider this as one context where all of these hypotheses are mixed together. But as a way of speaking about the linear hypotheses and the nonlinear ones, we usually use the syntax to denote which ones are linear and which ones are not. Then on the left-hand side over here, we have nonlinear logic, or in the original was intuitionistic logic. And here we can have, structural rules, weaken, contraction, we can have exchange. And then these two logics are connected by two modal operators. We have on the bottom len. And so what this does is it allows us to take a linear thing and inject it over into the nonlinear fragment by annotating it, saying, hey, I was originally a linear thing. I'm kind of pretending I'm a nonlinear one. And then from the nonlinear fragment, we can go back to the linear one using many. And there it gets annotated with many, saying that I can be used many times. I come from the many worlds over there in nonlinear logic, where we have no rules, right? Or we have lots of rules, I guess. There's more rules, but anyway. We sort of write it in this way. This diagram is from category theory. It's an adjunction diagram, and it says that if you start over in the linear logic world, then I use len to move over into the nonlinear logic one, but then I go immediately back, then I get this modal operator many len, and Benton showed that that actually is the original, of course, modality from linear logic. Sort of its semantics, you use symmetric monodal adjunction to model the logic, okay? So this is linear nonlinear logic, and I actually have some of the rules to show you because I wanted to kind of start with these rules first because I'm going to add stuff, essentially add stuff to them. And so if we kind of have a basis of the originals and kind of go forward with the grading, then you can see kind of how we're adding things together. But I also want to talk about like what kind of got me interested in doing this and some of the questions that I was thinking about at the time. So here I have the left rule actually on the right and the right rule on the left. So this is sort of the left rule and this is the right rule. And this is, so notice that on the sequent, sorry, I have an I and an L. So the I is for intuitionistic and L is for linear. So the len operator says, if you look at the right one, the one to the left, then we can see that what it allows you to do is you have this linear program L, and it's in type A. And everything I do in this this presentation will all be essentially term assignments. So we'll have terms on everything. So we have this program L, it has type A. If it is in the linear world, the L here, but it only has nonlinear hypotheses, then that's when you're allowed to move it over to the nonlinear fragment, and then you adopt those hypotheses there. All right, so now on the left side, we have the left rule. It says, again, so this is now, one thing that's interesting is that the right rule lives in the intuitionistic fragment, but the left rule lives in the linear fragment. And if you look at Benton's original manuscript, he actually goes through a bunch of different iterations of things that went wrong. And I think one of them is where he had them both in the same one and it didn't work. So you have to have sort of them in this way. So this one says, if I have a linear fragment, a linear program, and it depends on a linear variable, then I can move it over to the nonlinear side, but I tag it with L. And then I update, we have to update the variable here to essentially it's elimination, essentially. It's like unlen is like the pattern match for len, or the eliminator. And so that allows us to take a linear, so the thing on the left, the interesting part about it is that it allows us to take a linear thing and move it over to the nonlinear side. And then if you look at many, so here we have the right rule and then the left rule is over here on the sort of bottom. So the right rule, many, which if you kind of remember the rules for Bang, many really reminds me of Bang all the time. So it says if I have a nonlinear program T of type X, then I can move it over to the linear one, but I tag it with many. And again, you start with some nonlinear nonlinear hypotheses, and then they just get thrown into the context there. And then the left rule says it's just basically the opposite. So you start in the linear one and you can move the hypothesis back over. So you end up in the nonlinear side here with many on it. And then we have our pattern matching for many. And so because we're using a term assignment, we add these new variables z to do the left side. In a little bit, I'll show you why it was nice to do it with why we decided to do term assignments for everything, but it comes later when it gets to the meta theories up in there. So you also have another really key feature. So the cool thing about linear and nonlinear logic is that it allows you to program in the linear world and in the nonlinear one without necessarily having to do as much boxing of things up, right? If I just need to program non-linearly, I can do it. If I just need to program linearly, I can. And then I need to mix them, then I can mix them either by using the modal operators, or we actually have mixed rules. And so this is where the name mixed linear logic, excuse me, comes from. So here's an example of that. And this is the left rule for and. So here I have x of type big X, that's nonlinear, and then we inject the and there into the hypotheses on the left side. But you can see that I'm in the linear fragment, and the point is I'm manipulating the nonlinear fragment from within the linear one here, and that's sort of that these mixed rules make using the system really nice, and that's one big. It's a strong property you get from the design, so it's nice. And so now, keeping LNL in mind, so I had that in mind, and now I'm moving over and thinking about grading things, and it really kind of made me think of linear nonlinear logic, kind of hiding in the weeds a little bit. So these are the original rules for graded necessity modality, or just a graded box. And so, for example, here is here's the introduction rule, and then we have the dereliction, and then the elimination rules on the bottom. And so the dereliction rule really got me thinking, because it says I have a linear thing, and then we make it a graded thing by putting a 1 on it. So that tells me that the gamma is actually a mixed context, right? If you look at the syntax of the grammars, you can see this, but I think it kind of hits home here that we actually are mixing graded things and linear things. And so as soon as I saw that mix, I started thinking about the mixed context of linear and nonlinear logic. And then the other rules correspond to just like a graded version of box, and that's not surprising, right? These things all stem originally from bounded linear logic, and so we end up having these rules kind of fitting that. And so then I was really interested, like, could we do a linear nonlinear logic for graded types? Right. And I actually had an explanation already in slides for this. So this is where I was like thinking about thinking about how linear types, or sorry, the linear variable x on this side. So I can kind of like, so on this side, we have the linear one going to nonlinear one here. And it reminded me of this rule where we have the linear hypothesis moving over to the nonlinear world, right? So we have this mixture. It's kind of, I forgot I had these slides kind of written out this way. And then box, right? It looks like a stacked version of lin and many. And that, again, is not super surprising given box's relationship. So, but you start to think like, there's sort of, this is just what got me thinking, I guess, trying to motivate that. And then here, the eliminator for box, right, really looks like, I mentioned that earlier, it reminds me of the eliminator for many. So many, the left, sort of the half of the box really gives us the sort of the structure and the feel of the box. And so if I make a linear nonlinear version, I should see that in our system as well. And so, and we turned out that we do that. And so again, so is there an adjoint decomposition of graded types, right? Graded modal types. So can we do that? That's the big question. And so one little step towards that is we kind of need a result first. So a result has to exist before. And what is that? So Benton did this, right? Linear, nonlinear logic. But where did he suspect that this would work, right? What was the idea? Well, it came from, right, co-monads and category theory. So up at the top here, I have an M on D, and there's a result that says if you have a comonad, you can break it up into an adjunction that looks like this, where D is on the right, and then there's a category on the left. And then there are functors. You can think of the functors as modal operators if you're not familiar with category theory stuff. You have these two functors, F and G, that allow us to go from D over to C and back again. And we get the original comonad, okay? And now I'm being a little bit hand-wavy and just kind of summarizing. So C, you can use the element more category or the co-element more category, for example, to get this adjunction. But that's not really the point I'm trying to make. The point is that there is this sort of semantic results, right, that existed. And then he thought, can we do this for linear logic at the syntactic level? So one question immediately comes is, do we have a similar result for greater necessity modalities? And at the time when I was thinking about this, the answer was no. But then later, Shinya published this paper, a double category theoretic analysis of graded linear exponential comonads. And this actually answers that question. So, and does a whole bunch of other cool stuff too. This is a really cool paper. If you haven't read it, you should, because it's neat. I learned a ton from this paper. And what he shows is that if you have a graded, what I'm going to call graded modality at this point, because it just gets super long to say necessity modality all the time, M, then you can decompose it into an adjunction between C, D, and some C here. But you have to have this action here, 0 dot, where if you start in D and you go to C, and then you add the action. So if you look here, I have the action sort of wrapped around that. So you kind of go around the action, I don't know, like this or something. And then go back, then you get the graded modality that you started with. And so this is that, a similar results in sort of the semantics that corresponds to that similar one that Benton did. And so what we do is take this and do it for the syntactic presentation of it. And it ends up being its model is essentially this, but with a little bit of a cool addition. So that I'll talk about in a little bit. But so that's kind of like the motivation of where I was sort of coming at and thinking about whether this would be interesting and possible. And I think it would be. I think it is super interesting, and it is possible now that we have the actual system developed and all the theorems proven. But so let me sort of introduce. Yeah.
Could I have a quick question about that construction?
Yeah, sure.
Is there a like Eilenberg-Moore like co-algebra category construction that corresponds to? Like
yeah, there is.
Okay. So that's like how I should about this other category as some kind of co-algebras?
Yeah, exactly. The category C there's like a graded Eilenberg-Moore category that of co-algebras that you can use, and it's based on that's fully described in Shinya's paper, so you can take a look at it there. And I'll actually mention it in a little bit because I use it as part of our model, so you'll see it in a little while. Yeah, that was a good question. All right, so yeah, and anybody, you know, it's a workshop, so feel free to ask questions whenever. So now I just want to sort of like give you a tour of mixed graded linear logic. And so I want to start with just the syntax really quick to kind of make sure that I don't you know, introduce things that may be confusing. So everything will be based on an ordered semiring, and so anywhere you see a little r, it's going to be in this semiring R. So so then there's two fragments, right? There's the graded fragment, and those are all look like X's and Y's. And we have a unit, a tensor, and then len, which we saw earlier. And then we have terms. So we have variables, and we have the unit, and then we have the tensor products, and then len. So one thing we don't have on this side is implication, but it turns out we don't need to. And so I'll talk about that again in a little while. But so the graded fragment is pretty simple. It's not super complicated. There's not a lot going on there. So we just essentially, it's just multiplicative linear logic with len. That's really it. So just tensors on len. Okay. So just pausing and let everybody digest for a second. And I always say moving too quick with when I introduce a bunch of syntax. So, and then the other fragment is the mixed linear graded fragment, and that look like A's and B's. Also in the tensors, I use square for the non-graded one, just to kind of make things a little bit different. So again, we just have unit and tensor, but now we have implication, and then we have what we say GRD R. And so here this is the one that's labeled with a grade. And then the terms are everything we had in the graded fragment. So units, tensor, but then we have lambdas in application, and then grade. So we have the grade functor and then the eliminator. So the introduction and elimination form for those. And then we have the elimination form, which I actually, it's going to say ungrade now, but it's supposed to be, I tried to change it to unlen as part of my talk preparation, but we'll just ignore it for now, I guess, since I forgot to do it. I'm sure it's the same everywhere now. It's just going to be ungraded now. But yeah, it's one of those things where you make your talk too quickly, too close to time. So yeah, so basically very simple linear logic with this graded modal operator GRD. And then this is syntax we use, so it's just like LNL models. So the graded fragment is presented this way, where little phi is just a list of grades. So it's just R comma R, and but it has to be the same length as phi, which is just a context. So it's a list of variables, x colon x there, over here. And so the idea is that sort of pointwise related, you know, the first R and phi is the grade for the first thing and big phi. So an example might be like you have R1, R2, and so here R1 is the grade for X1 and R2 is the grade for X2, like that. And it's nice to break them up a little bit. You could just label all of them with the grades, it's fine. But when you do some of the proofs, it's kind of nice to be able to just do operations on the vector of grades. So it can be kind of nice. And then the mixed fragment here, it has the graded formulas with the linear ones. Okay, so right now I don't have an annotation on the dashes because this syntax for the judgments will be the same for our sequent calculus and our natural deduction, but I'll add the sort of annotation saying which one we're in, and when we get into those two systems, but the syntax will look the same. It looks exactly like this, so nothing changes there. All right, so that's the syntax. So we have both a sequent calculus and a natural deduction, and the sequent calculus is GS and MS. So that's what you'll see for graded and for mixed. S for sequence. So I thought I'd show you some of the rules. So here we have the left rule on the left this time, which I thought was a better idea than having it on the opposite side. So we have the left rule and the right rule for tensor. So not too surprising. So this is the graded fragment. So GS here. And so we have X colon X and Y colon Y. So here they both have the same grade. And if they do, then we can tensor them and give them an R there. And then what we do is we pattern match on Z. And then tensoring is the right rule is basically the same as you might expect. So you have T1 of type X, T2 of type Y. You can put them in a pair and you get their tensor together. The grades and the context just come together. So nothing too surprising there. All right. And then, so some more examples. So the cut rule, so we have the cut rule sort of embodies graded substitution, right? And so when you do a substitution in graded types, so we're going to have T1 and then X could be free in T2 here. And that could be used, if we think about numbers, for example, it could be used like R1 times. And then when I do the substitution or the cut, then I have to multiply the grades for T1 by an R1 because T1 is now could potentially be duplicated up to R1 times. And so we see the multiplication there. So if you're familiar with substitution, this really wouldn't be surprising, but it's nice to know that our cut is right in line with that. And then we have len, which is pretty much exactly like, it is the exact same thing as the one from LNL logic. So if you have just graded assumptions, then you can, from the mixed fragment, then you can move it into the graded one, but we just have to put len on it, right? To say we came from the linear fragment. So nothing really surprising there. So here's, I guess, a lot on one slide, but we have the tensor rules. And so I'm not going to step through maybe every single one, but I just was, the top two, right, are the standard ones from linear logic. There's nothing really, anything going on. It's just standard linear logic. The graded stuff just follows along. We don't do any manipulation there. The bottom one, tensor, the left rule for the mixed one is you do the same thing as we did in the graded fragment, but now we're in the mixed one. So we can do, we have our mixed rules that we have from linear and nonlinear logic in the same way, but now there's the graded versions of those. And then we have the cut rule for linear logic up here, so nothing different. But then we also have, so one thing you have in LNL as well as this one is you have a mixed cut, which I think is really cool. You can take a nonlinear program and you can compose it with a linear one, as long as you have the right assumptions, right, that matches up. And so you can have this mixed, sort of like a mixed composition. So it's a mixed cut. Here we call it G cut for graded cut. And so that's another one of those mixtures that's pretty neat about linear and nonlinear logic. And then we have the left rules for len, which allows us to inject the len on the left, and then we use its eliminator here. And again, the rule is exactly like the rule there. Sorry, this is supposed to be a 1 here. The only thing is that when we move this linear one over to the nonlinear fragment, we have to put a 1 on for its grade. And that's where that dereliction rule that I mentioned earlier in the presentation, it matches up with this rule, right? It's exactly the same thing. We have a linear thing, we move it over and grade it with a 1, but now we say we came from the linear world. Okay, so that's where that dereliction rule is showing up that I mentioned earlier. Then we have right rules and left rules for GRD, and this matches exactly up with the box like I was talking about earlier. So looking at the right rule, if I'm in GS, I get to move into MS, right? And I have T of type X, then I can grade it, right? But I have to multiply its assumptions, all of the graded assumptions by R. And so that's that promotion rule. And then the elimination rule is on the left rule. So we have X of type graded R. We can move this assumption over to the linear one, but we have to grade it with an X, and then we pattern match. We pattern match on that. And so what this is showing is that the rules that really look like the rules for the box are really coming from the left rule of Lin and the left and right rules for L and R. And so when we go around the bend to build that graded modality, these are the rules that are really coming into play to give us the structure of the box rules that we saw earlier. So it's kind of the point I was trying to make with that. So that's the sequence calculus. Now we have some meta theory that we've proven. So first off, box can be derived. So I hope that's the case. So this is what this limit says. You don't have to worry about reading every detail, but you can see that that here I'm eliminating box against R and X. And then over here, we're putting box on. And here I wrote box in these places, but it's really, these things are equal. So it's the same thing. I just wrote it there to kind of give you intuition. And so we do get the original rules out in the system. You can prove those, just straightforward derivations. You can also, so what this result's about is, remember, we do not have a graded implication in the Grady fragment. One thing that Paul Andre MIS showed is that if you have an LNL model and you don't have implication in the intuitionistic fragment, then you can define it in the mixed fragment. And he also, I think he embedded same-place-like lambda calculus into it and all these things. So here we show that you can derive graded implication in the mixed fragment as well. If that's something that someone would want to have. You can also add it to the graded side as well. That's not going to hurt anything, but you can also derive it. And then we've proven cut elimination. So we don't have to worry about necessarily reading this entire thing or anything, but the property here is that we did prove that cut elimination holds. So that's great. Tori has been working on that tirelessly. And another really cool one that Tori did was she proved the self-formula property for this calculus. And those are the main results that we proved about the sequence calculus.
Sorry, Harley, I think we might be sort of out of time now. So if you could wrap up, then that'd be awesome.
Oh, really? I guess my thing says I've only been presenting for 11 minutes.
Yeah, it's been 30. You had a question in the middle.
Oh, my thing is all right. Okay, right. Yeah, I guess I just kept talking and zoned out. I guess it's actually just saying that. Yeah. So I think my timing thing's messed up.
No worries.
All right. Yeah. Sorry. Yeah. So there is a natural deduction system, so I can just skip it. It's fine. What's cool about it is that some of the rules get a little bit simpler. And then the natural deduction system, we've proven substitution for it as well. And then we've proven that if you can prove something in the sequence calculus, you can prove it in the natural deduction system. And what's cool about these results is that the terms are the same. And so they're not different at all. I was kind of careful at designing the terms so that this would sort of work out. And so that tells us also that the model for the natural deduction system is the same model as the one for the sequence calculus. And we kind of get that based off this, so we don't have to go through and prove it again. So this is just showing that the natural deduction system embeds into the sequence calculus. And again, the terms don't change. And then we have a model, just 1 point, and then I'm seriously done. 1 point. So the model is really, really cool because it's based off Shinya's paper. So, but what's neat about it is instead of just some arbitrary junction, we have you can say that it's an LNL model on top of that graded coalgebras that we're talking about earlier. And then we define, instead of taking an action, we define it in the same way that you do for the graded coalgebras. And sort of, so that's really neat because you can see the word in the semantics, you see it's L and L logic with mechanisms for adding the grading. And that's exactly what one of the main points of Shinya's paper was. So that's really cool. And that's it. So in a nutshell.
Right, let's thank our speaker.
Yeah, sorry.
Maybe while Bob sets up, we can take a quick question. I think Bob is next.
Yeah, I think Bob is next one.
Harley unshares.
Any questions?
So does the correspondence between sequent calculus and the natural deduction system mean that the cut elimination result for sequent calculus gives you some kind of a normalization for the natural deduction system, or?
So we didn't prove that. So we were just we proved that basically if you have a derivation in one, then you have a derivation in the other. And the term witnessing the derivation from the first one is the same term that witnesses the derivation in the second one. And really what I didn't want to have to do was to have to, take, and what we did was we proved that the sequent calculus can be modeled by the categorical model. And we wanted to be sure that without having to necessarily do the entire proof again, that the natural deduction system lands in the same place. And so knowing that the derivations are preserved and then the terms witnessing the derivations are the same means that they would be interpreted exactly the same into the model for each system.
All right, thank you for the question. Okay, so we're going to switch to our short talks now. We should thank, do we thank our speaker again for the last round? Let's do that. Sorry, I think I forgot to do that before as well for Pritam, so we should give an extra clap for Pritam as well. Okay, Bob.
Yeah.
Are you talking, Bob? It says you're unmuted, but we don't hear you.
Hello?
Yep.
Hi.
And then moving over. So Bob is going to be, Bob Atkey from Strathclyde is going to be talking about unifying models of linear and graded dependent types, linear/graded dependent types.
Hang on, can people see this? Zoom is being a bit weird about, I want to just share part of my...
We can't see it. It says it started screen sharing, but there's nothing.
Okay. Right. Thank you. This is going to be a quick 10-minute talk. There's two ways to give talks. There's the sort of nice, well-prepared ones we've seen so far, kind of the way I do it. So this is going to be a really quick talk about some ideas I've had for unifying. I'll show the problem on the next slide. The problem is this. So there are many, many different ways of combining linear types and dependent types, or more generally, dependent types with kind of intentional information, which I mean quite broadly here. So I guess, Pritam already showed some of this in his talk, but I'm going to be a bit more expansive here. So I think maybe the first one to actually write something down was Matthias Barker in 2014. This linear dependent types system, which had this split context idea. And then I think the work was probably done concurrently, but then there was a system by Neil Krishnaswamy and others in 2015. And then Connor saw that and went, no, and came up with a system that's broken, and I fixed it with semantics. And then not long after that, there was this linear dependent type theory for quantum programming languages, which is actually a bit more general than the name of the paper title implies. It's more general. And then locally, the graded modal dependent type theory, the graded dependent type system. And then there's these other ones, which are kind of side thing to this kind of linear progression, or linear things. The kind of ideas of parametric quantifiers, which is upgrading a type system, a type theory with how sensitive, roughly speaking, a term is to kind of variations in its inputs, like in a kind of synthetic sense. So what does this mean? So the parametric quantifiers are things like this term, this preserves all relations between the types you put in. So it's a way of talking about that. And then that work led to this multimodal type theory, which is a very general way of talking about modal type theories. And then more recently, this has been this dependent dependency calculus, which is another kind of marries two of these kind of things together in a certain way.
Bob, could you stay nearer to the microphone
Sorry,
for us? Yeah, that's right.
What's really going on? So my conjecture is that, well, there's kind of three things happening. So one is the kind of linearity versus dependency. So there's a kind of this syntactic problem you run into where you sort of say, I'm not going to use X twice, and then you write down some dependent program, and then you inevitably use X twice, and then you feel bad, and you try to fix it. But my feeling, what I'm going to get to, is that mentioning a variable in a type, and by specifically in a type, I mean as a kind of specification you're trying to attain, does not count as a use. There are other mentions which are when you're constructing a witness for the type. But my contention here is that specifications cannot consume resources. They are not part of the program. There's also the intentional information used for specification. So this is things like productivity. This is like how far does this function look into the stream in order to, so you can do things like write productive co-recursive programs. There's things like information flow, tracking, parametricity. And these are important because they affect the kind of programs you can write in a kind of semantic sense. So they change the programs you can write. And then there's the intentional information used in runtime properties, which I think is related but different thing. And it's very easy to combine 2 and 3 and sort of see them as similar things. So this is things like resource usage, erasure at runtime, sub-Turing implementabilities, like you can implement it polynomial time or something like that. So I think there's these 3 separate things. So in QTT, we sort of pretend that you can interleave the linearity and dependency. So I'd say this is actually a complete illusion of what's going on here. So you have these typing judgments like this, where things are annotated with grades. And then at the end, there's this weird thing, which is that the final thing is annotated with a 1 or a 0. And the 1 means it sort of happens at runtime, and the 0 means it's going to happen at type time. Really, if you kind of look at the rules, you can write them out as 2 sort of separate type systems. Like really, it's a syntactic trick to make you think there's 1 type system. Really, there's 2 of them. And what happens in the semantics, every type effectively has 2 parts. There's a specification part, which is basically normal type theory. And then there's a linear part, which tells you what the implementations are. This is what happens in the semantics. And my contention is this is basically the only way of doing it. There's a separate thing between the semantic, there's a specification part, which is going to be some type theory, and then there's a linear part, which is linear type theory. Anyway, the trick is that only the specification part matters for dependency. So it looks like you can depend on linear things, but you can't. You can only depend on the specification part of the world, and you can just forget the linear stuff. You can't depend on linear stuff. So these split context systems, so the Varka and Kishmatani, they have an explicit separation of specification types, things that happen on the left of the divided line, and the implementation types happen on the right. And my conjecture is that QTT can just be very easily translated into the system by pairing up these 2 contexts. So you take the A1 and the X1, that's your first QTT type. Take the A2 and the X2, that's your second one. And the dependencies can only happen on the upper parts, so like the A1 and the A's. And this captures everything. And also, I think you can translate back into QTT as well, in terms of additions. Also, I reckon that graded modal dependent type theory, so the Kent one, grad, the depend one, both push out from Augusta, can both be also translated into this split context subsystem. So you might ask, well, how does this account for the uses of the types? I think if you have a universe, and then you consider that you're building the type in the universe which may consume resources in itself. So you're building the type as a term. But then what you do to actually treat that as a real type is convert that into one of these specification types, which is a separate thing. So my conjecture is that all linear dependent type theories are a mode of use of split context type theories. They're all basically probably useful and good and won't blow your weirdness budget, as Edwin put it, but they're a mode of use of split context theories. So that means that they can have a unified semantics in terms of indexed symmetric monoidal closed categories, or possibly indexed graded multi-categories, whatever they are, as long as you have a bit of extra structure. So the C is going to be a category of families, so that means it's basically a model of the type theory by itself, and you need a kind of thrall quantifier as well to make it work. And then essentially, again, warning, categorical just coming up. QCT is just the Grothendieck construction applied to one of these things, as long as every category you get from L is thin, in the sense there's a notable relation between them. And I hope this will be enough. So really what this is saying is that QTT is essentially a form of abstract realizability. This L is saying it's possible to get from X to Y. Looking at it this way, one interesting thing is the G constructor of Krishna et al. So that's like the dependent type version of the G from linear nonlinear logic, is a missing notion from QTT, which is a kind of notion of reflection, which allows you to take linear things and turn them into specification things, to say that assert that this thing is actually implemented. And there's other ways of saying it, monoidal vibrations to things. So I'm just going to end here, do these translations that actually work. So I haven't actually done the work yet. This is conjecture. Can we reason about the intentional information implementation? So one way of looking at QTT is all it does at the moment is stop you writing things. As soon as you put grades to Arndt Omega on your in your context, then you can just strictly write fewer things, and you literally get nothing for it inside the type theory. So you have to either be one of those type theorists who just enjoys not writing things, or one of those type theorists that compiles their programs. But if you're one of those type theorists who wants to write more things, but doesn't actually want to run things, then what logical properties do we get from knowing something about the implementations? And what I also want to do is, how do you systematically create systems that combine the intention information at the type level with the runtime information? So what I'm thinking of here is particularly the dependent dependency calculus, which mixes in erasure, which is a kind of runtime property, with compile time irrelevance, which is a compile time. So my conjecture is that multimodal type theory will work well for this in the place of the C part here. Okay, that's it. I think I'm in time.
Yes, thank you, Rob. Right, let's take some questions.
Hey,
go ahead.
Yeah, thanks. I was just wondering if you'd looked at all at the relationship to this and Sterling's pre-sheaf semantics for well, for information flow, for instance, which seems to relate a lot to a lot of this.
Yeah, so I think that's, sorry, the question was, have you looked at this in relationship to John Sterling's pre-sheaf semantics, or sheaf semantics for information flow? And that is another thing, yes, I want to look at, that I think relates to this thing about this part 3 of the question here is like, so, I mean, that's still a model of type theory, because it's a sheaf semantics, but it's, and it allows you more intentional information. The question is how to marry that with a kind of runtime interpretation. So at the moment, compiling a system like that is that there's some kind of program extraction going on, which sort of, in a sense, tells you a realizability semantics. What QTT does, and what the other systems do, is specifying the runtime is that the programmer is allowed to control that realizability. So I think, yeah, John's stuff's really cool, and it'd be nice to use that in the place of the C or the stuff to the left of the divider. Sorry if that's not very clear. I would like to be more precise if I haven't done the work.
All right, Max has a question here as well.
Yeah, so this semantics, you're where you do it as an index category over a category with families. Is that basically the same idea as what the homotopy type theory people call a two-level type theory, where you have like one type theory for reasoning about terms of an embedded type theory, essentially?
It might be similar to start with, but this one's significantly weaker in the kind of internal one, right? It's just a symmetric modal category.
Right, yeah, but that's what I'm saying is like there you just say maybe have two dependent type theory, like a dependent type theory over a dependent type theory, and here instead the inner type theory is linear type theory.
Yes.
Okay. Okay, because I'm doing something like that. Yeah, but with double categories. Cool.
Sorry, Max has just said something.
Oh, I said I was doing something with that, but with double categories instead of linear logic.
Sorry, and then there's a question in the room.
Yeah, so yes, where they quote, linear type theories which are parametricity. But then there's this thing where we should be able to prove more internal theories purely based on, for example, knowing that we cannot duplicate things. Do you have any chance of the relationship of those two or some?
Yes, we should, yes.
So, anything that you can share that you...
Right, so this is, yeah, so the question is like, we should be able to derive properties from the linearity. Like, so for instance, just to add it, if you have a linear function from list to list, then it could only get permutation. And yeah, this is what I would like to do in number 2. Like this is, right, so can we reason about the intention information and input data? If you know the implementation doesn't never duplicates anything, then it should be, you should be able to derive that property. Yeah, so we know how to do that for simple types, but then it's a kind of meta property. How do we do it internally within the type?
Okay, thanks very much. Let's thank Bob again. And our next short speaker is Max, I think. Oh, I've lost the schedule. It's Max, yeah, great. Okay, so if Max can share screen.
Like that?
Yeah, that looks cool.
Cool. Okay.
Okay, I think we're all good then. Great. So we've got Max New from the University of Michigan, going to be talking about some work that's joint with some fine people that you can see also on this slide. Gradual typing for effect handlers.
Yeah, thanks. So, yeah, like you said, I've been working on this for a while now. Now I'm at University of Michigan as of almost a year ago now, working with my student Eric Giovannini, and then previously with Dan Licata at Wesleyan. And so, so the idea here is that we're going to extend gradual typing for algebraic effects and handlers. And so first I want to go over the basic idea of what gradual typing is. And the idea of gradual typing is we want to be able to support basically 2 different languages. One that's we typically think of as a dynamically typed language, like say JavaScript, and we want to migrate to a typed language. So in that case, TypeScript. And the key is that we want this process to be simple in that the typed language is pretty similar to the untyped language that we use, and we can add types to dynamically typed programs as they're written. And that we can do it gradually over time. So we don't have to migrate everything all at once before we can run the type programs, like we would if we were just to rewrite it in a completely new language, and that we want to gradually accumulate the benefits of typing over time. Okay, and so I'd say the most famous, the most well-developed example of this from academia is going from Racket, which is like a version of Scheme, to typed Racket, and that's kind of the model that I'll be following here. And so the question that we've been facing is, what if we took a language like OCaml that we don't think of as a dynamically typed language, but we could think of it as one where effect typing is very imprecise. So for example, in OCaml, exceptions are not tracked by the type system, for example, right? And so what do we think about a language where we have effects and handlers where they're untracked like OCaml, and we could use gradual typing to help you to have a smooth way to integrate effect typing. Okay.
Max, could you just move the Zoom thing in the bottom right? It sort of seems to be, yeah, my face is over the top of everything.
There you go. Yeah, so we're going to move from the red imprecise world to the precise world gradually over time. And so the main goals of this are that it's gradual. So here on the left, think of this as we have like 3 modules written in our untyped language or imprecisely typed language. And the point is we'd like to be able to migrate. Eventually, maybe we're going to get over here to a fully typed program, but we want to be able to do it 1 module at a time. And when I add types to one module, like say here, I added types to module T2, then I should not have to add types to the untyped modules that interact with it. That should be, I should still be able to run the programs, and simultaneously, I should still be able to trust this typing information in the type module. One of the important properties that we want in any gradual type system is this property called graduality, which is that when you do rewrite a program like this, so you go from a more imprecise version, a less typed version, to a more typed version, then we want that there is a refinement of the runtime behavior. So essentially they do the same thing unless the more strict typing that I have over here catches a bug, either at compile time because the static typing has become more strict, or at runtime from more strict type enforcement at these boundaries. Okay. And the typing part of gradual typing is that we want the types to always be sound, even when we're in these mixed programs. So when you write in a typed module, you get to reason about the types just as if you were in a fully typed language. And so, for example, with lambda calculus, you know, we start out in an imprecise world. We don't really have any eta equality principles, but when we move to simply typed lambda calculus, say, then when I have something of a function type, then I get an eta principle. This, of course, is the lazy eta principle. You need a different one for call by value. But so we get that we want a gradual accumulation of the type reasoning principles from our gradual static discipline that we accumulate. Okay, so for gradual effects, these are our 3 big main goals. First, we want to design a syntax that combines these 2 together. We want to show that we gradually accumulate these equational reasoning principles, and we want to have this nice graduality property. And I developed a kind of semantic methodology for designing these languages in my PhD thesis, so that we get these equational reasoning principles and satisfy graduality. And the basic idea there was for dynamic typing, we model the dynamic type as a universal type. Think like Dana Scott's universal domain from domain theory for interpreting untyped lambda calculus. And then we have to insert casts at the boundary between dynamic and Segli type programs. And the key property for graduality to hold is that these casts have to be embedding projection pairs, which is a kind of slightly stronger than a Galois connection. Okay, so how are we going to adapt this methodology to effect typing? Well, for gradual effect methodology, we want, instead of a universal type, we want some kind of universal monad. So our effects are all going to be associated to some monad, and so our imprecise effects should be some kind of universal monad. And then the casts are not between just types, but now they're some kind of monad morphisms between the monads. And that's really the intuition that I had behind this design, if not the actual technical details. Okay, so here's some basic idea of the syntax. So first, let me fix a sketch of some of the syntax for the actual language with effects and handlers. So the first key thing is that in this language, you have effect declarations in the language. So you declare, okay, there's a new effect called flip that takes in a unit type and returns to you a Boolean. You can print a string and you get out nothing, and you might have exit effect where you provide it 1, you get back 0. And then if something is in the signature, then you can raise it. So you write it as a raise, and then the name of the effect, and then what the input type is. So with flip, you give it 1, you give it a unit. With print, you give it a string, etc. And then it's typed to have the output that the signature says. And then those effects are raised up through the stack, and they're handled by some ambient handler, which are written something like this, where you say, okay, I'm going to handle this current expression, just like I might handle an exception. And you have one clause that says what happens if m just returns a value, it doesn't raise any effects. And then you have, for each of the effect operations that you want to handle, you say, for that operation, give me the thing that it raised, and then provide me a continuation that accepts the desired, the thing that is in the desired output type. So that's this over here. Okay. And so, yeah, so the way that the reduction actually happens is when you raise an effect operation, you search for the closest enclosing handler, and you that's handling that effect, and you run that clause of that handler in, where the kind of payload of that effect is substituted for X, and then the continuation K becomes this captured evaluation context E, with the handler still around. So that's deep handlers. There's also shallow handlers, which don't capture the handle, and we actually do both. It doesn't make much of a difference for gradual typing. Okay, and so the effect type system looks something like this. We have a kind of graded monadic looking type system. So you have a value type in addition to an effect type, which I call sigma here. And so for the static effect system, you can say, okay, that these effect types are essentially, you have a set of the effect names that have been declared earlier in the signature. And so, for example, when you raise an effect epsilon, you look it up in the signature and you see what the input, which I call a request, and output and a response are, and you make sure that this value, this m here has the type of the request. And then this will raise an epsilon here. And then the output will be the response type. Okay. And like I said, this gives you a kind of semilattice graded monadic type system. So like this is, so when you have a value, you have a return, which has no effects. And then when you do a bind, you can think of that as joining them together. and there's a kind of sub effect rule as well. Okay. Yeah, and then this is just ordinary graded effect stuff. Okay, and so the basic idea is that there should be a sub language with dynamic effects, which is going to be equivalent to the language with no effect tracking whatsoever. So the idea is we add this dynamic effect type question mark, and as special rules, everything is going to work where if you have dynamic everywhere. Okay, and so this is essentially equivalent to one where there's no effect system. So it's like uni effect, you could think. Okay, and then the main thing that we want to figure out is how to define these tasks. And so the idea is that you have this dynamic module and static module interacting, and you can when you export from one module, like this module exports F, then you might want to import that into a statically typed module, and you will provide a new type to it that's more precise. But you can also vice versa import statically typed functions into the more dynamically typed. So in this case, static precise effects into the untracked effects. Okay, and so we need functions both ways. Okay, and so first of all, we define what it means for one type to be more precise than another. And it's actually very simple. It's just everything is basically a congruence with respect to this ordering. So we have a type precision relation and what we call an effect precision relation. And the main idea is that the dynamic effect is the most imprecise type. And then the other one here is, this one is a kind of depth precision rule. So it says, if I have two effect types that are epsilon takes A epsilon to B epsilons, and then this other one takes A epsilon primes to B epsilon primes, then I just check point-wise that those are related. And then that would say that this one is more imprecise than this one, basically if all the request and response types are more precise. Okay, and from these two ordering relations, we get a pair of casts, what I call an upcast and a downcast. So when A is more precise than B, we get both an upcast from A to B and a downcast from B to A. And we also get, when we have an effect ordering, sigma more precise than sigma prime, we get an upcast of effect types, which changes the effect type only, and a downcast of effect types, which changes the effect type only. Okay, so whereas normal gradual typing, we just have this stuff. Now with the effect typing, we also have this stuff on the right. And then the simple idea of the semantics is that each of these terms M that has an effect type sigma and value type A is going to be interpreted as an element of some monad T sigma A, right? Where, so this is a kind of graded monad, right? And so the basic idea is it's like a free monad. So we say that this computation tree T sigma A is either I'm returning an A or I'm raising a particular effect. And to raise, I need to provide you with the request R, and I need to provide with you for you a continuation for the response S. And then we also need to throw in that we always can have divergence and error as well. And then the dynamic type is just interpreted as the kind of universal monad where we take all of the effects that have been declared in the program and assign the request and the response types the kind of most dynamic version of them that's available in the program. And then we needed to, and then to define the semantics, what we need to do is whenever we have this ordering on effect types, we need to define embedding projection pairs, which in this case are embedding projection pairs of monad morphisms between the corresponding monads. And so we have, it basically comes down to two types of rules. One is the width precision rule, which is you know, where I have on the right-hand side, more effects are raised. On this side, more effects are possibly raised. On this side, fewer effects are possibly raised. And so the injection here is easy because this is essentially a subset of this. And the projection is the one where we can actually error. So we say, if you raise one of the effects that's no longer in sigma, then you'll have to crash. And this is basically a generalization of, embedding projection pair you can define between A1 and A1 plus A2 for any A2. And then the other one that we need for effect typing is what we call depth precision, which would be basically we have two effect types where we have all of the same effects, but the ones on the left are more precise. And so we end up with, all the requests on one side are more precise than the requests on the other. And so this just comes from a functorial lifting of all of the casts. Okay, and so everything works out quite nicely, and these all end up being embedding projection pairs.
I'm afraid you're out of time, Max.
Okay. Sorry. Like 15 minutes?
Yeah. Yeah.
Okay, yeah.
If you could wrap up, that'd be great.
Yeah. So so this was all kind of, we've done this all using operational semantics, but I'd really like to figure out how to relate this more to things like graded effects. So in the past, when we did this for call by name, we basically said that we had to go from a Cartesian closed category to Cartesian closed double category, where this double category was this precision ordering. So I'm very curious if we could model this by saying, oh, we have a graded monad is our static system where we have some kind of lax functor from some grading category. If maybe we can explain this as something similar using graded double monads or something like that. I don't quite understand. But yeah, okay, thank you.
Cool, let's thank Max. I think we might have to take questions offline there. I do have questions, but I guess I'll just email you, Max.
Okay.
Thanks very much for that. We're gonna I slightly flipped things over in the schedule, so Jack's gonna go now because Jack is online, and that'll mean less shenanigans with the laptops. So Jack, are you okay to share there?
All good. Let me just check it works. Is that okay?
Yeah. Okay. So Jack is going to talk about program synthesis with linear and graded types. Thanks, Jack.
Okay. Yeah, thank you very much. I'm Jack. I'm one of Dominic's PhD students, and I'm going to be talking today about my work in this program synthesis context. So I think the best thing to do is just to jump straight in with a demonstration in Gradual of a tool we've been working on of program synthesis. So Gradual, for those of you, hopefully many of you are aware by now, but it's a language that combines a linear type system at its core with, well, just check. Okay, sorry. It's just wondering if I'm audible. Hopefully I am.
Yeah, we can hear you. I think they're okay in the room as well.
Okay, cool. Yeah, so it combines linear type system at its core with graded modal types and index data types. So now let's switch over to a code editor. So here we have two kind of very standard non-linear functions, drop and copy. So they're both non-linear in different ways. Drop goes from something of type A to the unit type. Copy goes from something of type A to a pair of A's. So I have these two holes here, and what I can try and do is synthesize an implementation for both of them. But I'm not able to do that because at its core, Gradual uses a linear type system. And in fact, these two types are both uninhabited linearly. But what I can do is I can augment them and give a more accurate description of the behavior I want by using a graded modality. So I use this box syntax in the type, and I say I want to use A 0 times. And likewise for copy, I want to use A twice. And then what I can do is I can hit this key combination on the whole, and I can synthesize an implementation for drop, which pattern matches on the graded modality, to give us y, which we can then discard because we've said we're going to use it 0 times. Likewise for copy, I can do the same, and I can get a pair of y's. So program synthesis in this setting is quite useful because our types become quite descriptive of the behavior that we want. And not only are they descriptive in that we don't need additional specifications such as examples or constraints, but it also means that the number of inhabitants is very constrained. In fact, for drop and copy, there is only one inhabitant for both of these types. So this becomes quite powerful when we want to do things like define library functions. For example, I'll skip these ones here, and say we have a maybe data type, and we want to write some like very kind of standard library functions for it, which are quite routine. But since we know the types already, it'd be quite nice if we could get the implementation for free. So what we can do is we can synthesize the bind, we can synthesize the return, and then we might have some useful auxiliary functions like from maybe, which takes something, an a, which we can use 0 to 1 times. This is what this interval modality here means. And we take a maybe of something. And then if we have a just of something, then we use this. Otherwise, we use a, which we can use 0 to 1 times. So all of these we can synthesize, which is quite nice because otherwise we'd have to write out all these functions by themselves. So what I'll do now is I'm going to explain quickly how this works and some of the issues involved in this. So I mentioned that this is type-directed synthesis, and this is analogous to a proof search in a corresponding logic. So this is a style of backwards proof search, which means that we have some goal, and what we want to do is break this goal down into sub-goals and then solve these sub-goals to get our eventual program. But we have a bit of a problem here. Sorry, I think my slides are slightly out of order. I do apologize. Here we go. Yes, so here, for example, is our rule for synthesizing pair introductions, which is kind of a crucial rule to exemplify the problems we're going to face here. So from some context gamma, we want to synthesize A paired with B. We want to get some term out of this. Well, how do we do this? First, we need to synthesize the A, and we need to synthesize the B after this. So we want to pass some part of gamma into T1 to synthesize into the first premise to synthesize T1, which uses the resources from gamma correctly to synthesize this term. And then we want to pass the rest of gamma, which is gamma 2, into the second premise to synthesize T2 from B. And then at the end of the day, we want gamma 1 and gamma 2 to be some way of splitting the original gamma such that the resources are distributed among the premises that they're used correctly. So we might want to make sure that we don't like misuse a linear thing in each of these premises. We don't want to use it, for example, a linear variable in both T1 and T2, because this would violate linearity. Likewise, we don't want to use a graded thing such that we like overuse its grade or we underuse it. So we have to be a bit careful in how we split gamma here. But this way of splitting things isn't quite clear to us. It's non-deterministic at the point of this conclusion here. So how do we do this? We have to be careful. This is known as a resource management problem. How do we distribute the resources that we have available to us such that we can correctly construct a program that uses those resources? So for our tool here that I just showed, we implemented 2 approaches based on a model defined by Hodes and Miller in the 90s for linear logic proof search. So we call their approach the subtractive resource management approach, and we'll see why in a moment. But what we did was we adapted it from linear things to include graded things, and we present its kind of counterpart, the additive resource management mode. And we'll see how both of these work momentarily. But basically what they do is so here they introduced this synthesis judgment. From some context gamma, we have a type A, which we want to synthesize a term T from. In addition to this, we introduce some context delta, which, depending on our resource management scheme, contains different things, but it describes how we use things in gamma. So in subtractive resource management, the original Hoderson-Miller approach, how this works is that delta describes what was used in synthesis. It describes what we have left over after synthesizing a term. So for the first premise to synthesize this pair here of A and B, we want to get T1 and T2. We pass for the first premise to synthesize the A, the entire context gamma. We get back some output context delta 1, which describes what we have left over after synthesizing T1, what we didn't use. So we then pass this into the second premise to use as our basis for synthesizing T2 from type B. So then delta 2 is the result of this. It contains everything that we didn't use to synthesize T2. And delta 2 then just becomes the output context for the final conclusion of the rule. Nice little arrow there. I won't go through the example in the name of time, but then the counterpart to this is additive resource management, which instead of describing what we have left over after synthesizing something, delta 1 here describes exactly what we used to synthesize something. So in contrast to before, we pass gamma to both the premises in the synthesis of a pair. So we have A pair B, and now we want to synthesize an A using the entirety of gamma, get T1 out of this, and some context delta 1, which has what we use to synthesize T1. Likewise, we pass gamma to the second premise and synthesize T2 from type B, and then get another output context delta 2, which contains what we used. And then for the conclusion of the rule, what we do is we simply take the context addition of delta 1 and delta 2. So this addition that is defined here is it's a partial operation, which is only defined on things which are disjoint in their linear assumptions. So if we use the same linear assumption in delta 1 and we used it again in delta 2, then this addition fails. And what happens is the branch of synthesis terminates and we try something else. So for graded things as well, if we have a graded assumption that we used in for T1 and we also used it for T2 for the addition of delta 1 and delta 2, we simply take the semi-ring addition of the grades, because these grades are drawn from pre-ordered semi-rings. So what we did was we implemented both of these approaches, as well as a hybrid approach between these two called additive pruning, which I probably won't go into further here, but we did a little bit of an evaluation between them. And oh, my evaluation slide is gone, but essentially, sorry, the slides are a bit messed up. But what we found was that the additive vastly outperforms the subtractive in most cases. So the reason for this is, as the name implies, subtractive is it has to do some kind of subtraction, because you need to work out what you used and what you have left over after synthesizing something. And this implies subtraction, which, because we're in the context of semi-rings, we don't necessarily have a notion of an additive inverse. So we have to define the subtraction in terms of generating constraints on variables, which involves a lot of nested existential quantification and constraints that gets discharged via an SMT solver, which can become quite long chains of things that take a lot of time to resolve. And it all can become quite intense, as opposed to the additive, which also requires constraints to be generated. But these constraints are a lot simpler and a lot more easy to solve. So yeah, we found that additive is actually in general a lot more, a lot better. So that is essentially what we ended up deciding would be the most preferable implementation for this. Additive pruning takes the notion of subtraction from the subtractive approach and uses this to, instead of passing the same context to both the premises in the additive, we simply pass gamma minus delta 1 in this premise here. So we also do a subtraction here, but minus the things that we know we can't use because we've already used them in the first premise. And in some cases, this turns out better. I do apologize. I had a slide here containing my evaluation, but I'm not sure where it's gone. But instead of that, in lieu of that, we'll look at some extra examples that we have of synthesis. So we can also synthesize more complex things, such as a map function, which takes a list of things, a function from A to B, which we can use an unrestricted number of times, and in return, we get a list of Bs. So this hint here inside the whole implies that this T is just saying that we don't have a time limit, and this R says we're allowed to use recursive function definitions. So if I try and synthesize an implementation for this, oh, couldn't retrieve a position. Yep, what we get is for the cons case, we just unbox the function that we want to use, the A to B. We apply this on the U that we obtain from pattern matching on the head of the list. And then for the recursive call, we pass in map, which we're allowed to use from the dash R hint, and rebox the Z, and that's all well and good. So map here is because it's a top level definition, we're allowed to use it non-linearly, although we do use it linearly in this case. And for the other case, we just return empty. And then for a more complex example, we have stutter, which is something where we have a list of A's, which we have to use each A in the list twice, and we want to get out of it a list of A's. Well, what's going to be the implementation here is that we pattern match on the list. We get this Y, which is the A boxed with 2 here, and A we have to use twice. We pattern match on it. This gives us the ability to use the U according to this modality here, the 2. And then we just cons 2 U's onto the recursive call of stutter on the tail of the list. And then for the empty case, we just return empty. Yeah, so this shows that synthesis is something that is quite useful in the context of graded modal types because the tapes are very expressive. And because they're expressive, not only does it mean that we're more likely to get the implementation that we want, it also means that there's going to be fewer inhabitants. But there are considerations, as I mentioned, to do with the resource management.
All right, I think we better stop there, Jack.
Okay, thank you.
Very much. So Jack has a cool paper about that, which you can check out online. There, got the his website. I think we're out of time for that. Again, we'll have to take the questions offline there, but thank you very much, Jack. Daniel is next, I believe. So if Daniel wants to set up, we could probably get a question in while Daniel sets up, maybe. An attempt to do that. Maybe the online people can ask a question. That would probably work. Yeah. Any questions while Daniel sets up?
Echo. If it weren't echoing, I'd ask a question. Okay, so with the additive scheme, it kind of looks like it's got a few sort of nice symmetry things about it. For example, well, it's symmetric in the sense that it doesn't matter which order you do the two halves of the product, right? And presumably like parallelizable in a sense. Do those kind of aspects give you any benefit, or
you know, I've thought about this. I think yeah, the additive case gives you this kind of nice thing that you can kind of don't depend on the previous premise, that to synthesize each branch, but I haven't actually really looked into it much. I think it would be something really useful. Yeah. Yeah, it's mainly getting it working first would be the main thing.
That's great. All right, thanks, Jack.
Thank you.
So our next talk, which I think is ready to go, is by Daniel Marshall, also a PhD student at Kent. He's going to talk about graded session types.
All right, so it seems like people can hear me all right. So I'm just going to stay sitting here because that's how it's going to work with my microphone. So this is a sort of repeat of a talk that I gave at Places, the workshop. It's not really a repeat because it's been cut down quite heavily for this. It's just going to be kind of a whirlwind tour of what we did, and if you're interested, you can go and check out the extended abstract, and we're working on an extended version of this as well. So there'll be more to see soon. And the idea is basically, well, as we've seen earlier in a lot of talks today, as has been mentioned probably 6 or 7 times by now, graded types are kind of an extension of the idea of linear types, so they let us express things more precisely than linear types do. And, well, we want to be able to do the same thing for session types, so for communication, for this idea. We want to be able to be more precise in what we can say about these as well. So what session types really are, and actually I think, okay, that's apparently how I changed slide on here. So first of all, we're going to be working in Gradual today, obviously. I'm one of Dominic's PhD students, so this was joint work with him. And this is basically the same slide that Jack just had, but you know, here you go again. Gradual is a functional programming language. It has these cool features. Linear types are the default. We also offer things like index types. That's a lightweight form of dependency where your types can depend on things like natural numbers. And we also have graded modal types, which are an extension of this idea of linearity, where we can precisely say what behavior we expect our values to have. So going back to session types now, this is how session types look in Gradual. So first of all, what is a session type? Very quick reminder. They are types that just specify the exact protocol for how a communication is going to happen. So this is based on the GV calculus. The exact formulation is the one by Lindley and Morris for the session type fans in the crowd. So the idea is that you have this type of channels. It's what we call L-chan in Gradual. And the type is parameterized by the session type, which tells you the protocol by how that channel is going to be used. So for example, we have this send function, where we send one value along the channel that is, the session type says we need to send something. So we give it the value of type A, and then we carry on with whatever protocol is left. Similarly for receiving, if the session type says we need to receive, then we receive a value of type A, and we also have the channel to keep working with. This may be the important one here, is the fork function. So this is how we get a new channel to work with. All channels have 2 ends, so this dual thing is representing this idea of, well, if one end we need to be performing a send, then the other side we're going to receive what we just sent, and vice versa. So what fork linear basically says is, tell me what you want to do with one end of the channel, and I'll give you back the other end, and then you can use that one. So fork linear is just setting up a new session with 2 ends of the channel. And then finally for this talk, the last important one we're going to look at is this close function. This just says once we reach the end of the channel, the session type says we're done, then we can just get rid of the channel, we're finished. We also have these other things for different types of choice. So these are called internal and external choice. Again, for people who know about session types. We're not going to use these in the examples in the talk, so don't worry if you haven't seen session types before. The top 4 are the important ones here. So actually let's go over to VS Code now, which is on the screen, which is great. So here just a quick look at what session types look like in Gradual. I'm glad we had one talk where we used the light theme for Gradual and the other talk where we used a dark theme, so everyone's happy. Let me just zoom in a little bit more. So here we've got this client function here. So the session type here tells us we need to send a boolean, receive an integer, and then finish. So the nice thing about session types here is we basically just do exactly what the type is telling us to do. We really don't have that many options for what we're allowed to do here. So we send a boolean, we then receive this n, which must be an integer, and then we close the channel. And similarly for the server, which is going to be dual to the client type up here, so we have to receive a boolean and then send an integer and then finish. So that's exactly what we do. Notice some of the things that Gradual will stop us from doing here. So here, this sort of if statement where we're sending the integer is depending on the boolean that we received. We have to do that because if we just threw away the Boolean and did whatever we want to here, then we're going to get an error message. And the reason for that is because we didn't use this Boolean, which is a linear variable. So all values in Gradual are linear by default. And similarly, if we'd done something silly up here, like try to close the channel before we're done with it, then that's again going to give an error because Gradual is going to make sure that we follow the session protocol that we're given here. So it's telling us, well, we were supposed to be sending an integer, but now it's looking as if we're just closing the channel, and we're not allowed to do that. So that's just a glimpse of how Gradual makes sure we're doing the things that we're supposed to be doing here. And so here's the example of how that actually works in practice. So what we're doing is we're forking a new channel, like I showed before. So let me just look at it quickly. So just looking at the type of for linear again. Here we are, we need to tell it what we're going to do with one end of the channel, and then we get the other end back here. So when we fork, we're just using the server and the client because we can see that these have to be dual to each other. This one is doing the send first, this one's doing the receive first, and so on. So we're just applying one to the other. And if we actually do this, then what we come out with is this value 1. So why did we get 1 here? Well, the Boolean that was sent by the client was true, and this if statement is just checking against that Boolean, and since it's true, we get the 1 rather than the 0. So everything is working as we would expect it to. So moving on to the actual point here, what we did, our actual conclusion in this is we've got linear session types here, and that's great, and that's what exists in a lot of languages. You saw something very similar in the Idris talk earlier on. But since we've got these graded types in Gradual, we can say a bit more in the types. Maybe we want to apply this to the world of session types. Maybe we want our session types to be able to tell us a bit more and express a few more behaviors for communication without losing the guarantees that session types give us. So with regular session types, they're linear, and that means that we get these guarantees such as communication safety, deadlock freedom, and so on. If we want to express other communication behaviors that aren't linear, that's fine. We could just use nonlinear types, but then we lose all the guarantees. So what I'm going to show you is the way that we've used grading to keep some of the guarantees whilst still letting us express some more behaviors. So let's hop back over to the slides, hopefully. Yes, there it is. Hope that worked, because it didn't work last time I gave this talk. So here, just bringing that back up, is the first example of a nonlinear communication behavior that we're going to want to express. So this looks quite complicated, this fork nonlinear function. So just going through it slowly, ignoring the things at the top for a minute. So the actual type of this function, these, no, it's not, but the second 2 lines of the types image there, you can see that it's basically the same as for linear above, but we add this grade R onto the channels. So we're saying that the first channel is going to be used R times, say, if this is a natural number. That means the second channel also has to be used this many times.
Sorry, what is the exact semiring?
We'll get to that in a second. We'll get to that in just 1 second. So, yeah, so R is just telling us that these have to be used in the same way. Now, you can see that above, there are some constraints on how we can do this. So this doesn't apply to all channels and all protocols, or all semirings. So first of all, we've got this single action constraint up here. So this only works for protocols that have a single action. So either we send and then we finish, or we receive and then we finish. If we have a more complicated protocol, then we could, for example, if this is something that we're using twice, then we could send once and then someone else uses it to send once, but it was expecting a receive by that point. So that doesn't work, which is why we need this single action constraint. The other constraint here is this exact semiring one, which is a bit more subtle maybe. So we saw some examples of semirings from Jack's talk. We have the semiring of natural numbers, which says we have to use the channel exactly this many times. That one is fine for this case. But we also saw a semiring of intervals of natural numbers, where we can say, well, this could be used anywhere between, say, 2 and 5 times. That semiring is not an exact semiring. We shouldn't be allowed to use that here. And the reason for that is, well, if we have a client and a server, say, we use the client twice and the server 5 times, then something will be expecting a receive, but it will never get it because we didn't send enough values. So we have to be careful here again and make sure that whichever way the first channel is used, the second channel is used in exactly the same way. That's what we mean by exact semiring. So the communication behavior that this gives us is it lets us put an arbitrary grade on the channel, subject to these constraints. which lets us have, for example, channels that we can reuse some number of times rather than just in a linear way. So again, hopping back over to Visual Studio Code, I'm not going to have time to demonstrate all of these communication patterns, by the way. We're just going to do this one, and then the others I'll just kind of show you that they exist. So what we have here is this function which sends a vector of a given size, and also a function which receives a vector of a given size. So here we see an example of what I was talking about with index types earlier on. So the vector here is indexed by its length, which is this n, the natural number here, type signature. So the actual function definition here is maybe not that interesting. It's just recursion over the vector. So we send each element individually. But we have this n here, this grade in the type signature. So this is saying that since we have n elements in the vector, we're going to have to use this channel n times to send each element. And it's similar in the receive case. So again, we have a recursive function here. We want to receive this vector of n things from the channel, which means that we're going to have to use it n times. So maybe a small detail here is that we don't have fully dependent types in Gradual, so we have to pass this natural number in at the type level to the function receive vector, rather than just being able to, for example, receive it over the channel, something like that. Maybe that's something to look into in the future when we have a language that can express all these things and also has fully dependent types. Maybe that's coming one day. So again, here's just an example of how this is used. You can see this is very similar to the actual example from the previous file, except that here we can't use the fork linear primitive because fork linear requires that the channels are both used in a linear way. We don't have any grades on these channels. So that's what this fork nonlinear primitive is being used for to make this work. So if I just load this in quickly, or not so quickly as the case may be, then we will be able to run this example function. Oh, I didn't actually. I can't just run the example. I didn't. Yeah, I've got this main function here that actually applies the example to a vector. So if we pass this vector in, then we get the same vector back out. You know, that's what you might expect. All we did was send a vector and then receive the same vector. So that's not the most exciting result in the world. But you know, it's exciting that it worked, that we were able to do this and express this behavior over types in a safe way. So just jumping back over to the slides. There are two more communication behaviors that we've represented in this way by adding these extra primitives that have grades in the type signatures. I'm not going to be able to demonstrate them fully because I've got time, but just to quickly show them off. So here we have the idea of what's called a replicative server. So looking at the grades here, well, the idea here is that we have one server. That server has some grade on it that allows it to be interacted with by multiple clients in the end. So the result of this function, the bottom one here, is a vector of clients, and each of those n clients can be used either 0 or 1 time. So we can choose whether or not to use the client. So what that means for the server is the server has to have this grade of 0 to n, this interval 0 to n. And that means we don't know how many times it's going to be used. It could be used 0 times if none of the clients get used. It could be used n times if all of the clients do get used, or anywhere in between. So this is just expressing the idea that we have one server, lots of clients, and each client gets to choose whether or not it interacts with the server. And third and final communication pattern here is the idea of multicast sending. So here, rather than grade being on the channels or on the server or the client, here the grade is on the actual value that we're sending on the channel. So we have this graded type level function here on the top line of the function. That's just applying whatever natural number grade here to the actual payload that is being sent on the channel. So since we're applying that grade, what we end up with is a vector in the end of, again, n receivers who are going to receive that graded value, and each one of those receivers can use the value in a linear way. And since that value has the grade of n and needs to be used n times, then all the grades work out. So there's the 3 communication plans that we've implemented in this way. There are probably more that we could implement. That's what we've got for now. I've got this slide here about, I guess, a technical detail. Last one before I wrap up. If you're familiar with graded type systems, you might wonder, well, why don't we just have the fork linear primitive and then promote it to be able to deal with whatever grade we want? And this would be fine in a call by need or name setting, but the system here is call by value, Gradual is call by value by default. And we run into problems when we do this because we can get deadlocks from two places trying to interact with the same channel in different ways. So instead, we have to restrict promotion and use these specific set primitives to interact with our channels. So to wrap up, what we do is we combine the ideas of session types and graded modal types to capture these nonlinear behaviors, but in a controlled way that still keeps guarantees of freedom, communication, safety. And we introduce these primitives to do that for these different patterns of communication. So thanks. And I will try and turn my sound back on somehow. Maybe I can do that on here instead.
Great, thank you, Daniel. I think we'll have to take the questions offline there. But thank you very much. I'm sure the people who are there can ask you questions later, and other people online can email. There's a paper as well to look at. So the next talk is Michael, who I think is setting up there, hopefully. Oh, I can see that. Great. Ooh.
Does this work?
Okay. Yep.
It seems to work.
Okay. So thank you very much. Our next talk is Michael Arntzenius, who is from the University of Cambridge / Birmingham. I don't know if that's still accurate, Michael. And the title is One Weird Trick for Type Checking Coeffectful Programs.
Yes, well, I said it was going to be about how you could use modal subtyping to do type check, something about modal subtyping. But yeah, I decided a better name might be One Weird Trick for Type Checking Coeffectful Programs, because that's basically what it is. And I found this trick working with posets. So working in a language where types are understood to be posets and where functions are always monotone. So all functions, the function type is monotone maps between its argument and its result. And so, okay, this is a perfectly fine, way to build a language. The poset is a Cartesian pose category, so you get simply type lambda calculus. Another way of thinking about it is if you compose monotone functions, you get monotone functions. So if everything's monotone, then everything is monotone. But what if you want to have non-monotone functions? So the answer to that is you can use modalities, specifically 3 of them. One of them is the identity, that's boring, so that gives you monotonicity, right? Okay, great. What if we want to capture order inverting functions, which I call antitone functions? Well, that's just a function out of the same type with the order inverted. So if we have a mode, so if we picture I'm gesturing to this, but the people on there aren't going to be able to see me. Can you see my mouse pointer?
No.
Yes.
All right, right. Okay, I'll use the mouse pointer.
Just blind.
Sorry, what was that?
I can see it now.
All right, cool. All right, yeah. So if this is a picture of our type A, right? So the points represent elements and the arrows represent less than or equal to relationships. This is a Hasse diagram, right? So op A is the same elements, but with the ordering reversed. So what was lesser is now greater. And a function out of op A is now order inverting. And then box A is going to be the same type, only completely discrete. Nothing is less than or equal to anything else. And this is a very boring order with the very useful property that a function out of a box type is just any old function. A monotone function from box A to B is any old function from A to B. And so we can think of non-monotone functions as a special case of monotone functions, right? So this is nice. Using modalities, we've rediscovered non-monotonicity inside a monotone world. All right, is that reasonably clear? Because if this is not clear, nothing else in the talk will be clear. Yeah.
So
good.
The reason for the last one is the less strict behaviors on the trend.
Yeah. So since box A, x is less or equal to y at box A if and only if they're equal, right? So that trivializes monotonicity. Yeah. Any questions from the people on Zoom? Yeah. We'll get to that later. Maybe, if I have time. All right. Nice thing about these things is that they are graded coeffects. So they are a partially ordered semiring. So the order is like so. Box is the least thing, and then idnoff are above it. To add things, that is to say, if you use a variable multiple ways, the way that you figure out the way you're overall using it is you take the meat in this meat semilattice, and I've drawn that here. And if you use a thing in sequence, you compose these functors, and these functors happen to be closed under composition, right? So like box followed by box followed by op is just box, right? Box followed by anything is box. So anyway, they have these fairly boring meet and compose operations, but hey, that means that we can apply a bunch of prior work on graded coeffects. Problem is that if we do this, we get entirely too many square brackets in our terms. You have to annotate all your code whenever you want to pull something out of one of these modalities and whenever you want to put it back in. So here is a very explicit version of mapping over a set. So I'm assuming I have some type of finite sets of A's, and it's ordered by set inclusion, right? I'm not going to go into detail about why this type checks, but basically sets form a relative monad over box. So you can use basically do notation with them. And using that, you can write a thing that maps over a set. And it basically says, okay, I'm going to map the function f over the set S. Well, first I have to need to unbox f, because I'm not claiming to be monotone with respect to f, so it's boxed. Then I have to, for every element x of the set S, well, x is actually going to be boxed because the set is discrete with respect to its elements. So I need to unbox that. And then I need to return, and that's discrete again, so I need another box. And then the function I'm applying is discrete, so I need another box. And I have all these square brackets muddying up this perfectly clear, simple program that I would like to write that doesn't involve any square brackets. So how do we get rid of all these square brackets is what I want to do. I want to write these programs that are modal without having to write any term annotations to convince my type checker that they're actually monotone or non-monotone. And the solution is that we can convert into and out of these modal types automatically by using subtyping. Now, what does subtyping mean in a world where types are posets? It means sub-posetting, right? So box A is a sub-poset of A because it has the same elements, and all of the less than or equal to relations in box A still hold in A, right? So anything that was less than or equal to in the left-hand side still is in the right-hand side. So, okay, we can convert out of box A using subtyping, right? You can use a box A anywhere you want today. But the other way around doesn't seem like it should work, right? Like A is not a subtype of box A. You can't do that. The solution is you want to make subtyping modal, right? See, the way I think of it is, what does subtyping mean? So I'm using less than or equal to for subtyping, right? What does it mean that A is a subtype of B? It means that the identity function maps from A to B, right? It means I can just convert A's into B's by applying the do nothing function. Well, we're in a world that cares about monotonicity. It cares about coeffects. So what coeffect does our identity function have, right? Is it a monotone function? Is it an antitone function? Is it a discrete function? So what we're going to do is we're going to extend the subtyping judgment to say not just A is a subtype of B, but A is a subtype of B with mode T. So I use T, U, and V to stand for my modes, or the grades in this case. And that means that the identity function maps from TA to B. So this is the key idea. And if you do this, you can actually implement a little type checker. I've done it bidirectionally. So the judgments that we have are what I just showed, right? Like if A and B are types, find me the mode T such that TA is a subtype of B, if there is one, right? Find me the best one in particular. And then I'm going to say, okay, if I have context gamma that tells me what types things have, and a term E and a type A, I can check whether E has type A. And I'm going to discover at what modes each of the variables at gamma is used, right? So we're going to get out a vector of usages U that says, you know, here's how I use this variable, right? I used it id monotonically, or up anti-monotonically, or box, meaning discretely. And then we also have inferring, an inference judgment that says, okay, I can actually figure out the type of this thing, right? I don't need to check, I don't need to be provided the type, I can figure out the type of the thing, right? And the key thing is that in both cases, whether we're checking or synthesizing the type, we're always synthesizing the modes, right? And this seems to work out. I just tried it because I thought it would be nice, and it worked out. And so then our subtyping judgment actually gives us box introduction, right? So our subtyping judgment now has to deal with these usage modes. And it says, okay, if E checks at type A, but I want to use it at type B. E synthesizes type A, sorry, but I want to use it at type B. Well, I need A to be a subtype of B. That's what you normally do here. But now A can be a subtype of B with a particular mode T. And what you do is you slap that T onto the usage modes. You pre-compose it with all of the modes that the variables in U are used at. And this gives you box introduction because box A is a subtype of box A, right? A is a subtype of box A with the mode box, right? This is just sort of obviously true. Box A is a subtype of box A, right? But now the rule tells us you need to put the box onto gamma. And so this is basically saying, well, if gamma entails A, then box gamma entails box A, right? Which is just like duh. Right? And so just by doing this, we get box introduction and box elimination for free as a kind of subtyping. Of course, there's a lot more to it than that I could not fit into a 10-minute talk. The advantages of this technique are we have no more explicit boxing and unboxing in our term syntax. It just happens. You need type annotations, but you don't need term annotations. You also don't need to put modes onto your arrows anymore. You just, normally to get this property where you don't need to write these term annotations, you put annotations on your arrows instead. But I don't need this anymore. Instead of having A arrow B with an annotation T, I just have TA arrow B, right? And I think I figured out how to do pattern matching in this context, but it's kind of complicated and I'm not entirely sure I got it right. And so like the con here is the rules get really quite complex. Function subtyping in particular is kind of a mess. And there's more rules that I haven't shown you. And also, in order to make this work, all your modes kind of need to have left adjoints, which in this case works out. All the modes I show you do have left adjoints. I just haven't shown you the mode that is a left adjoint to box. And that is the thing where you squish things together if they're in the same connected component that Bob Atkey mentioned earlier. So, all right, open questions are like, is this really complete? Can I do everything I want to that I could do with explicit annotations in the system without those annotations? I don't even know what I would need to prove to show that. I think it's true, but yeah. Does this extend to other gradings, right? I've done this for monotonicity. Can we use this for other gradings than monotonicity? Like, I don't know, linearity, I don't know. And like, can this go beyond being just simply typed? And can we have some form of polymorphism here? And like, if the answer to these last three questions is yes, then I think this is an idea with legs. If the answer to any one of them is no, then that's a bummer. So, right. I also, how much time do I have left?
Well, we've got like sort of 4 minutes left to the end of the slot. So if you want questions, then yeah,
right.
It's up to you.
Implementation, it works. It can tell me the ways things use modes, the modes at which things use variables. For example, it's telling me here that plus x, like adding x to y minus x uses x discretely and y monotonically. So if people want to ask questions about that, they can. If people want to ask questions about anything else, they can.
Awesome, thank you. Right, let's take some questions.
Finbar seems to have a question. Oh, I should look at the chat probably. Where is the chat?
Someone's got their hand up. Oh, it's Max, I think. Max, go ahead.
Hi. Can you make sense of this using the functors as type refinements idea, where you're looking at it as functor from posets to sets? Because they have an interpretation of subtyping there where they say that there's a subtyping if it's a lift of the identity.
That's interesting. I don't know because I haven't been exposed to that work. I should write that down.
Yeah. And also, what's the left adjoint for op?
What's the left adjoint for op? Op is left adjoint to itself.
That's what I guess.
Yeah, very neat. So is identity, of course.
Yeah.
All right. So this was functors as type refinements.
Yes, functors as type refinement systems. Paul-Andre Mellier, Noam Zauberger.
All right, and they have some handling of subtyping that could be relevant here.
Yeah.
Cool. All right. Are there any more questions?
So I guess a sort of speculation then is that maybe this works. This seems like it could work for a kind of class of gradings. I wonder whether there's something to do with the role of one. I mean, of course, all semi-ring like necessity graded things, you need to go sort of box 1A to A is defined, but whether you can sort of go back, whether it's isomorphic to A, it holds for some semi-rings, not others. And I need to look at the rules in more depth, but I had a feeling like maybe that was an essential property here.
That was definitely something I was assuming because it's true in my setting, so it could be.
Yeah, so that's true for like the natural number grades where you're using equality for the pre-ordering, because then, you know, a linear A is really isomorphic to a box 1A. You know, it's exactly going to be used once. But then if you have less than equal ordering, then that's not the case, because box 1A might be, you might have used subtyping to go from a box 0A.
Right, yeah, less than or equal, the box less than or equal to 1A is not isomorphic A. But you can fix that if you just join in the natural numbers to the same system, like they can exist if you're in the interval semi-ring.
Yeah, so I think it would work for a certain subset. I mean, this is very neat. And this, you asked a question yesterday, which kind of goes into this a bit, you know, like, you know, how do you deal with all the boxing? And I think this is a kind of a neat, completely different solution to what I had, sort of the answer I gave yesterday. So, yeah. Any last questions?
I think there's a question from in the room. Yeah.
So one of the observations for this is that some arguments
yeah, so like being monitored.
Could you repeat the question, Michael? And go to the microphone. Yeah.
Similar to the different language. There's direct detector with modalities of people.
Okay.
And they kind of have these people talking about
yeah, that makes sense. I guess I should repeat that comment for the people on Zoom.
Please do.
The like question or comment was like, being monotone is kind of like being covariant, and being antitone is like being contravariant. And some people have studied how to check things like this in the context of, you said directed type theory?
Yes.
Yeah, directed type theory. So more, I have heard of directed type theory, but I have not studied it.
Different way of thinking about the same thing.
Yeah. Yeah, and I think similar stuff has also happened with like, you want to check strict positivity when you're defining things inductively in your like thing. So that's a similar sort of thing, right? Except strict positivity is even stronger than monotonicity. That's why it's called strict. I don't know why it needs to be strict, but apparently they want it to be strict. All right.
Okay, let's thank the speaker again. Okay, so we are at the final talk today. Vikraman, who is there in person.
Change the speaker this is on so people can hear. Oh, yeah, Vikraman, how are you going to present?
Yeah, hello.
I heard something briefly just then, and now it's disappeared.
Okay, can you hear me now?
Yep.
Okay.
Okay, so thank you very much. So this talk is by Vikraman Choudhury, who, wait, I've slightly lost track of Vikraman where you are at the moment. You're
sorry. Yeah. I'm
finished
at
your PhD.
Yeah. Yeah.
You're a postdoc at Glasgow, right?
I'm a postdoc at the University of Glasgow. Yes.
Great. So, and he's going to talk about weighted sets and modalities. Thank you very much.
Okay.
It has my face there at the corner still.
Yeah, I don't know how to.
I'll just make like a.
Okay.
Yeah, great.
Right. Okay. Okay. Yeah. All right. All right. Hi. Yeah. I don't know why my video is not. Okay. Okay. So yeah. So I'm going to talk about weighted sets and modalities. So this is we've seen a lot of talks about syntax for graded monads and comonads and different axiomatic models for them in terms of graded monads and comonads on sets or certain kinds of categories with structure. What I'm interested in is an actual demutational semantics for these modalities. So can we build an actual category where we can define these modalities, and can we prove semantic theorems about them? Okay, so so as we've seen many times in this workshop, programs have these kinds of intentional properties that can't be captured using the syntax of normal structural type theory. So things like effects and security levels and space-time usage and all these things. And we can use graded modalities, so graded comonads and graded monads, to make this information first class in the syntax of the language. So where do we? So when we actually build a model for this language, can we define these modalities? So why is this an interesting problem? Well, let me tell you about very old ideas from linear logic. Probably one of the most famous modalities is the bang modality in linear logic, where so the original motivation of linear logic was that Girard wanted to decompose the function space A to B using these two operators, the bang and the lolly. So A arrow B becomes bang A lolly B, and I think it was 1985, and in 1987, Girard wrote some papers about normal functors and analytic functors, and since then, like, it has been a very productive area of research, and linear logic has many applications. But at the same time, finding actual models of linear logic where we can interpret the bang and the lolly is also a difficult problem. So let me just highlight why. So linear logic has the first model that was basically folklore and never published was the relational model with the free commutative monoid monad lifted to relations, which gives you the bang, and the internal hum of the category of relations gives you the lolly. The relational model is not good because it is degenerate, where two different tensor products coincide. And so there are different ways to improve the relational model using more operational understanding of what it means for cut elimination and all these things. So for example, Girard came up with the idea of coherent spaces, and then there are different kinds of coherence conditions you can put on them, which led to finite spaces and totality spaces. So these are very syntactic models, or I should say, these are models which are very much familiar to us because they're based on just sets and functions and conditions in them. The relational model also has, there is an interesting line of research with the generalized species of structures, which is a categorification of the relational model, and so on. We can move to a completely different class of models where you take vector spaces and linear maps, and then the bang becomes a construction called the symmetric Fock space construction. So we have to actually learn some quantum physics to understand what's the model of linear logic. And then there are all the other game semantic models. So the oldest one I know was Joel's Conway games, which was improved by Paul Andre Méliès, and then dialogue games and template games and many others. So these are more syntactic models. So so what is why? So all of these models, there is the original motivation of Girard was to reconstruct the function space. So in all of these models, once you construct the lolly and the bang, you can prove that the co-Kleisli category of, so bang is a comonad on your category, and then you take the co-Kleisli category of bang, and you get an actual function space. So you get a Cartesian closed category after you take the co-Kleisli of the bang. Okay, so so my question is, can we ask? So why I would say that this is a really important theorem that like it says something about the expressivity of linear logic, that we can recover all intuitionistic functions. So all of this research about graded monads and graded comonads, can we prove a expressivity theorem like this, where we show that after constructing all these modalities, we take some Kleisli or co-Kleisli, and we get back Cartesian closed structure. Okay, so so to do that, let me start by trying to build an actual model where we have a language with graded monads and comonads. So if we start on sets, so the computational lambda calculus, there are lots of interesting monads on set: the reader monad, writer monad, state monad, and these are, we program with them every day, and set. So set is a nice category where you can write graded monads, but there are no interesting there are no interesting comonads on set, or at least none that I know of. And so if we actually want to build categories where we have comonads, we need to make this notion of resource a part of our model. So we need to enrich our models with some notion of resources, and and once we do that, our categories should have enough structure to interpret all the linear functions or intuitionistic functions, as well as the graded monads and comonads that we want, and we should be able to recover some sort of theorem like the one I showed earlier with the function space being Cartesian closed and all that. Okay, so yeah, so there's an easy way to do it. Well, historically, the free sheets have been studied very well. So you take some notion of some small category L, or some lattice, or some coset or a lattice, or some other algebraic structure which has some notion of resources. So it could even be semirings or some other monad or resource monads, and you can take presheets on this algebra. So presheets are nice because you take presheets and you get presheet topos, and you can do all of dependent type theory inside it. And in this workshop, we've seen graded sets and graded monads. In Dylan's talk, for example, if L is a discrete L is just a set, then functors from L to set are L graded sets. Okay, so let me tell you something which is neither presheaves nor graded sets. It lives somewhere in between. So the way I like to think about them is to think about completions of categories. So L is just an algebra. It doesn't have any of the nice structure that you have in a category. So presheaves can you take the free co-completion. You take L and you freely add all co-limits to it. That gives you presheaves. But in between L and presheaves of L, you can factor this through other completions. So so for example, the one I'm going to talk about here is you don't complete under all co-limits. You complete only other co-products. So if you notice, so if you have finite limits in L, the presheet construction actually factors like this, but that's not important, right? So so the free co-product completion is usually known as this familyless construction. So if C is a small category, I take the objects of fam C to be collections of sets of sets X, which are weighted in the set of objects of C. So I am writing this arrow W of X to objects of C, and so this looks almost like a slice category over C, but when we take the morphisms, we don't require them to be strictly equal, but we add these two cells. So we say we have these squares or degenerate squares where every time we write a function from X to Y, F, we also have to give it a two cell, which makes this diagram commute. So that yeah, so these are the morphisms, and Famo C is the small co-product completion of C, and it has a universal property, which is that anytime I construct, anytime I have a category D, which has co-products and a functor from C to D, I can uniquely extend it up to natural isomorphism along from Famo C to D. So this is a nice universal property to have, and you can use this to actually calculate things. So this is not, I wanted to mention some, this is well known in category theory, but unfortunately, it was studied in the 70s by Diaz in the context of like multi-adjoints and multi-monads. But all that work got lost because the papers were in French, and you know this. So I don't know who to attribute this to, but the oldest papers I know are from Diaz where studying this. So in particular, like he defined this notion of multi-limits, which is that you take limits, but they don't have to be unique. They have to be in some family L, in some collection L. And so Famo C has limits, and only C has multi-limits, and so on. So I don't want the whole general story, but let me tell you a special case of this. So if I don't give you any weights, so it's Fam of the trivial category, I just get back sets. Okay. But instead of the trivial category, I'm going to take a coset, which is my notion of resource. So objects are sets which are weighted in this coset L, and the only functions I'm allowed to write are the ones where the maps can expand along the weights of the input and the output, or I can take the opposite of L, and then I get the contracted maps where for every X, I'm only allowed to write, so for X and Y, I'm only allowed to write those functions which can never use more resources than the input. So I call these weighted sets. So there are two categories of weighted sets, and again, people have studied categories like this. So the oldest, sets which are valued in lattices or cosets are so Lovier's norm categories, and then some weighted categories which are just enriched weighted sets, and then there's this whole work on fuzzy sets and multi-adjoints, and then quantile enriched categories. So the thing that I'm interested, so in most of these works, there are people who are interested in monadal structure, Cartesian structure, but I'm interested in higher order functions. So I'm going to look for Cartesian closed structure. So so for my notion of resource, I'm going to use a complete Heiting algebra, which means so it's a Heiting algebra which has all small products, which I'm writing as meets, and Heiting algebra has an exponential. So I'm writing, so you can think of the exponential as a difference operator. So so if you start from a complete Heiting algebra, you can write down what a weighted set over what structure weighted sets over L have. So they happen to have all the structure you need to give a Cartesian closed category. So they have terminal objects, they have products and exponentials, and co-products, which is so if you start with a complete Heiting algebra, you get all the structure you need to make a simply typed language with. But you can go even further and actually get locally Cartesian closed structures. So you start from pullbacks, which are easy to define. You just take the pullback set and assign the weights accordingly, just by taking the meet. And then there's a way to describe the entire locally Cartesian closed structure, which is so you take so the way I did it is by giving an internal language for working with families of weighted sets. So so if you have a morphism F from B to A, you can define the reindexing functor and take left adjoint and right adjoint, this gives you pi types and sigma types, and further they also satisfy the Beck-Choudhury conditions. So here is a model of an extensional dependent type theory where you have where all the types have weights associated with them. So what is an actual application of this? Well, there were these length spaces which Martin Hoffman wrote about a few years ago, which where he uses this structure of natural numbers with infinity and min and max for the beats and the joints, and this happens to be a complete Heiting algebra, and from this you can recover his entire semantics of length spaces, although he only uses the Cartesian closed and the monadal closed structure. And the reason I'm interested in is because there's this capability spaces construction from 2 years ago that I wrote about, and that uses actually the power set lattice. So power set happens to have two different Heiting algebra structures, and the one where you take the supersets actually gives you this capability spaces where you can track the capabilities of the capabilities that are used and make sure, yeah. So you might have seen in Jonathan's talk earlier where they described the system called system C. So the denotational semantics of that is actually given by these capability spaces. Okay, so so yes, finally, let me just quickly tell you. Okay, so now that we have this flow set with a partial order on it, and we can use this to get modalities. So the way to think about these is that the comonads are going to restrict what you can do, and the monads are going to give you operations that allow you to do more. So there's a principled way of defining these comonads, but I will just tell you an example of a graded version of this box modality, which is you take any weighted set and you just for any p you just restrict to the subset where the weight is less than or equal to p, and there is a co-unit and co-multiplication, and this gives you a left exact idempotent comonad, and it also admits due to the Heiting algebra structure we started with, you can get these the semiring identities, but now with meets and joins, and they satisfy the graded monad, the graded comonad axioms. At the same time, you also get so we have monads on set, but to lift them to weighted sets, we have to give them. We don't want the canonical lifting with the Cartesian structure. We actually want to give them a specific weight to track how much of the how much computation that you want to do. So, for example, an exception monad would have this underlying set, and anything inside the exception monad will always be allowed to throw an exception. So we add the weight p. Or, for example, a writer monad would have to, for example, writer monad that uses variables from C to print to some monoid M. You have to define this writer monad in such a way that you track whatever is being printed. And so there's an interesting thing that happens once you define these, which is these monads and comonads actually interact. So for example, some of the interaction laws that I calculated where this cancellation law where box of T is isomorphic to box, and if you work with the graded versions, so box of P and T of P and Q, oh, actually box of Q. Yeah, so the T gives you P and Q, but the box takes away the P, and this gives you box of Q. Having this interaction law actually lets me recover the original thing, which was I started with the Cartesian closed cache tree. I added a box and I added a box and a T, and now with this cancellation law, I can lift box to the Kleisli cache tree of T, where it's also a comonad. And now I can take the co-Kleisli of this box, and now this happens to be Cartesian closed. So I know this works for the ungraded version, but I don't know if such a thing could also be done for a graded version of this comonad. So yeah, so here's a concrete model.
Sorry, Vikraman, do you think I think we're going quite far over here time? Would you be able to? Sorry.
Okay, this is my last slide. So
okay,
yeah, so
sorry.
here's the model, and so perhaps I could use this to make an actual dependent type theory with graded modalities and these interaction laws or cancellation laws, and it might we might be able to prove adequacy or some sort of expressivity results about them, and perhaps these weighted sets could be used as models of linear dependent type theories. That's fine. All right, thanks.
Great, thank you very much, Vikraman. Pause. Let's take a couple of quick questions before we wrap up.
Yep. The reason is I get this.
Could you repeat the question? Sorry.
So Dylan is asking, why did I complete only under coproducts? I could also complete under filtered colimits or something like that. So the reason is I didn't start by thinking about coproducts. The reason is this: I have this weight function. So the concrete version of free coproduct completion has this weight function, which it doesn't work in free sheaves because you can't just take a free sheaf and assign a weight function. And I don't know any concrete way to do filtered co-completion. So yeah, I don't think there's going to be any weight functions or something.
I have a comment more on the question. This is very nice. You said something earlier on. You said something about there being no interesting comonads in set, which I sort of sharp and take a breath. I think there's some nice comonads in set. You know, do all sorts of kind of containery things, and there are lots of graded comonads in set. Even sort of irrelevance you can do in set with particular graded comonad. But
okay. So I think well, the interesting comonads on set are going to be ones where you take some subset. So you have box of X is some subsingleton, some subset of X such that it satisfies some property.
Yeah, I suppose that might be true. I'm thinking of the graded comonad where you do sort of box 0 of A is 1 and box 1 of A is A and box omega of A is A. So it's like the 0, 1 tons semi-ring, but where the 0, just erases. Does that fit what you just said?
So it's a graded version.
Yeah.
Right. Okay.
Maybe that changes things once you add the grading in. So.
Yes, I think yes. Having the grading probably allows it to be more interesting.
Right. Okay. Okay, great. Well, I think we'll take the rest of the comments and questions offline. So just do some applause. And if everyone can still hear me in person, can people hear me there?
Yes.
Yeah. Okay. Great. So I'll just conclude then this meeting. I just want to say thank you so much for everyone coming in person and online. We made it work. Still pandemic times, lots of sort of changes and people unable to make it and so on. So thank you for bearing with us with technical things as well. And yeah, I think it's just been exciting to see the variety of talks and just lots of really nice breadth and things that all link into each other as well. And I'm sort of hoping to go from here into thinking about writing a Dagstuhl proposal for a Dagstuhl seminar on these topics, because there's just tons of people working in this space in lots of different interesting areas. We could spend a week doing this rather than like a day where we're just very fast talks. So I will send a follow-up email to everyone, and then I'll delete all your emails afterwards for GDPR purposes. But I'll send a follow-up email just to see if people want to join a mailing list where they might hear about other such events on graded types. And I hope to put the video of this online. So if you have featured in this today, I mean, I'll send an email to confirm this, but if you featured in it today in some way and you don't want yourself to appear on the version on YouTube, then send me an email and I will I'll edit you out. My plan is to just upload the edited thing as one piece onto YouTube with then the times as a contents thing, because splitting up will be too much of a hassle. Yeah, and with that, I'll say thanks again, everyone. And I think in-person people are going to get some beer and some food, and I'm going to do that here with the family. So, and thank you very much to all the Kent people, to Mike, to Tori, to Vineet, to Daniel for sort of looking after the things there today, and also for rest of Kent people showing up too. All right. Thanks, everyone.
Thank
Bye.
Thank you.
Thanks, Dominic.